Hello, welcome everyone. Thank you for joining us for today's Optics 2022 webinar. My name is Gausya and I am the webinar host at Continuum Forums, and it is the leading provider of organizing conferences. Hello doctor, can you hear me? Now we begin the webinar with the opening plenary talk by Professor Jigang Chen, Nankai University, China, presenting on the title, The Interplay of Topology and Nonlinearity in Photonics. On behalf of Professor Jigang Chen, I am going to play his video presentation.
Hello, everyone. Thanks for coming to my talk. My name is Jigang Chen from Nankai University in San Francisco State. So I'll be talking about nonlinear control of topological state in photonic structure. I'd like to take this opportunity to thank organizer for inviting me. I also want to thank all my collaborators here. So here's the outline of my talk. Mainly I'll talk about nonlinear control of logic state, nonlinear trilinear PD symmetry, and high order topological state. We all know that topology of physics is very interesting. It's the matter of physics. In 2016, Nobel Prize in Physics awarded this year. And it's the same then from one of the Nobel laureates for this concept, photonics, proposed that using photonic crystal can create unidirectional waveguide. This idea soon was realized by a group in MIT in 2009. Later, there's a lot of experiment demonstration focus from microwave to optical wave demonstration of photonic topological insulators. As listed here, some of the examples is your optical photonic crystal, helical waveguide arrays, periodic coupled resonators, and other different platforms. So this actually driven the field into a very active photonics frontier. There are several reviews already in topological photonics, including the one in Nature Photonics and the modern physics. There are quite a few special issues on this topic too. We have also edited a special issue for light and science, including a collection of about 20 papers on this topic. Recently, with Professor Marty Seki, we also wrote a perspective article for the New Journal Life on the area discussed is also topological photonics. So they say, what is the motivation, or what is why the topological photonics is so interesting? First, from an application point of view, I'll just give a few examples. The first one is topological fiber, which is going to be dramatically different from the conventional fiber, either based on the total reflection or based on the band gap guidance, as in the photonic crystal fiber. So topological fibers supposedly will have no backward reflection, so it will support unidirectional propagation. Recently, by the way, the idea was proposed by a group in Chinese Academy of Science, Institute of Physics. Recently, it's about direct vortex topological photonic crystal fiber, which supposedly can support super broadband and single polarization, single mode fiber. The other idea is using the concept of topologic physics in the laser design. As you can see here already, many group already demonstrated the concept from one dimension to two dimension, from the one rely on magnetic field to without field, and to the body Hall type lasing. So this is a very active field and indicating that indeed topology photonics may find a real application. So in the fundamental side, very interesting to study the interplay between, say, symmetry and has a global property, topology also, and and with the optical nonlinearity. Right. So in the topological photonics side, we did some work on flat band lattices, unusual, non-trivial localized state protected by the real space topology, and also singularity mapping. But my talk were on the nonlinear side. So when you combine topology and nonlinearity, what is the physics, dynamics you can expect? So this is recent work on light and science, two papers, which I will talk about that. And also, if it's in a non-commission system, about nonlinearity, induce the tuning of PD symmetry and non-commission topological state. That's the work we published in Science recently. So let's first start with combination. Now, topology and the nonlinear optics. As you see already, there's quite a few recent work, including the one by Alex Zamatsky, demonstration of nonlinear induced topological spectrum, and Mishmer group about topological band gap solitons. And Kirsch's group using the topological state to enhance harmonic generation. So in this work, published in Light and Science, demonstrate non-trivial coupling of light into a defect. So, and they introduced the concept of inherent nonlinearity, a nonlinear topological phenomenon. We also developed general framework for the nonlinear coupling dynamics in the topological system. So let me just give a bit of background here. What do you mean topology? One thing that topology photonics know familiar is unidirectional propagation of energy state. Here in the one-dimensional case, it's actually a simple for the SH model when a dimer chain can be in the trivial region and the non-trivial region. So this is periodic array 1 to 2. And if you shift it, you will get this diamond change, right? But depending on how you shift it, you can have the retrieval with what is called the barrel face here in this table. Non-retrieval barrel face will be pi. So this is already known. The one-dimensional topological state, but it does not involve transport of edge state. So a bit more about 1D such lattice here. You can see here the waveguide, the unit series coupling, a unital coupling T and a unital coupling T pi. Basically, it's the coupling inside the unit series and one with the other unit series. So, under certain condition, if the intercoupling is smaller than the intercoupling, if you look at the edge, it really just means this coupling is weaker than this. Then the chain, the system will be in the topological non-trivial regime, which will support a two-edge state called a zero mode, right in the middle of the band gap in the discrete model. So this simple concept was a proposal many years ago, but demonstrating the photonics was done in 2009, the optic system, and then recently it's been used for demonstrating topological lasing, PD symmetry, and even the topological quantum state, all based on this SH system. So in this work about nonlinear control, we optically fabricate a laser right on one dimension. So you can see, you can create a defect at edge. This is a topological defect. It is ended at this, at the weak bonding. Here is ended at strong bonding. So equivalent, you will have the same non-trivial and trivial topological phase, or that phase mentioned before. So then you can send a beam to the edge, right? In the linear regime, you'll see light cannot couple to the defect because of the topological protection. But the nonlinear regime, the experimental, we just apply electric field, photoplastic crystal, then you have the nonlinear induced index change. You'll see a light being coupled into the topological defect. The nonlinearity break the chiral symmetry, the light being coupled into the edge channel. On the other hand, in the trivial case, you have light in the edge and the bulk in the linear region. The nonlinear region, light will not be coupled into the edge. So this difference can also be demonstrated in experiment, even moving the topological defect into the center. This is an example here. The SH lattice with a defect in the center. Then we can launch a light straight into the channel, and you can see there is topological localization in the linear case. So this is the experimentally generated lattice. Then, if we launch a beam from two sides, the linear case will not be able to couple here. Okay. Either these two beams in phase or out of phase. But by applying the nonlinearity, one can see that light coupled into the channel. of course, the outer phase will not be able to reach there due to the non-interaction. So this idea can also extend to the 2D. Basically, here is the illustration. If you send light from a different opposite side, you can tap into the topologic deflection. By extending 2D, will be more like a tapered fiber and induced by non-induced coupling light, the topologic defect, and appropriate conditions. All right, so the next topic is the nonlinear control of higher order topologic state. So in this book, we extend the platform from the 1D to the 2-dimensional case, and demonstrate that nonlinear excitation of high order topologic state, which happens with both the bound state and the beam. And we demonstrate the coupling between the edge and the corner states induced by nonlinearity, and the interplay between nonlinearity, high order topology, and BIC. This is published recently. So let me just give a very brief background about high order topology. It's later, it's Haughty. The idea was proposed to him just 4 years ago. So here, what they mean for high order is that we have a 2D system. Not only we can generate edge state, but we can also generate the corner state. The 3D, not only the surface state, we have the edge state and corner state. Like the high order topologic state, it always has a dimension listed two times higher than the geometric structure of the real system. Right? This is a simple illustration, and already there's some review papers on this. And the concept has been demonstrated in many different systems, including length and matter physics, acoustic, photonic crystal, right? Either in the capable lattice or the 2D SS structure, and even the honeycomb phase here. But not to work, just I have only focused on the linear topological system corner state as a high order topological phase. What about a non-invert? There are two recent independent group, one Alex Bath, and one is ours here. As you can see, so demonstrating the corner state in the capable lattice and in the 2D SS lattice. Of course, these two lattices have different symmetry. One is the C3, the C4, and so they are an interesting fundamental question more different symmetry, especially 2D SS lattice. It also has the carriage symmetry here. To identify the high order topological phases. So our work, and address the question: the corner state survive the system. What will happen if apply the nonlinearity? And nonlinearity introduce transition between corner and edge state. This is particularly interesting because if you do theoretical analysis, you will see that the dark state here forming the band, a block band, and the green one here of edge state, then right in the middle, the red one, corner state. This is the tuning of the coupling coefficients between intra and the intercells. So when the C is less than 0, this regime is a non-trivial regime. In a non-trivial regime, you can see a corner state embedded in the band called, it's also a bound state in the continuum, which of course or has been studied theoretically. So here is the demonstration that in such a system with a weak nonlinearity, it can do the transition from this corner state into the edge, but only in the continuum will not dissipate into the bulk, or very weak coupling the bulk. When the nonlinearity is high, it will localize into the corner. So here shows the linear case, say typical the block state and a different condition. Since the non-trivial case in the corner state, and in the square lattice, you do not have this localized state in the corner. That's all bulk mode. This is the trivial regime. As you're changing the coupling coefficients, the difference between the coupling coefficients of inter and interspheres. So interestingly, is when you put a nonlinearity, this corner state as a BIC can be driven by the nonlinearity coupled to the edge state. Theoretically, we can show that actually it's undergo periodic beating between the corner and the edge state. So you can see here, there's no coupling or energy dissipation into the bulk. The higher nonlinearity, the local corner localized to solid. Here's the experimental demonstration with 3 different cases: the non-trivial lattice, the square lattice, the trivial lattice. That's the corner is the side. We send beam to the excitation. You can see in the linear chain here as a corner state localized in the non-trivial lattice. A simulation here, especially if you go to longer propagation distance, you see a dramatic difference. Light only localized in a non-trivial lattice for the corner excitation. So when you put nonlinearity, you will see the weak nonlinearity to coupling with the edge for both focus and defocusing. When nonlinearity is high, it localize the corners all the time. Defocusing case, it cannot localize. Here's the calculation of the polarization or lack phase, showing that there is a topological transition in the nonlinear case. In this topological insulator system. Okay, the next topic is about nonlinear tuning of the PD topological state. So far we know that non-Hermitian optics has been also active in research here. It has many applications, including wireless power transfer, sensing. It has a very active research field, right, in the 3D image and non-Hermitian optics. So, what about non-Hermitian topological system? When you add a nonlinear effect, already it has been demonstrated that you can create topological state in PT symmetric system. But now, the effect of nonlinearity is something intriguing when you have this three integrants play the role together. The nature does not have a system really to find that this or display or exhibit these features, the nature material. So what we did here is create a system or in the design a photonic platform that we can do to study the interplay between these different concepts. This is the work published recently in Science, a nonlinear training producing a non-Hermitian topological state. It has also a perspective article about this work. Customer notice group. So, what is the main feature of this? Our main idea here. This is a simple illustration showing the scheme of control. So, as you can see, we start in the middle. Middle one is the green that is here. We put green. The central one is a neutron. Okay? Then the continuous waveguide, called the gain side. The sectional waveguide is the loss side. So basically, by doing that, we can have a passive PD system. Instead of minus gamma, 0 gamma, active system. Here we have 0 gamma, 2 gamma. 2 gamma is the lossy one, and 0 will be the gaining one. The gamma will be the central neutron waveguide. So this will be the PD symmetrical system. Then by applying nonlinearity, the focusing case, it will become a non-PD gaining system. That defocusing will be a lossy system. And this dynamics, of course, can go in a different direction, in a sense that you can prepare the system initially does not have a PD symmetry, but by using the nonlinearity, you can bring back to the PD symmetrical regime. So this is a good platform to study local optical nonlinearity to control the global property of PD symmetry of the system. Let's look at the experiment how we do that. This is the nonlinear crystal. Now we can have a ray of light arriving from the top. We have a sectional waveguide. Sorry, it's just too far here. Yeah. So you do one by one. Okay. You can write continuously or sectional waveguide. When you write sectional waveguide, you will use a periodic modulus. If it's continuous, you use the continuous. You're writing. And then you send the problem to the waveguide. So this is the side of the structure created. You can see the green dot here. It's a sectional one. And the blue one is also sectional waveguide, but it has different losses because the gap between the waveguide is different. While the continuous, the red one here is the continuous waveguide, like a gaining side. But this the side of the lattice. It's a passive PD symmetrical system. And then here is the setup, just showing how I do it. Right from the sideway to the nonlinear crystal here. And then you can send another beam to examine the waveguide. This is the waveguide. It's again the SSH lattice. We mentioned it before, one-dimensional. Okay, is this established? Then you can see first, it's a linear system. You send the probe in here. It has the a topology state, which has a symmetrical profile. Okay. But when you put the focusing or defocus nonlinearity, light will go to either the gain side or the loss side, make it a symmetrical profile. This. it's intriguing that nonlinearity can really affect not just the change the index of real part, or it can only change the real part index, rest index, but they affect the potential of both real and imaginary part equivalently. It can, changing a string system from the PD symmetric to a non-PD symmetric system. If you start with non-PD symmetric thin system, as you can see here, right, when you send them approaching the linear regime, it is not symmetric, it's more like the gaming side. But by applying the nonlinearity, the system can here, by applying the defocusing phase, it will become symmetric. This is a linear control here. Same here for the non-PT lossless system. Start with the lossless system. By applying the focusing nonlinearity, it will become PD symmetric. So this is an example showing between the non-Hermitian topologic state. Of course, theoretically, also investigate the two competing effects. One is what is called sensitivity close to the excitement point, and the other one is the robustness of the topologic state. So I don't want to go to the detail, but look at the right side here. The excitation is very close to the central one here, which you will see. It's a robust, and you put the same perturbation here. The perturbation will not grow, but if it's far away from the excitement point, then the robustness is reduced accordingly. So this is the interplay between the nonlinearity and the PD symmetry. When you go to close the excitement point, then many interesting can happen, especially when the system also have a high order excitement point. So yeah, there are many interesting things happen, but in the interest of time, I'll stop here. And skip the high order topological system and the non-Hermitian system, the linear will bring a lot of interesting features. You can see the orbital state and synthetic dimension. So what is the take-home message is that interplay of nonlinearity, topology, and symmetry can bring about the intriguing physics. So with that, I'd like to thank all co-workers and my students. Also thank everybody for listening. That's it. Thanks.
Thank you for that presentation, Professor Jigang Chen. Now moving on to our next presentation by Dr. Jasna Krajinski, University of Belgrade, Serbia, presenting on the title Implementation of Injection Locked Fabry Parrot Lasers as Activation Unit in Photonic Neural Networks. Hello, Dr. Jasna.
Hello.
Can you hear me?
Yes.
Okay. So are you going to give a presentation or I'll play you?
No, you can play it by playback, and I'm here if there are any questions. Thank you.
Okay, doctor. Thank you.
I come from Good morning to everybody. My name is Jasna Crnjanski. I come from University of Belgrade and I will give a talk about implementation of injection-locked Fabry Perot lasers as activation units in photonic neural networks. Let's start with a few words about motivation behind our work. As we are all aware of, the emerging era of big data analytics demands at the same time high speed and energy saving. Faced with the breakdown of Moore's law, traditional von Neumann architectures cannot climb over this digital energy efficiency wall. An alternative computational paradigm is bio-inspired. So-called neuromorphic computing offers computational efficiencies approaching those of a human brain. However, if we want to provide both high computational speed and high efficiency, we need to rely on photonics. The general scheme for artificial neuron is well known. We have linear part, which provides weighted summing of input features, and nonlinear part, or so-called activation function. The interference by itself provides simple and highly efficient realizations of the linear operation in the optical domain, but the nonlinear activation unit most requires for electro-optical conversion. To unleash the full potential of the photonic neural networks, we need an all-optical activation unit typical for deep learning networks, for example, some sigmoid, tangent hyperbolic, or variants of ReLU functions. Design of all-optical activation unit is an exceptionally demanding task, and we want to tackle exactly that challenge. Previous work was related with fundamentals of injection-locked lasers. This technique has been proven to benefit laser dynamics, for example, by increasing side mode suppression ratio and modulation bandwidth. And this is the general scheme. The light from master laser is injected into slave laser, and the slave laser output under injection locking, besides central wavelength in free-running regime, comprises additional emission at the wavelength of the master laser, denoted here by lambda in. In order to describe dynamics of injection-locked Fabry Perot laser, we use standard set of multi-moderate equations for carrier concentration and photon density. And as you can see here, for this simulation, we need gain spectrum with respect to carrier concentration n. Under assumption of a multi-quantum well-active region based on some Q1.55 compound, and relying on model solid theory, we calculate material gain and corresponding spectrum. Here, the spectrum is shown in free-running regime under some small bias current, and you can clearly see a dominant mode and large number of side modes. In this case, when side modes are present, interaction between injection-locked mode and other unlocked modes can lead to a so-called dispersive bistability. For example, with M-3, we can denote side mode, which is third mode on the red side of the spectrum with respect to this dominant or central mode. And since injection is intramodal, the injected signal will impose a frequency shift of the mode under injection by delta omega. This frequency detuning, delta omega, has to be negative or red in order to achieve stable injection locking. And as you can see, for small injection power, like here, we still have a dominant central mode, although we now have larger photon density at the tuned frequency. On the other hand, in case of significantly larger injected power, as here, spectrum is drastically changed. First, the central mode is now suppressed, and then photon density at the tuned frequency is more than 10 dBs larger than in previous case. However, really interesting is the case of moderate injection power, since two different situations can happen, again, changing photon density for more than 10 dBs, but now for same injected power. If we briefly investigate phase plot representing carrier concentration rate with respect to carrier concentration, we can notice that for moderate injection power, the phase plot has 3 stationary points, but only 2 of them, this and this, are stable. In the case of small injection power like this, only one stationary point exists corresponding to this spectrum here. And in the case of large injection power, this curve here, then this stationary point exists, and that corresponds to this spectrum here. However, for input powers related to the phase plot lying in this shaded region, two stable stationary points exist at the same time, and depending on whether the input optical power is increased or decreased, the laser can settle in this stationary state corresponding to this spectrum here with relatively small optical power at the tuned frequency, or in this stationary state here corresponding to this spectrum and large optical power at the tuned frequency. These two stable states lead to optical stability, which is manifested as hysteresis cycle in the slave laser output at the tuned frequency. By increasing injection power, we are moving to the right on the lower hysteresis branch, and if after reaching sufficiently large power we start to decrease it, then we will move to the left, but now on the upper branch of hysteresis. So this upper branch corresponds to this stationary state and this spectrum here, while lower branch corresponds to this stationary state here, also called free running state, and to this spectrum here. This hysteresis shape gives clear indication of the underlying nonlinearity. Moreover, as this picture shows, the loops will differ with respect to the frequency detuning. Additionally, in our previous work, we showed that it will also depend on the bias current. Actually, this will enable adaptivity of our nonlinear function, being one of the crucial advantages of the proposed method for obtaining activation functions. However, an implementation of injection locking in all optical neuron demands that the laser diode nonlinear response on the injected power, or in other words, transfer function, is provided in the dynamic or non-stationary regime of operation. Therefore, we analyze Gaussian optical pulses with fixed full width at half maximum and with different peak powers injected into laser. In dynamic regime, instead of forming hysteresis loop, the peak power transfer function will be a bijective nonlinear function. Nevertheless, the features of the hysteresis, by that I mean boundaries and branches shown on previous slide, will govern the pulse evolution and strongly influence the magnitude of the injection locked side mode pulse response. In order to achieve desired operation, the peak power of the input pulse should be high enough to provide that only one stationary state is available to laser during the transient regime, and that would be this state here. And then dynamic trajectory of the phase plot will essentially try to reach this stationary injection locked state in response of the raising pulse edge, and then it will return toward this free running stationary state following the falling edge of the input pulse. If injected power is low, like this here, the trajectory remains in the vicinity of free running regime, corresponding to low optical power. Although the input pulse peak power in this case corresponds to this stationary state, the trajectory of the phase plot will remain far away from it since it doesn't have sufficient pulse duration. However, for sufficiently high input peak power, like this here, the phase plot trajectory is able to reach a corresponding stationary state and provides high optical power. It is also interesting to note this characteristic spiral trajectory following the falling edge of the input pulse and indicating that relaxation oscillations will be present in the laser output response. Okay, so in the transient regime, injection locking can provide nonlinear response. And as I already said, the bias current and frequency detuning affect on its profile. Thus, they will also have influence on the nonlinear profile. And this feature is really great since it provides a kind of adaptive activation function, further leading to in situ reconfigurability of our activation unit. Let's have a look on transfer function profile transformation in case of bias current change from 1.1 to 6.1 times threshold current. As you can see, obtained activation functions are sigmoid-like with different midpoints, and their thresholds are gradually shifted toward larger input power with increase of bias. And if we show them all together, you can see that threshold points sweep range of approximately 15 milliwatts, which is really great from the adaptivity point of view. Nevertheless, activation function profile can be tuned by variation of the injected signal frequency detuning with respect to the nearest side mode. The increase of the frequency detuning magnitude leads to frequency shift of the injected mode toward left or toward a red side, as shown in this animation. This can be used for in situ reconfigurability in two ways: by using a tunable laser for generation of optical inputs, or by thermal tuning of the injection-locked laser. For example, if we change frequency detuning from 13 omega to 36 omega, where omega represents 10 to the 10th radians per second, we obtain family of activation functions presented on this figure. And if previous result was great, then this result is exceptional. Threshold points sweep through more than 50 milliwatts wide range, and moreover, the change in activation function profile is much more pronounced. You can see that for smaller magnitude of detuning, the profile is still sigmoid-like, but with detuning increase, it transforms to prelude-like profiles. Okay, we can definitely provide nonlinear transfer function with suitable profile, and we can alter it by variation of operational parameters. But to prove that this feature is useful, we need to implement the proposed nonlinearity in the activation unit of some neural network. In order to prove the concept, we opt for a simple example of binary classification that requires only one neuron to separate the inputs into two classes. We choose standard NIST dataset consisting of handwritten digits, and every digit is represented by 28 by 28 image with pixel intensity in range from 0 to 255. The neurons were trained and evaluated separately on each digit pair from 0, 1 to 8, 9. And every neuron corresponds to a single digit pair. After the pixel intensity is normalized and images are reshaped to 1D arrays, dimensionality of data set is reduced to 8 features. This dimensionality reduction is employed by autoencoder shown here, and since the activation function is optical power transfer function, weights and features are set to be non-negative values. Utilized loss function between original and decoded pixel array is binary cross entropy, and the optimizer is the variant of stochastic gradient descent with momentum called Adam. The predicted values of encoder here represent digit features, and after coded, these normalized samples are fed to the neuron. Neurons are trained in Keras API running on the top of the state-of-the-art machine learning framework TensorFlow, and they are trained within 10 epochs in batches of 128 samples with non-negative constraint applied to their weights and bias. Since the neurons are trained to inference if the digit belongs to one out of the two possible classes, the classes are labeled as 0 and 1, where class 1 corresponds to the lower digit in pair. And input values are normalized features obtained from the autoencoder, and the weights of the neurons initially set to 0 are optimized again using Adam with learning rate 10 to the minus 3 to minimize the mean squared error cost function. As activation function, we use normalized transfer function obtained from physical model simulation. And these are data points obtained for different tunings. Here we show some set of values for which we have characteristic activation profiles. However, symbolic training and testing requires analytical form of activation function, so we use a custom function similar to Boltzmann sigmoid equation, which we propose in our previous paper. As you can see, it provides excellent fit to simulated data points. And here are the first results. This graph shows testing accuracy for nonlinear functions comprised within family of functions obtained by variation of the tuning, some of which are presented on this figure here. And as you can see, for the tuning parameters with larger magnitude corresponding to PRELU-like profiles, for classification of each digit pair, we can achieve accuracies above 95%. However, the best accuracy values for each digit pair do not correspond to the same detuning parameter. This is especially pronounced for digit pair 6-7, for which optimal detuning is around 25 omega, corresponding to activation function with lower threshold and stronger saturation. As we already said, the presented results were obtained by training and testing each pair of digits separately for each of the activation functions from the family of curves provided by variation of the tuning. And now the logical question is, if we already have an analytical function that can perfectly fit the entire family of curves, can the process of choosing the optimal activation function be more efficient? Can we also train frequency detuning and therefore the activation function profile for each pair of digits? And the answer is yes. These pictures present values of coefficients b from a function used to fit the complete family of curves versus actual detuning value. These are blue points on these graphs. And now we can use higher order polynomial function to provide analytical dependence of coefficient b, each of these 6 coefficients, with respect to detuning value. And these fitting functions are given in red. Now, along with weights, we can train frequency detuning to provide maximum classification accuracy. Thus, in addition to adaptive or reconfigurable, we can refer to our activation function also as to a learnable activation function. This procedure results in the same optimal values of the tuning as in previous case. Finally, it is left to confirm results obtained via symbolic testing with actual signals propagating at physical layer. We use the same feature elements as in previous analysis and generate Gaussian pulses with peak power corresponding to elements of the feature vectors. And after weighting, again with the same weights and finally summation, signals enter to injection-locked laser used as activation unit. Classification is done according to the value of the output signal peak power at detuned frequency with threshold for classification set to 0.5. In this procedure, we repeat for every digit pair at exactly optimal activation function determined from previous analysis. And here you can see activation functions, actual detuning values, and testing accuracies for each digit pair used in this simulation. For each digit, we randomly pick one image which is correctly classified, and these examples are denoted with circled numbers on this graph here. And we pick one image which is wrongly classified, and these are denoted with square markers. For example, this image here definitely looks like 0, and it is correctly classified as 0 since peak output power is around 0.7. On the contrary, this image here corresponds to 0 digit, but it is classified as 1 with output peak power around 0.3. And similarly, we can connect all other images with values shown on the figure at left. Finally, We show signal forms centering in activation unit with these dashed lines and final output signals with solid lines. Again, these waveforms correspond to the examples shown on the left figure for classification of the 0-1 digit pair. Comparison with symbolically determined values show excellent agreements, as you can see from these numbers representing output values generated by both approaches. However, output signal profile significantly deviates from input Gaussian, dominantly due to relaxation process to which we have pointed during transient analysis of dispersive stability. Finally, to conclude, we have theoretically shown that the control of the activation functions profile and its slope can be achieved by tuning of injection-locked lasers bias current or frequency detuning. The proposed method offers the benefit of selecting not only one, but rather a family of activation functions during design stage. By training the activation functions parameter, we can have deeper exploitation of achieved all optical nonlinear profiles. So we can have more efficient and less time consuming training process, which is especially significant in case of more complex neural networks. And finally, the in situ activation adaptivity promotes smooth neuron transformation depending on the task at hand, even during its operation, making this an ideal candidate for the reconfigurable neuromorphic networks.
Thank you very much. I would like to thank the organizers for the opportunity to present this talk, and also to my co-workers on the work we already done.
Okay. Thank you for that insightful talk, Dr. Jasna Krasinski. Now the stage is open for questions. Okay, Doctor. I assume that you have no questions from speakers. Once again, I thank you for being a part of this webinar and hope to associate with you in our future events as well. Thank you so much, Doctor.
Thank you. Bye.
Thank you, Doctor. Bye. Now we're moving on to our next presentation by Dr. Rekha Gautam, Tyndale National University, Ireland, and presenting on the title of talk by Spectroscopic Assessment of Red Blood Cells Quality. Hi, Dr. Rekha Gautam, please share your screen.
Could you please allow me to share?
Okay, Doctor. Okay, Doctor, now you can share your screen.
Yeah, thank you.
Thank you, Doctor.
I hope my screen is visible now.
Hello,
Good morning,
Doctor.
everyone. Is it visible, my screen?
Okay, Doctor. Now you can start your presentation.
Thank you. Yeah. Thank you for the opportunity. Today I'm going to talk about how laser light can be used to assess the quality of red blood cells. This presentation may be very different with the other presentation when I saw the program. It's more by photonics oriented. So the motivation behind assessing the red blood cells quality comes from why blood is really life-saving therapy. It is used to treat different conditions like cancer, hemoglobinopathy, and it is used during surgeries and childbirth. But blood is allowed to store only for 35 days in Ireland and 42 days in Europe. WHO says that even though there are 120 million donations annually, many people do not have timely access to the safe blood. COVID made this situation worse because people were scared of visiting the donation center due to infection. Storage is, now question is, storage is the right criteria to discard the life-saving blood after 35 or 42 days. because this blood is not only life-saving, but it is also associated with a cost. It is expensive therapy also. So, sorry, why there is a strict guideline of the storage age? Because red blood cells are alive, they metabolize during storage, and they create lots of byproducts. These byproducts are created by cell burst, which could be like cell-free hemoglobin or iron or lipid fragments or methemoglobin over time. Transfusion with these byproducts may create some acute lung injury or maybe septic shock in specifically critically ill patients or infants. So we need a way to quantify these byproducts. Right now, it is done only by saying that the aged blood has more byproducts compared to the young blood. So currently, to quantify these byproducts, they open the blood bag, take blood out, centrifuge it, and then quantify the byproduct like cell-free hemoglobin or total heme in this supernatant. For this, they need to open the blood bag, and once blood bag is opened, its sterility condition is gone. So that blood bag won't be able to use for transfusion. And therefore, only 5 out of 100 bags are tested using this method. So we need a method which can probe these biomolecular changes non-invasively without opening the blood bag. And for that, optical methods could be helpful. And here in this study, we used Raman spectroscopy, which is an inelastically scattering process, where we see the difference between the incident light and the scattered light to probe the molecular vibrations. And once the incident light or the excitation laser matches with the absorption spectrum of the molecule, we get resonance enhanced Raman spectrum. So you can see that this resonance enhanced Raman spectrum can clearly differentiate between the bad hemoglobin, methemoglobin, and the oxyhemoglobin, which is a good hemoglobin. So now the question was, can we identify these spectral markers inside the blood bag? For that, first we tested the blood bag outside using a drop of the blood bag and also by washing the cells, just separating cells out from the solution. And this is a representative spectra from a donor. You can see it is hard to appreciate the changes with respect to age, where day 7, day 21, and day 35 are compared together. But when we zoom into different sections, you can see that these spectra are different from each other at different spectral locations. So then we decided to do some statistical analysis. Are these changes are really significant? And then we took the ratios which were related to the oxyhemoglobin, and you can see increase in oxygen saturation over time, which can be detected by Raman, and also increase in the methemoglobin, which is a bad hemoglobin, over time with the age of the blood bag. So now it was the question like, are these changes coming from the blood supernatant or from the cell part of this tube? You can see the supernatant has red color and the bottom are the cell precipitates. So question is, these changes are coming from these cells or the supernatant. When we did comparative analysis on this, we found that the changes were much stronger in the blood drop, but these changes were less significant in the washed cells, which doesn't have this supernatant. So most of these changes were coming from the supernatant, which is present in this blood drops. And which is good because gold standard method is also using this supernatant to identify these byproducts in the blood bag. So to correlate, to find out like the gold standard method is matching with the Raman spectral markers, we did a correlation analysis. This is done with respect to oxyhemoglobin bands. You can see that the total heme, which is calculated by gold standard method, is correlated, at least significantly correlated with one of the oxy bands. So that could be the spectral marker for the oxygen saturation in the blood bag. However, for the MAT hemoglobin, the correlation was found to be much more significant, and two different spectral regions of the MAT hemoglobin were correlated with the gold standard techniques. So we know that Raman spectroscopy is able to identify these changes in the blood over time. So, but the idea is finally to probe the blood inside the bag. So we have to probe the blood like through a polymer layer, because blood has a polymer and Raman also has signal for polymer. For this, we used a diffused beam to create a diffused beam in our system. We changed the location of the beam expander and underfilled the back aperture of the objective to get this diffused beam, and it helped us in reducing the fluorescence background and also the photon density on the sample. So with this, you can see that when we were using a focused beam, we can see this beam on the CCD, which requires only 7 pixels. But when we move to a diffused beam, it acquires, like, illuminates much larger region of the detector. So it was important to identify how many pixels are really illuminated by the diffused beam we were using. So we did a series of analysis for that, like we changed the number of the pixels, and then compared the signal to noise ratio, and we found that 37 pixels were sufficient to capture the diffused beam. After that, the signal to noise ratio was decreasing due to increase in readout noise. So the next thing was, as we are using a diffused beam, which is bigger beam, do we need to change the slit width of the spectrometer, the entrance slit width of the spectrometer? So we did a series of analysis on that. And we saw that with increase in the slit width, as you can see x-axis of this graph, the amount of the signals were not improving in the red and the black curve. However, the full width half maxima, like the bandwidth of the peak, increased with increase in the slit width. Means we were losing the spectral resolution by increasing the slit width, which was not good for us because we wanted to conserve the spectral resolution. It was important to differentiate different byproducts. So we decided to keep the slit width same, as it is not helping in improving the SNR. We use 50 micron slit width. So diffuse resonance Raman spectroscopy in this way is able to see through the blood bag, through the polymer, and we could see the signals from the blood. And this is from results from 6 donors. We tried to differentiate this day 7 and day 35. Black one is the pure polymer spectra. Raman has spectrum for the polymer also, but there are some free regions where we could see only the blood signals, and using those bands, we could differentiate between the green, which is like the day 7 young blood, versus the old blood, which is day 35 here. So this proves that Raman spectroscopy is good enough to probe these biomolecular changes. However, there are some structural changes in the cell shapes, which were not we were not able to target using Raman. So for that, we collaborated. This work was done in the collaboration with SFSU with Dr. Chen. He already gave a very nice background of nonlinear optics in the starting of this session. So here, idea was, because light implement some forces on the particles, and red blood cells can act as a particles. So can we differentiate that using light? So we know that light, when refractive index of the particle is greater than the background media, then particles are attracted towards the center of the beam. And when refractive index of the particle is lower than the media, then particles are repelled out of the beam. So means light is able to differentiate between the particles with respect to refractive index. But what we wanted, light to be differentiate the particles with respect to the size also. And shape, size and shape. This size and shape, which was important to see the changes in the blood bag. So for that, we used a very simple system as shown in this diagram. And we used a cell suspension in a 3 centimeter cuvette. We just used an input beam and then imaged the output beam. We know that when gradient forces are more, like when particle has higher refractive index and gradient forces are more than scattering forces, then particles are attracted towards the center of the beam, and after a point there is a collapse of the beam. But however, when scattering forces, which are important to push the particle along the beam, when scattering forces are higher or equal to the gradient force, then we get a like a beam of the particles attracted towards the beam, and we can see that helps in higher transmission, like attraction of the particle towards beam, which helps in the higher transmission. Means it is creating like a waveguide along the channel. So for that, the idea was for us was to see if these forces are different with respect to different shape of the cells. So here we used a isotonic. Isotonic is the normal condition, physiological condition. Hypotonic solution also, where like due to osmotic pressure change, the water is going inside the cells and it makes it like a ball shape. And the this hypertonic solution, where water is coming out of the cells. By changing just salt concentration, we could change these 3 conditions, and that helped us changing the shape of the blood cells. So here you can see that with hypertonic solution has quite dense blood cell and spiky shape, which is like helped in creating the scattering forces, and thus very relatively small power was required to create the channel in the blood cell suspension. So hypertonic solution required the least power. This can also be appreciated by quantifying the transmission after the cuvette. You can see that hypertonic solution has higher transmission compared to the other 2, which red one is here isotonic, which is the normal condition. And then the green one is hypotonic, which is the ball shape. So when the ball shape means it has more water, so refractive index was smaller and the shape was much more uniform. So that required more power to create the waveguide into the channel. And this sign color line is just to show that for PBS, the normal PBS, the transmission was not changing with increasing the power, it was same. And then to see the output beam diameter, we measured the output beam using beam program, and you can see that the beam was also smaller, transmission was higher for hypertonic. At the same time, beam was also smaller for the hypertonic solution, as expected in this scenario. So then because the finally idea was to differentiate between the young versus the old blood. And we know that how old blood is different from the young blood, that old blood has that cell-free hemoglobin, like the supernatant is not clean. it has red color, means it has cell-free hemoglobin. So when we did the cell suspension with the old blood, then we saw that the hypertonic solution, even though it requires the least amount of power, the power requirement was much less than the young blood. So means this could be one of the criteria differentiating between the young versus the old blood. To further analyze this, like what's happening in the old blood, we increased the amount of the cell-free hemoglobin in the cell suspension. And this is like from HB1 to HB4 is the increase in the concentration of the hemoglobin in the solution. And with increasing the concentration, we were able to get the minimum spot site, like higher transmission, formation of the waveguide much easier with the higher cell-free hemoglobin. So this technique can detect the changes in the shape and also the cell-free hemoglobin. So which is really good. It can target both together. However, the limitation of the study is this requires slightly higher power. This power is higher than the maximum permissible power for biological solutions. And secondly, it requires a dilute suspension, the free movement of the particle in the solution. In the back, if you can see that these are tightly packed red blood cells separated from the plasma. So there won't be enough scope to use this directly in the transmission mode. So for that, here at Tyndall, now what we are trying to use diffuse reflectance spectroscopy is similar to the optical forces. Diffuse reflectance spectroscopy can also target the scattering, which is coming from the change in the shape of the red blood cells. You can see here the scattering background is changing from going hypotonic, which is the ball shape, more watery red blood cells, to the hypertonic, which is the dense and very spiky. And also absorption will change because the concentration of hemoglobin is higher. So DRS can target both the scattering property and the molecular absorption property of the cell suspension. So here plan is to combine the DRS in the Raman spectroscopy together to increase the accuracy. And we are just working on a hand-handled probe. We are trying to design a Raman and DRS together. DRS with two different spatial offsets so that we can see deeper through the polymer. And Raman to target other biochemical changes. By combining those two, we will get a bimodal optical probe, which probably will help us increasing the accuracy of differentiating between the red blood cells quality over the age. So with this, I will conclude my talk. So we know that Raman spectroscopy at 633 nanometer, which gives resonance enhancement, is capable of characterizing blood quality objectively. Big data set will be helpful in creating the models for real-time output, which may help the staff at the blood bank. Integration of diffuse reflectance spectroscopy can give some extra parameters. As you, in the slide I showed that only few spectral band of Raman were highly correlating with the gold standard heme. So it will be good to have some another parameter and then fuse them together to improve the efficacy of the model. And in future, I think the self-trapping, because it is important after transfusion, it is also important to see how blood is reacting inside, because sometimes blood reacts inside. So I think for that, the waveguide formation may help directly in probing the blood inside the human body through the skin. So thank you so much. I would like to thank all the collaborators in this from SFSU, Dr. Chen and the other team members, and the at UAB, Dr. Louis, Dr. Patel, and the other team members and the funding agency. And for now, we are working with the Irish Blood Transfusion Service to make a new bimodal prop for this. Thank you.
Okay, thank you for that insightful talk, Dr. Rekha Gautam. Now the stage is open for questions. Okay, doctor, I assume that you have no questions from the speakers. Once again, I thank you so much for being a part of this webinar and hope to associate with you in our future events as well. Thank you, doctor.
Thank you. Bye.
Thank you so much. Now, moving on to our next presentation by Dr. Mohsin Rahmani, Nottingham-Trent University, UK, presenting on the title by Light Matter Interaction with Engineered Metasurfaces for Applications Ranging from Night Vision to Ultra-Sensitive Detection. Hello, doctor. Now you can start your presentation.
Hello, thank you so much. Can you hear me? Can you see me? Everything is fine?
Yes, doctor, I can hear you.
You see my screen, yes?
Yes, doctor. Yes.
Yes, okay. Thank you so much for having me here, and thank you for the invitation. So yes, my talk is about light matter interaction with engineered metasurfaces for application ranging from night vision to ultra-sensitive detection. And I am from Nottingham-Trent University, and obviously Nottingham-Trent University is in Nottingham. If you don't have a clue where Nottingham is exactly in the UK and in the territory of England, Nottingham is right in the center of the England. And we have this luxury that with less than 1.5 hour driving, we can get 85% of the cities of the England, which is a very good point for us. It's really ease up the traveling and communications for us. And if still it doesn't ring any bell for you, Nottingham is the city of Robin Hood. So I hope that it's already make some connection to you that where we are. So today I'm going to speak about light matter interaction with metasurfaces. But before that, I want to provide some background that what other kind of light matter interaction we have. We can have light matter interaction with homogeneous surfaces like mirrors and normal, I don't know, windows, which is something that's happening around us every day. But if the surface are structures, we still have 3 different kind of light matter interaction. If the dimension of the nanostructures or the components are much larger than the wavelengths of the light, so we are speaking about the geometrical optics like prisms, lenses, and so on. But if the dimension of the nanostructures are on the order of the light, so we are speaking about the diffraction grating. But when the dimension of the nanostructures and the separations are less and smaller than the wavelengths of the light, then we are speaking about the metasurfaces, where we can change the behavior of the light and use them for so many exciting applications. So my talk is about the metasurfaces, and today I'm mostly speaking about 2 different regimes of light matter interaction with metasurfaces: linear regime and non-linear regime. When we are speaking about linear regime, we are speaking about this area where the response of the light, the intensity of the response of the light, depends linearly upon the intensity of the incoming light. And so it's already very well studied, and it's maybe just last 20-30 years there have been so many different papers and studies about it with light matter interaction with dielectrics, where we are taking advantage of the high refractive index of the electrics, and we have the accumulated field inside the nanoparticles, or where we use the metallic nanoparticles or plasmonics, where we are exciting the free electrons on the surface of the nanostructures, and we can generate surface plasmon resonances. And particularly in the metals, because of these fields which are on the surface of the metals, when we have 2 or more nanoparticles close to each other, so we are able to generate near field accumulation, so-called hot spots or near fields, which you can see here in this very nice illustration in this figure. And as you see that we have very strong near field enhancement where the 2 nanostructures are very close to each other, but when we move away, exponentially we lose the intensity of this hotspot. As you see here, 1 order of magnitude reduces when you go only a few nanometer further from the center. But the good news is that these hotspots and near field enhancement are very sensitive to the change of the environment. That's why they really can be used for sensing applications. Here I am providing one of our old papers as an example to show that how sensitive these near fields are. And as you see here in these nanostructures, we have alkyl styles molecules attached to them. They are really small, maybe they are on the order of 2, 3 to 7, 8 nanometers. But as you can see, even such a small molecules can still change the optical properties of these plasmonic nanostructures, and they induce these shifts as you see here. And of course, by detecting and translating those shifts, we can determine presence or absence of some nanostructures which are around our nanoparticles, some molecules or cells which are around our nanoparticles. In order to give you some more insight into that, so I am sharing this one again, which is another old paper, but it is very good paper to show that how sensitive these near infrared are, because the previous example were around a few nanometer, but this example is about 1 layer of graphene, which is sub nanometer, which is 1 atomic layer, which is around 3-4 nanometer thick. But even such a 3.34 angstrom thick, sorry. Even such a thin material can induce the change in the optical properties as you see over here, and therefore the plasmonics nanostructures can be used for sensing and detecting such nanostructures. But so far we have been speaking about the materials like solid materials or liquid materials which make significant change in the refractive index of the surrounding environment of nanostructures. So therefore we can detect the changes, those refractive index. But what about the gases? When we are speaking about the gases, the concentration of the gases and the changes they make to the refractive index of the environment are really, really little. For example, you see here the difference between refractive index of gas, of air and ethanol is 10⁻⁴. So it's much harder and much more difficult to detect such a small refractive index difference. Here there was some paper more than 10 years ago suggested by the group of Harald Giesen to use some bilayer material and using some material that are sensitive to near field enhancement so that they can absorb the light. They use this hybrid nano antennas for detecting hydrogen, but because of a lot of difficulties in fabrication and the fact that this one is for single nanoparticles, so it stayed in the laboratories and it didn't come to the production lines. So what we have done recently, we have from a few years ago, we have started to combine this concept, plasmonics and plasmonic sensing, with a porous film concepts, where you can have your plasmonic nanostructures and you can make your porous film around it, so that in this case you can significantly enhance the sensing volume, and it really help you to detect a lot of different gases, which is very interesting and very exciting. So I show you some of our results in this direction. So first, before that, I want to show you that these porous films, they are really ultra porous. 96% still is air, and interestingly, they don't themselves to make any change on the optical properties of plasmonic nanostructures. Here in this graph, you see that even by having 2.9 micrometer of these porous films and our plasmonic nanostructures, still we don't see a much difference in the optical properties of the metallic nanostructures underneath. So I encourage you to compare it with that one single layer of graphene, which made some changes in the optical properties. But here, 3 micrometer of these porous films, they do not make significant change in the optical properties of the graphene. So here they are our experiments and our results. And as you see here, when we have just bare gold plasmonic nanostructures, we don't see much change in the localized surface plasmon resonances, even when we purge 4% ethanol. But when we use 1.8 micron, which is actually the optimum one, I'm not going to go to the details. If you are interested, you can go and read this paper. But this thickness is the optimum thickness. So for it can show you can see that there is a good changes in the optical properties of the plasmonic nanostructures in this case. And here it shows that it is very repeatable. You know, when we purge the 4% ethanol and then we turn it off, so it goes up and down. We can show that it's very repeatable, and it's very reliable to detect this purged gases to the sensor. So not only for ethanol, we also managed to measure the acetone and toluene, and we also took into account the different condensation at different temperature. And as you see here, by having this library at different temperature and different concentration of the gases, and the shift they induced in the localized surface plasmon resonances, you can see very different behavior of different gases. Therefore, if you have this library in advance, and then you make the model of this different sensing, so you can detect the different gases, and at the same time you can detect the concentration of those gases with this technique. So we didn't stop, we went further, and in a newer paper, we went for the 3D structures, where, as you see over here, we have the nanostructures, plasmonic nanostructures only underneath, but they have within this porous film everywhere, as you see here. And by this strategy, we managed to measure the refractive index change as low as 10⁻⁸ at room temperature, which is really, really high. And in this graph, you can see the differences when we have the plasmonic nanostructure at the bottom, or the plasmonic nanostructures are embedded in a 3D fashion over here. And we also use this sensor for detecting different gases. And as you see, you can see different signatures, which is demonstrating that we can use this sensor not only for certain gas, one gas, we can use it for very different gases as a sensor. So now I go to the second part of my speak and my talk, which is about nonlinear regime. When we are speaking about the nonlinear regime, we are speaking about these areas which are beyond the linear one. And for that, we need much higher intensity of the input light. In this case, the response of the light doesn't depend linearly anymore. on the intensity of the input light, and based on the number of input and output, I mean incident light and reflected or transmitted or emitted light. Here we have so many different nonlinear interactions based off their energy, the number of photons. We have so many interactions, but all of them, they need very high intensity of the input light. So in order to give you some idea that how high I mean, so the intensity of sun on Earth is 10 to the power of 3 volt per meter, which is actually inducing normal and linear light matter interaction. In order to go to the nonlinear light matter interaction, we need a 10 to the power of 8 volt per meter, which is much higher. And these days, in order to reach that intensity, we only need very intense lasers to go there. So nonlinear optics, it's something that's around us every day, and we are using it in our daily life. As you see, a few examples are like the laser pointers and nonlinear microscopes, or even something that we are using every second is optical fibers, and where this nonlinear interaction are heavily involved, and we are using them in our daily life, but at macro scale, at larger scale. Nonlinear interaction at nanoscale, they are not mature yet because of several issues. The main issues are low conversion efficiency at nanoscale, because at larger scale, we can have larger crystals, then we can accumulate the very weak signal and generate just decent signals. But at nanoscale, we don't have that luxury, and we should have some nanostructures that they alone, or maybe some metasurfaces that they can generate high intensity, and we cannot use phase matching at nanoscale. So it makes our life very hard to generate decent efficiency for actual applications. And the other issue is that fabrication challenges at nanoscale. It's something that it makes very hard to fabricate these kind of structures. So let me. That's why there have been a lot of efforts recently, and not recently, maybe last decade, to find some strategies to generate high efficiency nonlinear signal at nanoscale. Of course, plasmonics nanostructures were the first alternatives, because already they were very well studied in the linear regime. So in the nonlinear regime, people try to see that whether they can be used for second harmonic generation, where, for example, you have 2 photons with the frequency of omega as input, and 1 frequency of 2 omega, and 1 photon with the frequency of 2 omega as output. So they use different kind of resonances, magnetic metamaterials, or even electric resonances in the plasmonics to generate second harmonic generation. And we also did some research some years ago to study the effect of symmetry of nanostructures on the second harmonic generation, and so on. And also there are some studies and research on the third harmonic generation by plasmonic nanostructures. But the issue of the plasmonic nanostructures that they suffer from loss issue. They absorb light a lot. They have very low resistance against heat, and they can offer very low directionality, and the efficiencies subsequently are low. That's why in the last maybe 5-6 years, there have been a race among the people in this field to find a better material for generating nonlinear signals. So lab materials like 3-5 semiconductors, nitride oxides, different semiconductors, phosphides, and so on. And mostly for the second harmonic generation, people, they come to the conclusion that the 3-5 semiconductors and gallium arsenide families are the best because they have very high susceptibility, and there is a lack of central symmetry, which is essential for generating second harmonic generation. So that's why several groups in the world, they try to make these 3-5 semiconductors, but because of the fabrication issues. This 3-5 semiconductor can be only grown epitaxially, which is much more difficult than normal fabrication with electromagnetography. So people have tried to just propose different techniques. First, it was with the group of Giuseppe Leo using some aluminum arsenide layers and then have aluminum gallium arsenide on the top and then oxidize this aluminum arsenide to make aluminum oxide. The group of Eagle Brenner and the Sandia lab, what they did, the very similar approach, but they used the aluminum gallium arsenide as a buffer layer and then they oxidize it to aluminum gallium oxide, or the group of Stefan Meyer. So they just etch down gallium phosphate wafers and make gallium phosphate nanostructures directly on the gallium phosphate wafer. But the issue in all of these techniques and all of these ways is that they use the wafer, handle wafer, as the substrate, which is not transparent in the visible light or visible range. That's why they are very limited to reflection only, which is a disadvantage for this nanoparticles and nonlinear generation by these nanoparticles. So the issue is that you cannot really grow these nanoparticles on glass or transparent substrates because of the lattice mismatch. It is a big issue which has avoided many researchers to have nice 3-5 semiconductors on transparent substrate and have high efficiencies subsequently on transparent substrate. So it is where we stepped into this field a few years ago by this technique, which we proposed to first fabricate these 3-5 semiconductors on a gallium arsenide substrates. As you see here, different steps. I'm not going to go to the details. If you are interested, you can see it in this patent or in the following papers, which I show you. Then what we did with some techniques, we embed these nanoparticles within some BCB, which is the transparent polymer, and then we transfer it to very thin glass substrate, 170 micron thickness. It's very, very challenging because it easily gets broken and it's very fragile. But we managed to have this nice 35 semiconductor nanostructures, on glass substrates. It was our first paper published in 2016. We managed in that time for the first time to have this 35 semiconductor on glass. Therefore, we could measure both reflection and transmission in nonlinear regime. It means that we will have the input frequency of omega, but output of 2 omega. It goes both backward and forward. And as you see here, we managed to get the efficiency of 10⁻⁴, which is very high efficiency. In order to give you that, so how good it is. So I want to tell you that the efficiency that can be seen by eye is around 10⁻⁴ to 2, 10⁻². So we are not really off. We are still very close as compared to the, for example, plasmonics efficiency, which are on the order of 10⁻⁶ or 10⁻⁷. And also they have been in the following years, there have been some other techniques to fabricate them and to measure both reflection and transmission, nonlinear signals. But the main issue, regardless of these fabrications, is the crystalline orientation of these nanoparticles, which generates zero emission in the normal direction. If you see here in the 3D, in this 3D emission radiation pattern of this nanoparticle, here is the nanoparticle. You see that when the light is coming here, the reflection goes the way to not to the normal direction, to the side direction. And if you see this front view in the normal direction, we have technically nothing, zero. And if you see here in this top view simulation in the middle, we have no nonlinear signal. It is because of the crystalline orientation of this aluminum gallium arsenide and 3-5 semiconductors. Here, 2 circles. The outer circle is the entire emission, and the inner circle is what we actually detect by the microscope and by our characterization tools, and you see still we see nothing in the center. So there have been several efforts in different strategies to solve this issue. One of them was to using some gratings around the nanostructures, so that you see here by this grating you can change the direction of the emission here, and here you see with the right grating you get the normal normal emission, and also here by oblique incidence, not normal incidence, you can get the normal emission. Sorry, but you can get the normal emission around 0 degree. It's also another nice technique, but the strategy we incorporated is to use the crystalline orientation of the nanoparticles to control the emission. So as you see here in the linear regime, you don't see any difference in the linear scattering and the optical properties when you are speaking about the different crystalline orientation, because in the linear regime, you are mostly relying on the refractive indices, not the crystalline orientation. But when you go to the nonlinear regime, you see the crystalline orientation has a lot to say. And for example, for some of the orientation like 110, 100, and 111, you have very different nonlinear second harmonic generations when you just rotate just the polarization, not even the angle of incidence, only the polarization of the input light. And for example, for 111, you can see that interestingly why this while the nonlinear signals, they do not change with the changing the polarization of the light, and all these different modes are the same, but the emissions and the radiations are very different. As you see, at different degrees, we have very different emissions and radiations, which is really interesting, because linear properties are the same. Nonlinear properties also, I mean that in terms of the intensity are the same, but the radiation patterns are different, which was very nice discovery in that in 2019, I believe we did it. But we didn't stop. A year after that, we studied a 110 orientation, and that one not only we solved the issue by having to have the signal in the right in the middle, as you see in this radiation pattern, we have right in the normal direction these signals, but also this orientation has this luxury that by changing the polarization, you can have the nonlinear signal to forward or backward on demand. So you can just, without changing, without any contacts, you can have forward second harmonic generation or backward second harmonic generation. And as you see over here, you can control the proportion of the forward and backward second harmonic generation by this orientation. So it is not stopped. We are still doing a lot of other researches which are not published, unfortunately, yet, but hopefully in less than a month, I expect 2 papers will be published. Unfortunately, I was not able to put those results there because not published yet, but we are very heavily and actively working in this research field, and hopefully you will hear more in this research direction. In conclusion, I spoke a little bit about what are the metasurfaces and what are the different kind of light matter interactions, and then I shared some of our results on the sensing metasurfaces, and then I spoke about nonlinear metasurfaces a little bit, but I emphasize again that that's not all, and metasurfaces are building block of the many other high-tech for tomorrow's technologies, and I believe that we hear much more about the metasurfaces in the following years. So I would like to acknowledge all my colleagues who were contributing to these papers in different universities in Australia, in the UK, in Switzerland, and so on. And I would like to sincerely thank them. Funders and my current funders, which are Royal Society and UK Research and Innovation in the UK. Thank you so much, and I am very happy to answer your questions if you have any.
Okay, thank you for that insightful talk, Dr. Mohsin Rahmani. Now the stage is open for questions. Okay, I assume that you have no questions from the speakers, Doctor. Once again, I thank you for being a part of this webinar and hope to associate with you in future events as well. Thank you, Doctor.
Thank you so much.
Thank you, Doctor. Now, moving on to our next presentation by Dr. Bettina Hesse, Johannes Kepler University, Linz, Austria, and presenting on the title, Current Developments in Low Coherent Imaging. Hello, Dr. Bettina, can you hear me? Okay, on behalf of Dr. Bettina, I'm going to play her PPT presentation now.
Good morning. In the range of low coherent imaging, if we speak about low coherent imaging or about low coherent imaging or about coherence in general, we know that electromagnetic wave can be coherent, partly coherent, or incoherent. So coherent has some degree, and if we say long or short coherence, that is often a question of scale and of resulting application. If we consider, for instance, coherence lengths of highly stabilized lasers, and they have a coherence length of hundreds of meters. And if we speak about short coherence, then we regard the coherence of few micrometers or meanwhile down to submicron range. And that is also expressed by the coherence length, which scales with the square of the probing wavelength and the spectral bandwidth. So coherence length and also coherence time is inversely proportional to the spectral bandwidth, as broader the bandwidth, as shorter coherence time or coherence length. And furthermore, we have also to consider temporal, longitudinal, or spatial transversal coherence. In the range of low coherent imaging, we have white light profilometry, white light holography, and here I will focus on optical coherence tomography. That is a technique with resolution in the mesoscopic size range, for instance, larger resolution than visual optical inspection, but on the other hand, more coarser resolution than, for instance, an electron microscope. And technique, this low coherent technique based on interferometry, is maybe more well known in medical applications. So in the 1990s, it was developed in the group of Wang and Fersche for ophthalmology. Meanwhile, over the years, it has also been transferred to other medical disciplines. Dermatology to analyze, to visualize skin pathologies, urology, and also cardiology to be realized in endoscopic version, and also in dentistry can be found to visualize implants or different dental layers and cracks, for instance. So in such a way, it can be seen as a non-invasive biopsy tool with microscopic resolution and a penetration depth of few millimeters. And after this short introduction, I briefly show some configurations, and then I come to applications with focus in non-destructive testing and extension of OCT towards functional imaging, and finally trends and some outlook. To the configurations, it is an interferometric technique, so it can be in principle realized in a Michelson configuration or also in Mach-Center configuration. And in history, first was established as in so-called time domain OCT, measuring the time-resolved interference signal, and movable mirror performs the scanning over the depth, and at each interface, at each internal structure, a signal is back reflected, and the back reflected light is measured in its strength and runtime by raster scanning approach. Later has been developed the so-called Fourier domain OCT, which can be realized in car space by measuring the spectrally resolved interference signal with a line detector and a spectroscopic version, and applying a grating. And still in further development is to use swept source, laser sources and tunable laser sources, and to register the spectral resolution and interference signal by a point detector. Here we have applied first a Fourier transform back to the spatial domain to get the information about the structure and about the depth distribution. This raster scanning approach can also be extended towards full fit illumination schemes, also be applicable in time domain or frequency domain. The samples which are investigated in our cases are, for instance, fiber reinforced polymers, coatings, also in metals, plastic multilayer foils, in general semi-transparent turbid materials, to get information about layered specimen, about their structural features, about artifacts or inclusion, but also biomaterials, biofilms, biochips has to be investigated. OCT as an inspection tool at a micron size scale for monitoring and validating coating polymers, ceramic 3D printed materials, for instance. And it has the advantage that it's a non-destructive and non-hazardous technique. So, for instance, it has been applicable for inspection of polymer welding seams, pharmaceutical application, or later I also report on ceramics inspection. Here a bit more in detail, here you can see such a multi-layer foil, and with OCT, you get the cross-sectional image to see the welding seam, the welding point, for instance, here, and you see also the different layers as barrier coatings within this foil for packaging industry used. Other example also from polymer packaging industry to monitor the laser bonding. Here it is a correct bonding visible, so more or less there is no structure visible. And here we have a bonding defect, we get some back reflected light, and so we get here some contrast, that structure hinting now that we have here a region of defect. Also flow pattern can be visualized and application for injecting molding. Essential for the quality of OCT is always the light source, spectral features of the light source, and in such a way resulting in axial resolution. So here with Informer SLD application and within low contrast, and here you see the higher contrast. And additionally, we have also the central wavelength, which more or less determines the penetration depth, and that is in particular important, for instance, also for different types of polymers, where those biological samples or where those organic coatings, there is important which central wavelength has been selected. This is an example for quality inspection in pharmaceutical engineering, and for instance the monitoring of the coating layer, of the thickness of the coating layers over time, and that is visualized within the production process. That is more or less a trommel coater, where you have here the spraying device, and these pills and tablets are randomly coated, and through a window, an optical window, so OCT sensor is included and can monitor instantaneously this coating process. As application is OCT for food inspection, for instance, for testing some fruits, storage condition of fruits and their influence, and to see some defects earlier than to be outside visible in the shop, or to see, for instance, the cereals shaping or deforming due to hydration. You can see it also here, maybe in the movie. That is bread with some water droplet, and you see here now the growing and the deformation due to the wetness. And these all have been examples for getting structural information. We can also use the statistical information. OCT is often connected with scattering samples and therefore with speckles, and exploiting the speckle statistics allows to say information about deformation, about flow pattern, and in such a way to get information about elastomechanical features. And as an interferometric technique, one can also use the phase information, the phase shift due to geometric path length changes or due to refractive index changes. It's, for instance, you can see here, these are more or less optical path length maps, and also caused due to changes in refractive index. And also frequency shifts can be exploited, leading to Doppler OCT and getting information about velocity fields, or one can consider amplitude ratios or phase shift, which is exploited in polarization sensitive OCT. And in such a way, additional features beyond structure can be extracted, providing insight on functional characteristics of materials. And some examples here for. First is a tensile test in polymer plate, which is under load and strained. And you can see here the speckle OCT pattern with almost no information. A bit maybe you see the flickering, and that is statistically and patchwise analyzed by image correlation. And now we can discriminate between three regions, more or less the whitish, that is relatively static pattern, that is a flow, violet is a flowing pattern, and brown is more or less deeper, where we have only noise. And similar is also here another tensile testing that is here monitored within full field OCT configuration. And you see here now also this evolution of the fracture point and the jumping out of the internal glass fibers. And that is not monitored, let me say, from above, like within simple microscope. That is monitored in some depth in a more or less semi-transparent whitish polymer sample. And we get inside the information in a non-invasive, non-destructive way. Coming now to phase sensitive or polarization sensitive OCT. So we have here a two-channel configuration measuring independently the two polarization directions and taking the ratio or the phase shift between these two interference signals according to polarization direction. And in that way we can extract the retardation image and the phase orientation image, which finally gives information about the birefringence features of the specimen. And you see here now this was the sample with the flow pattern, which is not very characteristic only in the reflectivity, in the intensity image, but where you can get detailed information due to the fringes in this retardation image. And that can be analyzed and provides often, especially for polymers, also information about their internal strain. Here another example, the crystallization and the formation of microcrystallites. And here you see this evolving microcrystallite, here in enlarged view, which additionally provides information for such processes in polymer engineering. Here, finally, also often the question of ground truth. Here is a special light modulator containing a liquid crystal layer inspected. That is a ground truth, and more or less that is a measured phase retardation image. Extension of spectral range is one essential option, multimodal OCT and combination with mathematics and signal processing. Meanwhile, beyond these conventional supercontinuum laser diodes, also new light sources are applicable, which use nonlinear effects in photonic crystal fibers, so-called supercontinuum lasers, and they cover mid-infrared spectrum meanwhile, and also near UV spectrum. And these sources can be applied for now also new classes of materials like ceramic, and you see here the images are taken still in near infrared. You see here the coating, but you see you cannot penetrate. One can see one cannot penetrate within ceramics, these white ceramics, And there is highly scattering in near infrared range. It was predicted already that going towards the range, spectral range of 3 micrometers or 4 micrometers, one can penetrate much deeper and also detect hidden structures. So that is a paper of Feng Zhu, where he in 2014 has done such simulations, and that was a motivation for us to extend in mid-infrared range about 3-4 micrometers. And you see here also now a comparison of a sample which containing several internal structures, and they are more or less not visible in an OCT system operating at 1.3, also in near infrared, but have been clearly visible and recognizable in our new OCT, which is operating at roughly 4 micrometers. So the resolution is a bit lower, that is understandable because it's higher wavelengths, but we can penetrate much deeper in these ceramics and see hidden structures there. And these can also be combined. Mid-infrared range is interesting also for spectroscopy, and the OCT imaging can also be combined with spectroscopic imaging and getting not only structural information but also to get chemical information, and so having not only sensitivity to structure but also specificity to the chemical compounds. And finally, also we use also modern techniques for automated analysis, and there are a huge amount of data occurring, and therefore also automated data analysis is needed. And nowadays these are these learning tools for instance, classification of materials, classification of samples here with respect to different pigments, and more or less it's the same shape, 3D printed samples, but depending on the color of the pigments, one can see internal structures more or less. For instance, in semi-transparent, you see it here relatively good, but in this whitish, they are hidden. And applied machine learning to extract this information and to classify it. And in technical applications, there we have results of about 99% accuracy with a lot of training data of 3,000 images for deep learning, and classification accuracy about 95% for conventional machine learning tools like random forest and support vector machines. And in such a way, I want to summarize, I want to bring the message that OCT is not only a tool for getting structural information, but also dynamical processes can be monitored and functional features can be extracted. The extension towards new spectral ranges will enable new material classes to be tested. Multimodal techniques can extend the insights, and we have also different variation methods by contrast, and nowadays all tools for automated image analysis become available. And in such a way, low coherence imaging has potential, OCT imaging has potential also for future in medicine and also in active testing. And by this, I thank for my team at the company at Recent, and I think also my team at the university in Linz and the county of Upper Austria and the FFG Foundation for funding. Thank you for your attention.
Thank you for that insightful talk, Dr. Bettina Hasey. Now the stage is open for questions. Okay, Doctor, I assume that you have no questions from the speaker. Once again, I thank you for being a part of this webinar and hope to associate with you in our future events as well, Doctor. Thank you so much. Moving on to our next plenary presentation by Professor Zimmezu, Brown University, USA, and presenting on the title, Mining Gold for Chi-Square on the Way to Quantum Technology. As the professor is not available, I'm going to play his PPT presentation. Thank you for that PPT presentation, Professor Jimmy Ju. Now moving on to our next presentation by Dr. Konstantin Falagis, University of North Carolina at Charlotte, USA, presenting on the title by Metrology of Freeform Optics Using Vision Rays. As the speaker is not available, I am going to play his video presentation.
Good afternoon, everybody. My name is Costa Falangis, and I'm from the Good afternoon, everybody. My name is Costa Falangis, and I'm from the University of North Carolina at Charlotte. Today, I'm going to be speaking about a metrology system for freeform optics, which uses a concept which is actually known from generic camera calibration systems. And this concept is basically based on so-called vision rays, and those vision rays is something that we adopted to actually perform measurements on freeform optics. The co-author for this presentation is Mrs. Ramirez Andrade, and she's also from the same university, and she's currently doing her PhD in that area. This work has been funded by the Center for Freeform Optics, and the Center for Freeform Optics is actually a collaboration between the University of North Carolina at Charlotte and the University of Rochester, and together we are basically forming the center and also with a lot of other companies to actually do research in the area of freeform optics. Freeform optics are some new type of optics which are actually expected to revolutionize the area of imaging and non-imaging. The idea is actually quite simple. Instead of having those kind of like symmetrical lenses, as we know it from the classical optics, now we are now having optical surfaces, either transmissive or reflective, which can actually have any shape. They don't need to have a axis of symmetry, and they can have actually any shape. And in this way, we can actually create systems which are having a much higher performance. And examples of freeform optics are actually found almost everywhere, in lighting and illumination, in lithography, in mobile displays, remote sensing, and surveillance, in energy research, transportation, heads-up displays, LiDAR, medical and biosensing applications. So there are lots of areas actually referred to quantum cryptography where actually freeform optics are employed. I'm sure if you're now looking at your mobile phone and looking at the camera lens of your mobile phone, you will find also a freeform optical lens inside that phone as well. And at CFO, at the Center of Freeform Optics, we are basically carrying out research in that area, and we have many member companies who are actually carrying out research. And actually, you can see from here, from the names of the companies, which ranges from Facebook Reality Labs to Nikon. There's all sorts of companies there who are actually having a strong interest actually to carry out research in the area of freeform optics. And and all the things, and this center actually brings all those companies together. There are numerous faculty members actually involved in the Center of Freeform Optics. Here are a few actually listed over here. So Dr. Roland, Dr. Lambropoulos, the directors at the University of Rochester, and Dr. Zaleski and myself, we are actually the directors at UNC Charlotte. And if you're looking at the names of people involved, many of the researchers are actually doing research in the design of freeform optics. Other researchers are doing research in the manufacturing, the fabrication and polishing of freeform optics. And others, as myself, are actually doing primarily the research in the metrology and the measurements of freeform optics. And historically, when we were thinking about designing an optic, there were always like some people who were designing an optic, and then they had an idea, then this was manufactured, and at the very end, the manufacturing people brought this to the metrology in order to see if the manufactured item actually met the specs. In the area of freeform optics, it's actually slightly different. We don't follow anymore this linear trend. To create a freeform optic, you actually have to bring much more know-how to the table. And the metrology, the design, and the manufacturing has to actually happen concurrent. So people who know design, of course, need to know actually how to manufacture optics, because they know the samples that they're designing need to be able to be manufactured. But at the same time, the designers also need to know if the sample that they're manufacturing can also be measured using metrology, and if it can also be measured in a specific amount of time, for example, or with which instrument it can be measured, because all this plays back into the cost of the system. Because you can always design a freeform optic, but if this freeform optic is very expensive, nobody's going to buy it. So the designers need to know about the manufacturing process and also about the metrology process as well. And at the same time, the other areas also need to know about the others as well. So it's always like a back and forth between manufacturing, metrology, assembling and alignment, and as well, of course, also the design of freeform optics. Those concurrent engineering principles have actually been discussed in a recent review paper, which have been actually published here in Optica, and I encourage everybody to actually have a look at this one if you're more interested. Going back to metrology, so usually in metrology we are often interested in either measuring the so-called form of a sample, which are basically those lower frequency shapes, and or the so-called mid-spatial frequencies, which are basically higher order Wernicke's, or these kind of like this high frequency grading structures over here. They are often a result of the manufacturing process. So people who are manufacturing some optical samples, they want to know actually how the mid-spatial frequencies look like. Often, if you're diamond turning a sample, then you have those circular ring structures over here. And if you're milling a sample, you may have this raster pattern over here in the mid-spatial frequencies. And this is actually a picture from Dr. Zaleski over here, and he actually showed that for wavefront error, which is actually equal between these two structures. The milled surface has a much worse imaging performance and compared to the diamond turned surface. So we have two wavefronts, the same RMS, and as we in the error, and we can actually see right over here that the turned surface actually looks much nicer, and it actually makes people question the importance of actually RMS as a quality measurement. So going back to metrology, actually often when we speak about metrology, we always hear about CMMs, and CMMs are actually very nice if you're actually working with a small volume for high-end applications. You can actually afford a very expensive CMM, and if you have a sample which can be expensive, you just measure the sample. You have only a few of those samples. You can take your time, and CMMs are actually great if you're actually working in the small volume regime. If you're working in high volume applications, usually the price is justified to buy a computer generated hologram, and then there you can actually do interferometric measurements with a CGH. When it comes down to medium volume applications and you're looking into mid-spatial frequencies, then deflectometry is actually a very nice technique, because deflectometry provides very accurate results for the mid-spatial frequency region. It has lots of systematic errors, but those systematic errors are low frequency in nature, so they provide you like very bad form measurements in the order of 0.5 micron to 2 microns. But when it comes down to mid-spatial frequencies, the error is actually in the order of 10 nanometers. So deflectometry is actually a very nice tool to measure mid-spatial frequencies, and it's actually very useful for medium volume applications. And the principle of deflectometry is actually quite simple. We have basically an LCD screen, and the LCD screen emits rays in all directions, but there's only one ray which is actually reflected by the surface and then basically catch at the given pixel by the camera. So there's one pixel, there's one ray actually hitting into the camera, and because we are projecting different patterns or displaying different patterns on the screen, we actually know where this ray came from. So we know the starting position of the ray, we know the end position. And the problem we don't know is actually where the sample is located. So, and because of this, we are not really able to calculate the slope. There's this so-called slope distance ambiguity, as you can see right over here. So if the sample is further away, then the same reflection is caused by this angle over here. And if the sample is closer, then we almost have like a 90-degree reflection. So if you want to calculate the slope of the sample, or the surface slope, you actually need to know where the sample is. And this is one of the big difficulties with classical deflectometry. Now, however, when we're comparing this with interferometry, it's actually free from retrace errors, and this is actually a very big advantage when compared to classical interferometry. If you're adding a second camera to deflectometry, then you can actually resolve this height-slope ambiguity, and basically you're basically relying on how good you're calibrating your system and how good you know actually the baseline between the first camera and the second camera. The biggest disadvantage of deflectometry is that it actually depends on optimization solvers. So because you don't know the distance between the screen and the sample, the camera and the screen, or the camera and the sample, you're always relying on some sort of iterative procedure and optimization solvers that allow you actually to estimate those distances. And if you get them wrong, or if the solver is trapped in a local minimum, then you're producing huge form errors, and this is actually the reason why deflectometry is not really working very well in the form regime. It's good for mid-spatial frequencies, but not very good for form. So today I would like to discuss one new technique, and this is what we coined actually vision ray metrology. And we actually recently published this one in Optics Express. And the idea actually originates from so-called vision rays, which are actually part of so-called camera calibration techniques. And it's actually a very nice technique, and we actually adopted this principle to the metrology of optics, and in this case we applied it to the metrology of freeform optics. Those of you who work with camera calibration techniques, you may have heard about not only deflectometry but also in fringe projection or classical photogrammetry. There are always like specific camera models employed, which are kind of like describing how the rays are basically going through the imaging system of a camera and then reaching basically the pixel. And those models are actually kind of important because a point in 3D space can actually be mapped onto the sensor, onto this pixelated sensor of the camera. And this is actually kind of important for 3D reconstructions. If you don't want to do like some sort of triangulations, for example, then you need something like this. And classical camera models, they usually have like 5 linear parameters and then 5 nonlinear parameters. And then you're working a lot with linear algebra, homographies, and those kind of models. And the idea is actually quite simple. They're actually trying to mimic a so-called pinhole model, where we have different pixels of a camera sensor, and they are all corresponding to different rays. So each pixel basically corresponds to one ray and basically can see in one specific direction. And all those rays are going through one point, one focal point. And this model is actually not very accurate. So what people are doing, they're actually applying some nonlinear corrections. And then with those nonlinear corrections, they're actually improving the reconstruction a little bit. And another thing what optical designers are doing, they're actually creating like some very fancy lenses. I know Nikon is doing some of those fancy lenses with some of aspheric surfaces, which are actually mimicking this pinhole model actually quite well. And those ones are actually working very well with the pinhole model. But in general, regular optical systems don't really work very well with this so-called pinhole model. And the so-called vision ray model is actually kind of like simple. There's actually no restriction imposed, as we can see right over here, that all the rays have to go through one point. In the vision ray model, every ray is actually independent and can actually point into any direction. Two rays may go through the same point, but it's actually no restriction on the model itself. So when we're looking at the caustics of our optical imaging system, we see something like this as well with the vision rays, but they're actually not creating a point. There's actually a circle where all those rays are concentrated, but it's never gonna be a point. It's more like a disk actually right over here. And the way people are measuring vision rays for camera calibration techniques is actually quite simple. They're taking like an active target like this, and they're moving this target around the volume. And then, for example, like Porto did over here, with two reference cameras, you can basically determine the XYZ position of one point on the screen. And then with our camera, the red one over here that needs to be calibrated, you can actually see what the vision ray can actually see when moving the screen to different positions. And then if you're just measuring a point of a vision ray at multiple distances, you can actually just fit the line in 3D and then have the vision ray itself. Oleg did something similar as well, where he just moved it around, and he has like also a nice algorithm which allows actually to do like some quick reconstruction. So we're basically just moving a target through 3D space, and then we are just recording for each vision rays a point cloud, which is ideally actually on a line, and then we're just doing a single line fitting for each pixel, and then we have actually the ray. We have the ray direction and also the origin of the ray as well. And this is actually like a typical result for a camera. And as we can see right over here, we see that the angles in X and in Y direction, or tangents of the angles, look like this right over here. And this is basically the origin in millimeters for each pixel over here. And we can see we have like a range of plus minus 1 millimeter in X and Y, and we have actually the tangents over here for this camera is basically plus minus 0.15 or 0.2, as we can see right over here. We have tested actually this vision ray model extensively, and it turned out the vision ray model is approximately like 9 times more accurate than the classical pinhole model. Of course, as I mentioned before, it all depends on the imaging system. So if you get the Nikon lens, which is optimized to work actually for the pinhole model, then the performance may be the same. But if you have a regular lens, then you see actually a huge difference. Now, if you make your own imaging systems, then in general, the vision ray model actually performs a factor of 9 or 10 better. When we're doing those kind of calibrations, we always have to keep in mind that if we're using an active screen, like a display, that there's always like a small cover glass on top of the display. And if you're basically observing a point with a cover glass, we're actually not really observing the origin. We're actually having like this, due to Snell's snore, like this cover glass effect over here, and we're actually getting like some wrong information. So what we did in our group was actually to get rid of the cover glass itself and just use a simple passive target over here, where we're actually using a projector below, and we're just illuminating the projector with different fringes. So this target has different XY markers, just to have like a reference frame for the X and Y position. And then with these patterns over here, we can actually get sub-fringe resolution for those positioning over here, for this positioning. So, and then we just take the camera that we want to calibrate, and we're just moving the camera along this linear stage. And then exactly with this camera, basically the vision ray, basically once it reaches the diffused target, it actually measures exactly the correct position. So there's no cover glass effect there. What we see is also what actually really exists. And when doing those kind of measurements, we can easily get, without any problems, we can easily get reprojection errors in the order of like 14 micrometers. In comparison, if you're using a display, you're in the order of 100 micrometers. Huh? So it actually helps a lot to use like this kind of like passive target. So getting back to the metrology of vision rays. So how are we using actually vision rays to measure new things? And the idea is actually quite simple. Imagine we have like a camera that is already calibrated using the vision rays. Here in this case, we're using a telecentric camera so that we actually have not much problems with not the critical sample placement. So we place the sample in front of the telecentric lens, and then we basically just record the vision rays. And the sample, let's say the lens in front of if the sample is a lens, in front of our reference imaging system, kind of like produces like a deflection of the vision rays. So we can actually measure the sample-induced deflection of those vision rays, and these are kind of like related to the slope of the object wavefront. For example, if you have a convex lens or a concave lens, then the radial and the tangential slope basically look like this, and we can actually measure the surface slopes. So this is actually in radial direction, and this is actually in tangential direction. And if you plot the vision rays, you can actually see that both the concave and the convex lenses, they're actually expanding. But if you look at the focal point, you'll actually realize that the convex and the concave lens, they actually have a different or the focal point of those two lenses, they're actually at different positions. And from there, you can actually find out if the one lens is concave or convex. Or you can just look at the tangential component of those vision rays. Then you can actually see the vortex. And from the direction of the vortex, you can actually see if you have a concave or convex wavefront. And we've tested also this vision ray method not only with regular lenses. Here below, we can actually see right over here, we can actually see a cubic faceplate, and we can actually measure very nicely those vision rays. Two cubic faceplates are actually forming an Alvarez lens, and here we can actually see again the vision rays for the case of an Alvarez lens. And again, here we bought also like some off-the-shelf glasses, which are basically something like an Alvarez lens glass, which are actually adjustable. And just by adjusting the lenses, we can actually see over here we can actually change the ray bundle over here, so that that's actually very nice and visible. Doing some real measurement with this. So once we have those slopes in X and Y direction, or in tangential and radial direction, we can actually integrate those slopes. You can actually apply so-called modal integration or zonal integration, and then from there you can actually get the wavefront, and then fit Zenicus to the wavefront, and then see actually how this one performs. And then once you remove the best fit sphere, you can actually see the deviation from the best fit sphere. As I mentioned before, our reference target had some markers, and in those regions we actually, technically speaking, we don't take measurements, so that's why we have like some small artifacts there. But that's also one of those things that we are currently working on, and shortly we're going to be presenting a solution on this. Here's the other example where we're actually having those off-the-shelf glasses, and yeah, again, just by adjusting the position of those Alvarez or the cubic faceplates, we're having this Alvarez lens, and again, we can adjust the ray bundle, and yeah, we can actually reconstruct the wavefront, and look also at the deviation of the wavefront. And if you're removing the lower order Zernikeys, you can actually see the mid-spatial frequencies very nicely over here, and then give some information on the regarding this one back to the manufacturer. So yeah, here's the same thing as well with a cubic faceplate, and this is also something what is actually related to the manufacturing process itself. So when we compare this to deflectometry, there's actually kind of like an important difference. No? So if you're looking at the distance between the camera and the sample, for vision ray metrology, it's actually unknown, but it always remains constant. If you're looking at the distance between the screen and the sample, it's also unknown, but the Z-step is actually known very accurately because you can actually buy a nice stage and you can move it in one direction, and you can buy stages nowadays with a 100 nanometer resolution, or an uncertainty in the order of 200 nanometers, and you're actually getting the Z-step right. And when it comes down to the sample placement, in deflectometry, it's kind of like critical because you need to. It depends on the success of your optimization solver. If you're using telecentric lenses, it actually works very nicely also for vision ray metrology. So the sample placement is actually not so critical. And if you have baseline drifts in deflectometry, you get huge errors in the measurement. In vision ray metrology, you're actually making differential measurements. So all those drifts kind of like are calibrated, are canceling each other out. So if you had some time between your last calibration and your measurement, because you're doing back-to-back measurements of those vision rays, those errors should, because of the drift, should actually cancel each other out. The reference target is cover glass free, so we don't have any cover glass problems now. And the idea is we are just looking at the sample induced deflections. And when looking at the error budget, we know that with phase shifting we always obtain like a 2 pi over 400. Then this translates actually in accuracy in measuring the vision rays of in the order of 500 nanometers, depending on of course it depends on the number of planes you're using. And again, if you have this random error in your vision rays and you're doing some modal fitting or modal integration, the error in the reconstructed wavefront is actually really, really small. So it's actually so small that I don't even dare actually to say this number. The elephant in the room are actually systematic errors. And those systematic errors are basically due to aberrations or thermal drifts. And this is actually the ones that we have to combat, which is very similar to deflectometry itself. And this is something that is actually still work in progress. But if you have like an axial drift of 1 millimeter, then this system actually produced like a 50 nanometer RMS. So in summary, we have a nice tool from the area of camera calibrations. We're using this tool to measure freeform optics, and the accuracy, similar to deflectometry, is actually basically limited by systematic errors, but it has less systematic errors, and many of those systematic errors can be eliminated because of the differential nature of this measurement system. Thank you very much, and I'm happy to answer your questions.
Thank you for that insightful talk, Dr. Konstantinos Falagis. Now the stage is open for questions. Okay, Dr. Konstantin, I assume that you have no questions from the speakers. Once again, I thank you for being a part of this webinar and hope to associate with our future events as well, Doctor. Thank you so much.
Thanks.
Thank you, Doctor. And the next presentation will be by Dr. King Gu, North Carolina State University, USA, and presenting on the title, Perovskite Light Emitting Metamaterials and Devices. We'll wait for Dr. King Gu, and if he is not available, we'll go to another speaker. As the speaker is not available right now, we will proceed with the next available speaker. So next presentation will be by Dr. Isabel C.S. Carvalho, Pontifical Catholic University of Rio de Janeiro, Brazil. And on behalf of Professor Isabel, I'm going to play his presentation now.
Hello, I tried to route with my mobile, but it seems that my internet is not good. So,
hello, doctor. Just now we completed your video presentation, doctor. Thank you so much, doctor.
You're welcome. So you have my video, my presentation, no?
Yes, doctor. Just 10 minutes before itself, we played your presentation, doctor.
Okay, so it's going to be, what time it will be then?
Still one more speaker need to join, so I'm waiting for that speaker.
Okay.
So we completed with your presentation also.
Okay.
Okay,
But
doctor.
I just didn't understand. My presentation is going to be at 14. Still, or are you going to present it now? That's what I want to figure out.
As some of the speakers are not available, so that's why we played your presentation, doctor.
So you're going to...
So we'll see if anyone joins.
Okay. Okay, that's fine.
Okay. Thank you so much, doctor.
You are easy, Lizzie? You are Lizzie? No,
doctor.
No.
I'm conference host. If you want anything, any issues, you can tell me. I will forward it to Lizzie, conference manager.
Oh, no, it's fine. So anyway, so I wait now. That's it.
Hello, doctor. You are waiting for your presentation.
Okay, that's fine. Yeah, 4 hours. I'm 4 hours. You are 4 hours ahead of me. I'm in Brazil.
Okay, doctor. If you want, I'll play again your presentation, doctor, now.
Okay, that's fine.
Thank you so much, doctor. I'll play now.
You're quite welcome. You have it, no? Good morning.
So now the next video presentation by Dr. Isabel C.S. Carvalho, Pontifical Catholic University of Rio de Janeiro, Brazil. And on behalf of Professor, I'm going to play her presentation.
Good morning. My name is Isabel Carvalho. I'm going to talk to you about the cellulose nanocrystalline based random laser. I work at the physics department at the Catholic University of Rio de Janeiro in Brazil, and my laboratory is called Laboratory of Optoelectronics. So the outline of my talk is going to be, first I'm going to give a brief introduction of what's a random laser, just one slide. And then I'm going to talk about the characteristics of the material we use to build the random laser, so it's the cellulose nanocrystalline needles. And then I'm going to describe two configurations. One is use the nanocrystalline cellulose in a suspension configuration of the random laser, and the other one, we are going to use the nanocrystalline cellulose in a flexible, configuration of flexible film. So this work was published at the Joseph B. and the references here. So what's a random laser? So a conventional laser, you have a gain medium, two mirrors, and then you have some mechanism to pump this gain medium so that you start laser and have inversion symmetry and so on, inversion population and so on. And so what I want to point here on the conventional laser, you have two mirrors and form this cavity whole cavity. On a random laser, we don't have this configuration of these two mirrors. So what you have a medium that can be the gain medium, that the medium that's going to define the laser wavelength. And then we have scatters, some particles that scatter the light that's being emitted by the gain medium. On this configuration here, you can see you have like the scatters and a certain medium. So we pump light from a laser on this medium and it emits light. So in this case, it can emit that it's going to be these red arrows or this green arrow. So the light emitted is going to scatter by the other scatter center, and then that emits also the same wavelength of the laser emission. So on this way, you have amplification of the light. One very interesting configuration, characteristic of the random laser, that it's a multi-directional emission. So on this sense, our work is going to be, we are going to use a dye, rhodamine 6G in ethylene glycol solution, and we use cellulose nanocrystalline needles as the scatter on this laser medium. So first, as I mentioned before, I want to talk about the characteristics of our material, the cellulose and nanocrystalline needle. So this material, they were produced from microcrystalline cellulose from cotton. So this was done by Fernandes et al. In the University of Nova in Lisboa. And you can see here we have an image, a sandbag image of the CNC as in flakes, so micro-sized agglomerates, cross-section. And then if you look here, and if you zoom it, you can see like the needles. So these are the scattered centers that we're going to scatter the light. And also, if you have a zoom here on this image here, and you can see this line here. So these lines here are the scatter centers. So these are the needles I'm talking about. So typically, these needles have a length of 135 nanometer with a diameter of 41 nanometer. And as I mentioned to you before, we have these two configurations, the liquid suspension and the flexible film. We can see here you have the dye here, just in ethylene glycol. And here you just have in a cuvette, you have the dye of ethylene glycol with already with the CNC on it. We use various quantities of CNC-related CNC in ethylene glycol. We varied its concentration, so it was 0.5, 1, 2, 3, 5, 7, 10, and 15 milligrams from ml of CNC and ethylene glycol. After we have this CNC and ethylene glycol, we did a sonication just to disperse the centers, and then we add the rhodamine 6G to this. The rhodamine 6G, the dye, to this CNC and ethylene glycol. So at the end, we have a liquid suspension, typical 1 to 7 milligrams per ml of CNC and ethylene glycol, plus 1 millimolar of rhodamine 6G. So this is the way to have the liquid suspension. To produce the flexible film, we have HPC, so hydroxy propyl cellulose, with CNC in distilled water. So and then we have again the dye in the ethylene glycol added to this liquid suspension. So at the end we have HPC, CNC, rhodamine 6G placed in the molds. Once we have the suspension, we place in molds, and then we dry it for at 6 degrees for 1 hour, and then we end up with this fluorescent flexible film with a typical thickness of 70 microns. So here you can see the film, so it's very flexible. So characterizing the flexible film, again under the MagFag microscope, so we can see the needles. If you look at this needle, that's going to be the scatter center. It's a line along longitudinal axis of the film. So again, continue to characterize this material, the films. We use a optical polarizer microscope to determine if the scatter was forming a cluster in the film. It was clustering the film. So here you have the HPC film, and then you have the HPC plus CNC film. And as you can note, we use polarized light and non-polarized light, and then there is no evidence of CNC clustering for HPC or HPC plus CNC film, because this cluster could influence the results of a random laser emission. So once we have characterized this film and the suspension, we now here show the random laser experimental setup. We have a neodymium YAG laser, Q switch, 6 nanosecond pulse width, and the emission of this laser was 533 nanometers. So on this sense, you have the beam here, you have a lambda/2 and a polarizer just to control the energy of that we launch in the sample. So then I have a mirror, and then you have a beam splitter here that you have part of the energy, the beam of the laser directed to the energy meter, so you could measure, calibrate what's the energy we launch in the sample. And then here you can see you have the sample with the cuvette typically, and then after you have the 532 emission pump, and then we have 5, 6, 7 nanometer emission of typical of this dye laser, and then of a dye laser. And then we have the spectrometer, and then we make the measurement. So here I show the results of the measurement that we have. So for the liquid suspension, on this graph you have the furnace's intensity with the wavelength. As we increase the pump energy, the energy from the 532 energy that we are launching in the suspension. So we increase from 0.08 millijoule to 2.12 millijoule. And as you can see, the spectrum of the emission of the laser that will come out of the pumping of the 532 laser, it starts broadening. It starts varying such that we end up with a laser, so the typical of a laser. So the laser threshold is 0.35 millijoule for this case. In this case, we have a liquid suspension with higher efficiency. So it's 5 milli, the highest efficiency we got, it was 5 milligrams CMC with per ml of ethylene glycol. So this was the case for the suspension, and also we looked for the. I plot that I have the spectrum. Now I have the intensity with excitation energy, and then the full width half mass with the excitation energy. And you can see that the intensity, so we have different concentration: 1 milligram per ml, 3 milligram per ml, 5 milligram per ml, and 7 milligram per ml. And you can see that the best efficiency was obtained for the threshold was with the 5 milligrams per ml. Also, you can look here at the narrowing of the full width half maximum of the spectrum. And again, for the same concentration plot of this graph here, you can see that the 5 milligrams per ml is the one that falls more sharp here. So again, just as I mentioned, the liquid suspension highest efficient was the 5 milligrams CMC per ml of AG. Also, we did the same experiment for the flexible film with HPC CMC for rhodamine CG. And then here you have the graph, the full width half mass with excitation energy, and here you have the emitted energy and the excited energy. So it's, again, we have a decrease on the full wave half mass, typical to up down to 10 nanometer, and then you can see here the threshold. So in this case, the flexible thick film has a laser threshold of 0.30 millijoules. One problem with this random laser that we did is the cellulose base presents a degradation under long excitation regime. So here we have the intensity and the percentual variation of the signal, and then we have here the number of shots. And for the same measurement, we could do measure the full wave half max that was happening. And you can see that the full wave half max has increased. So it shows that the laser presents a degradation under the 1 millijoule 10 hertz excitation. So comparing the film suspension and the film and the suspension, here we have the plot of full wave half max with excitation of both film and suspension. Films in the red dots and suspension is the blue dots. And here you have the emitted energy with the excitation energy. So the film presents a similar energy threshold when compared to the colloidal suspension, but we have to keep in mind that the film has 10% less fundamental 60 than the suspension. So it seems to be more effective. So as a summary of my talk, as I mentioned, we were able to produce a random laser where the CNC needle was scattered components of this laser, where the gain needle was fundamental 6G, the dye. The suspension cuvette was optimized for the CNC concentration of 5 milligrams per ml, and the random laser in a flexible self-support 70 micro thick film was valuable to do, and it is very important that we can make displays, we can make a component with this flexible film. And also the film has a similar energy threshold compared to colloidal suspension, but keep in mind that we have 10% less for the minute 6G than the suspension. We also did a comparison of our work with other works using cellulose-based random laser, and the threshold in this work is among the smallest threshold that was observed in literature. So I would like to talk that this work was, as I mentioned, was developed at PUC. So it involved PhD students, undergraduate students, and also the collaboration of Professor Anderson Gomes at the Federal University of Pernambuco, and Professor Edson Pecoraro at the UNESCO in São Paulo, Araraquara, and also the material that we have collaboration with the Nova de Lisboa, Dr. Professor Suzette Hernandes. And also I thank you for attending this meeting, my talk, and I'd like to thank for the sponsor of my work. Thank you.
Thank you for that insightful talk, Dr. Isabella. Now the stage is open for questions. Okay, Doctor, I assume that you have no questions from the speakers. Once again, I thank you so much for being a part of this webinar and hope to associate with you in future events as well.
Okay, thank you very much for the invitation.
So much.
Okay. Okay. Bye-bye.
Doctor, thank you for your valuable time.
The connection not very much. I couldn't hear you, but I thank you for the invitation.
Hello, Doctor. I can't hear you. Can you see?
Yeah, so I thank for the invitation. Just I think the connection is not very good, but yeah, that's it.
Yes, Doctor. That is the option.
Okay, so I leave the meeting now. Yeah.
Thank you so much, Doctor.
Okay, bye-bye.
See you at our upcoming conference, Doctor.
Okay. See you soon.
Thank you, Doctor. Thank you.
Okay, bye-bye.
Bye-bye, Doctor. Thank you. My name is Gause, and I am the webinar host at Continuum Forums. And it is the leading provider of international conference services. Now we begin the opening plenary talk by Professor David Moss, Swinburne University of Technology in Melbourne, Australia, and presenting on the title Integrated Care Microcomb for Optical Neural Networks and Ultra-High Bandwidth Data Transmission. On behalf of Professor David Moss, I am going to play his video presentation.
Hello, everybody. Thanks for watching my talk, and I'd like to thank the organizers for inviting me to give this plenary talk on our work on ultra-high bandwidth optical signal processing based on Kerr micro-frequency comb sources. My name's Dave Moss, and I'm the director of the Optical Sciences Center here in Swinburne University of Technology in Melbourne, Australia. So this is our domestic and international collaborators. Mengqi or Sim10 has just graduated, has done a lot of the work in the lab. Xingwen Xu or Mike Xu is now back in China, has graduated and has a professor position back in China. Dr. Bill Corcoran at Monash University has driven a lot of the data transmission work. Dr. Jiayang Wu is a research fellow in my group. And I particularly like to thank Professor Arnhem Mitchell at RMIT, where a lot of the experimental work was done using his facilities. So this is an outline of my talk. I'll cover a bit of the background of microcombs, the combs that we work on these days, which are soliton crystals. I'll just mention briefly our recent work on ultra-high bandwidth data transmission, and then talk about the optical neural network. So I'll first talk a bit about the work that we published about almost 2 years ago now in Nature Communications, a world record data communications over a single optical fiber with a single chip source. In the main body of my talk, I'll talk about our work that we published in Nature just over a year ago on ultra-high speed teraops per second photonic neuromorphic processors, including a convolutional accelerator for optical neural networks. So this work started originally back around 2005, 2006, when we were looking for different platforms to do nonlinear optics in, and it was clear silicon wasn't very good because of its two-photon absorption. So we got onto this platform that was developed by Brent Little for linear optics called HIDEX, and it has a lot of interesting properties, intermediate properties that make it a sort of a Goldilocks type of platform, and we started exploring the nonlinear properties of this material. So there's a lot of nice things about this platform for integrated photonics. One is that it's compatible with CMOS processing that electronic devices use, which is a really big factor. So we can make very complicated photonic circuits. It has a very high index contrast. So optical fiber is typically a few percent. This is up to maybe 25%. Which means that you can get much tighter bend radii and a number of other factors as well. It's also, despite this high index contrast, still quite low loss at around 4 dB or less per meter. And a couple of years later, we got our first results in Nature Photonics, just simple 4-wave mixing, which had been done before in ring resonators, but we showed that it could be done in a very comparatively low index, very low loss glass material, which had never been done before. So I think that really was the first report that made people sit up and pay notice to these platforms, because everybody was really focused on silicon at the time. And once we published this, a number of groups jumped onto silicon nitride, which is very similar to this platform. We found ourselves in a race with people, and about 2 years later we published back-to-back the first optical parametric oscillator OPO in this platform, in an integrated platform together back-to-back with the Cornell group at the time. So this was really quite a big breakthrough, because even though microcombs, Kerr combs as they're called, so this work was based on the original inspiration, which was the discovery of Kerr microcombs in these exotic resonators by Kippenberg and Bahala in this famous 2007 Nature paper. So since then, this field really has exploded with tons of nature papers and science papers over the last 10 years or so. This is just a sampling from the last couple of years. So since then, it's just been an amazing ride. Our collaboration, our group is focused on certain aspects. Quantum optics has been a big aspect of what we're doing. This is in collaboration with Roberto Morandoti. So 2019 was quite a good year for us as well. We had a major review. There was a focus issue on microcombs and nature photonics, and we had a review on quantum optical microcombs with this is with Roberto, Andy Weiner, and Mike Coos and Christian Reamer, and our other co-authors, and also a paper on high-dimensional one-way quantum processing on D-level cluster states that came out in Nature Physics. And finally, that was the year that we, with Alicia Pasquazzi, discovered laser cavity soliton microcombs, which I'll talk a bit more about later on in this talk. So the real motivation, I think, for these interest in these Kerr combs, integrated Kerr combs, is to ultimately achieve on a chip what was invented around 2000, these bulk mainframe frequency combs by Hansch and Hall that earned them the Nobel Prize. And to achieve that on a chip, basically, that's the final goal. Essentially, frequency combs, this regular array of frequencies, links the optical domain with the microwave domain really for the first time. And using one of the key techniques is this frequency doubling or self-referencing to actually calibrate the absolute optical frequency here. And the things you can do with this are really quite astonishing. I mean, a whole array of different things. Optical clocks, 1,000 times more accurate than the current microwave clocks, and the list goes on and on. And many of these, and some of them anyway, have been achieved already with Kerr microcombs. So, I mean, the ultimate holy grail, if you look in the future, is things like, a NIST clock, or a clock with the accuracy of the NIST time standard in your iPhone, which would allow all kinds of things like even mass sensing from the gravitational redshift of, your clock and so on and so forth. So it really is exciting, this technology. So the key to this so-called self-referencing is actually quite simple. It's just basic arithmetic. If you take, so there's two parameters here. One is the frequency spacing itself, and the other is the overall offset of the frequency. And the offset is the tricky bit to get because you can't measure it directly. But if you take one of these frequencies here and you frequency double it with second harmonic generation, and you beat it with, you can find the difference frequency with the closest comb frequency up here, and that difference frequency gives you this offset frequency, which is usually in the microwave region directly, and that is what links the microwave with the optical frequency domain. So as I say, the first part of my talk is going to focus on our world record data transmission experiment over single mode standard fiber with a single chip source, and we did this over an installed network in a field trial as well. So, but I must say, I mean, this work actually, to be honest, it almost got up as Nature and went through 3 rounds and didn't quite make it, and we weren't very excited about it, to be honest, and we published it in Nature Communications, and then we just sat back and didn't expect much, and then bam, it just absolutely went viral around the world. I don't know if anybody has seen any of this or remembers it, but it just took my breath away. I mean, coverage in the BBC News, even the Daily Mail in the UK, Radio Canada. I mean, just something like 150 media outlets. Then we had a full-page article written about us in the Australian, and about 140 media outlets around the world. Just a phenomenal reception. It was just really exciting. Anyway, the motivation for us doing this was that telecommunications has really changed in the last few years. It's become really moved away from long haul and conventional, the old style long haul communications, and now it's driven by regional data centers, in particular data centers, even more so than metropolitan networks. And so the emphasis now really is on small, cheap, high performance devices. And so that's really been a big part of our motivation for looking at this. So solitons have been around for a while now, since about 2014. They were first discovered really probably by Tobias Kippenberg. Microcombs have been around, as I've shown, since 2010, but they hadn't really been that useful until people found out ways of phase locking these things or mode locking them. And these so-called dissipated Kerr solitons was the first breakthrough in that regard, and so that enabled a lot of things to be done. The issues, though, is that these things are quite complicated, and now, I mean, a lot of breakthroughs are being made and to understand and tame these, and it's becoming quite routine to do it, but nonetheless, it still requires incredibly complicated control and pumping to get around the sort of nonlinear feedback and the fact that the resonance shifts around when you start, pumping it and getting oscillations. So it's a bit of a challenge. So the first big breakthrough in this area came in 2017 with a paper by Kippenberg's group, where they used a microcomb operating through these so-called dissipative Kerr solitons, DKS solitons, to generate a comb with 100 gigahertz spacing, and they used this to achieve 28 terabits per second transmission, which was a record for certainly at the time for a single device. And so they worked in both the C band and the L band using a coherent modulation format of 16 QAM, quadrature amplitude modulated, and achieving a spectral density of about 2.8 bits per second. There should be a second in there per hertz. So this is a tremendous result that was a benchmark in the literature. We came along when we wanted to apply soliton crystals that we've been using for a while, it was interesting to try to apply it to this application. Soliton crystals are very interesting for a number of reasons. First of all, they're very robust, stable, and energy efficient. And the reason for all this is really fairly straightforward. It's because the energy of these crystals going around in the loop is much closer to the chaotic background state. And so when you switch from the chaos to the soliton crystal, the energy step is very, very small, almost non-existent. And so the thing doesn't shift around. And so you can actually just move through this slowly, even tuning manually, and you can get it to oscillate, and you get these quite interesting spectra at the output. It's been very useful for us for microwave signal processing. These combs were actually discovered by the NIST group, by Pascal Delay and co-workers in about 2016 or 17, and the understanding exactly that. This just shows the progression of the different states. So the first state that usually oscillates is these so-called primary combs, or Turing patterns, if you like. The spacing here is given by the peak in the modulational instability gain peak. And then if you ramp up the power and the tuning, it goes through the chaotic regime, and then out of this distills the soliton crystal states, as you see here, where you get these very low noise states. So most of these are fairly low noise, except for the chaos regime. So we'll look at this in real time as we're pumping it, and you can see that as we sweep the pump, we get the primary combs, and then boom, all of a sudden the soliton crystal combs come, showing how you can actually manually tune through the thing. So as far as our transmission experiment goes, I mean, in principle, it's very simple, right? We just take the comb and we flatten it and we modulate it. and then we combine it with WDMs, put it over the transmission fiber, and then demux and detect. But what looks simple in practice, in reality, is a lot more complicated. The other thing we did was to do the demonstration in a field trial over a real network. So this is the first time that soliton crystals have been used to do this sort of thing. This was a network in the metropolitan Melbourne area that was established for research purposes, and so we used that network to demonstrate our transmission experiments. So this is some of the results, and you can see that again a bit more detail on the transmission experiment. We flatten the comb, and then we do the transmission. And when I say we flattened the comb, that's actually not necessary. We did it just to show that we could and not suffer too much penalty. Again, this is a little bit more detailed, showing the amplifiers and so on, and in the link and whatnot. Just some of the transmission, the network details. And again, this is for the hardcore people that want to know a bit more detail. Just showing some of this. The actual experiments are actually quite challenging, and it's really a testament to Bill Corcoran and the work that expertise that he brought to this experiment that enabled us to do it. So this is looking at the actual transmission now. So we actually got up to 64 QAM, which is a record, at 25 gigahertz spacing. And using only the C-band, and this shows the constellation plots, back to back and through the network and so on, showing very nice plots. So just a brief note, I guess, for the uninitiated, used to be in the old days that it was on ones and zeros, and now it's a lot more complex. Each bit slot, if you like, or symbol can occupy one of, in this case, up to 64 values, depending on the amplitude and phase of that particular bit. This shows the average over time, which shows all of the bits occupied. So this is 64 QAM. There have been experiments up to, I'm not sure what the record is now, but probably over 1028 QAM. Extremely complicated data modulation formats. And some of the results here. So again, these are kind of details for the hardcore aficionados that are into data transmission, but there's a number of different benchmarks: bit error rate, forward error correction, soft decision, and so on and so forth. And GMI is a generalized mutual information, which is a new benchmark people are using. That's what we used in this work. So we achieved in the end pretty good results. I'll compare it to other people fairly soon here. So this really was a record. It was a record for a single source over single mode fiber. We got 50% higher bit rate than the Nature paper of a few years ago. But more importantly, I think we got 4 times higher the spectral efficiency. So right up to 11 bits per second per hertz, which is really important. We have better noise, better efficiency, and much higher stability, turnkey generation basically, because we don't need these feedback loops. And we did the field trial over a real network. So this compares our results with some others that are out there in the literature. Some of them you can't really compare to because they're over this multi-core fiber. So we just put it there for reference. So in conclusion, we report record high bandwidth for optical fiber data transmission from a single source over standard fiber. We achieve a 50% higher bit rate than before and 4 times higher spectral efficiency. And we do this over a field trial in an installed network. At a record low spacing of 49 gigahertz at 64 QAM. And these particular combs are very high efficiency, 40%, and very stable and reliable to work. So now on to the second topic of my talk, so Kerr microcombs for teraops per second scalable optical neural networks. So optical neural networks is a really hot topic these days. There's 2 big reviews just published, one in Nature in December and another this month or last month in Nature Photonics. Our paper was published in January back-to-back with a group from Europe with Tobias Kippenberg in Nature. And it was interesting that for almost the entire week of that issue, we were actually on the front page of Nature, and the only research article actually. All the rest, if you can notice, are either news or editorials, and so it was very exciting for us. So the content for this part of the talk are 3 parts. I'll talk a bit about the background of optical neural networks, then our work on teraops per second convolutional accelerator based on time wavelength interleaving, finally with the optical convolutional neural networks. So artificial neural networks have really become almost ubiquitous in all kinds of areas in our life. Formally, it's a mathematical algorithm to fit nonlinear complex models. If it's trained with proper training, it can vastly outperform human brains. It's widely used in industry and research for a wide variety of applications. I guess the most common ones are probably things like image recognition, speech, translation, and decision making. And it excels at things like gaming and all kinds of things. It's going to be absolutely indispensable for self-driving cars. So this is the mathematical model for neural networks. They usually consist of an input layer, 1 or more hidden layers. For deep learning, it usually consists of many hidden layers, and then the output layer. Each layer consists of many neurons. In the case of digital electronics, thousands or tens of thousands of neurons, each all interconnected by synapses that are weighted. And so each neuron basically sums of weighted inputs of the synapses, and then outputs a nonlinearly scaled version to generate the decision of each neuron. So the scale, the number of neurons, determines the difficulty of the task that can be done. So the more neurons, the better, and the more deep layers, the better to perform deep learning. The other parameters, of course, the speed, the faster, the better. This is the throughput speed. The things like latency is not always that much of an issue. So the idea here is sort of neural networks 101, I guess, is just to train the weights, basically to train the network to find the optimum weights. And so you test it with a huge testing set to generate the outputs and compare the output with what the ideal is, and then vary the weights. There's a whole heap of ways of doing this. It's simplest is the backpropagation method, but there's lots of other ways to finally come up with the weights for a particular task, and then just run it to analyze new data. So this is the hierarchy, if you like, of the different networks. The first breakdown, I guess, is whether it's software, algorithms based, or hardware. And then for hardware systems, it can either be digital or analog. So the thing that distinguishes these two is that digital systems are sort of based on the classic, computer architecture, the von Neumann sort of architecture, where the processing and memory are in different places, and so it has to read and write data to the memory every time it does something. There's advantages of this. It's very flexible, and you can have a huge parallelism. The disadvantage is the cost in both energy and time. So this partly explains why electronic processors, each processor is limited to about 700 megahertz. They need thousands of these in parallel for the Google TPU chip, for example. So analog, on the other hand, is not limited by these. And so we feel that there's going to be a real opportunity perhaps for hybrid systems, with some of it being done with analog and combined with digital systems. So for analog systems, they're basically split into electronics versus optics. And again, the trade-offs here are similar. Electronics is limited by the electronic bandwidth, basically. Optics has the potential for very high speed. Electronics is a lot more flexible, I guess, and in terms of mature fabrication technologies, you can get very high integration densities and so on. Whereas optics potentially can get up into the terahertz bandwidth. So we envision systems, really optimized systems, that probably involve both aspects to this, to combine the advantages of both. So over the years, there's been a very wide array of vastly different approaches to optical neural networks, some really ingenious approaches. Integrated Mach-Zehnder arrays, this is primarily the group at MIT that's doing this. And reservoir computing with a loop where you basically circulate symbols and operate on them that way. So some other techniques that have achieved quite a bit of success, the diffractive optics based, working on parallel processing of data with free space optics, and then phase change based memory materials where the weights are sort of embedded in the phase change materials. This was the paper that was published with ours in January. So all of these techniques really have advantages and disadvantages. One of the big limitations is that there really hasn't been any reports of high-speed networks that optics is really capable of. I've got 20 gigahertz listed here, but really, except for one paper, all of them have been limited to around 1 gigahertz, and many of them are much less than that. Some of them are actually even DC or zero speed sort of work. You have to basically operate it in a continuous or DC mode. So that's one limitation. The other is the fan-in for optics is determined by the physical connections. So for fully connected networks, the number of sort of synapses is really limited, and that can really restrict the power, if you like, of the network. So what we're looking for is a combination of high computing speed that's enabled by optics and a really high or sufficient fan-in, if you like, or connections for real-life data or real-life problems. So one really powerful approach that's been used is this so-called convolutions. And this really addresses the scale of the network. And essentially it changes a fully connected network into a locally connected network by doing these convolutions over the data, where you see that basically it creates a number of locally connected neurons where each kernel, I guess, extracts the key hierarchical features out of the data to really greatly reduce the sort of parametric complexity of the network. So this is a very powerful approach. This is not an actual network as such in itself. It's the front end of a network that does the convolution before the neural network takes over, but it greatly reduces the number of synapses and parallel connections. So this shows the basic principle of the convolutional vector convolution accelerator in our system using time wavelength interleaving. So basically, the weights of the kernel are encoded in the weights assigned to the weights of the different wavelengths. So if you've got a, say, a 3x3 kernel, that's 9 elements, so you would need 9 wavelengths, and they'd be weighted according to the weight of the kernel. At the same time, the actual data itself is recorded serially in a series of symbols, if you like, and each symbol has a certain resolution. It's an analog symbol, so in our case it was 8 bits of data. So the second step is to basically use the serial electrical data to modulate an electro-optic modulator, just a single modulator with all of the wavelengths from the kernel passing through, and so basically multicasting the temporal waveform of the signal onto all of the weights or all of the wavelengths of the kernel simultaneously. So the next step is to take all the wavelengths and progressively delay them through a wideband dispersive optical buffer. So in our case, it's just standard SMF fiber with a dispersion of 17 picoseconds per nanometer per kilometer, and was set up so that the delay between different wavelengths precisely equals the intersymbol duration. And so basically what it does is allows you to line up successive bits or slots of the different the different symbols for the data on different wavelengths. So basically, the next step 4 is a very simple step where you just simply detect the output signal, and because of the delay between the different wavelengths, you're essentially summing or detecting, adding together all of the weights or the signal in the different slots. And so basically, this gives you a dot product between the kernel and the input vector waveforms by adding them all together. You fold it in with the weights of the kernel. So in this way, you can really get an amplification of the overall speed, because the net speed is 2 because you're summing and multiplying it accumulate. The n is the number of wavelengths, and b is the basic baud rate of the input data. So you can get this multiplication factor happening. So this shows a schematic of the setup. So we have the weight vector here, which is the convolutional kernel. These tend to be quite small, either 2 by 2 or 3 by 3. So 3 by 3 is 9. That's 9 wavelengths. That's quite doable. Even 5 by 5 is doable. This is the electro-optic modulator and the dispersive delay in the detector, and this generates a signal at the sliding at the same baud rate as the input data. So the kernel size, as I say, tends to be very small. The input data size, on the other hand, can be arbitrarily, indefinitely large. It's just limited by your electronics, essentially, and we processed 250,000 pixel images. So the duplicated signals of the wavelength channels are all useful, so the output speed is equal to the input baud rate. So this summarizes our experiments for the convolutional accelerator processing images. So the kernels we used are quite standard, well-known processing kernels to extract certain features of the images here. The images were 250,000 pixels, so quite high size, more than enough to do sort of facial image recognition. The input data speed was 62.9 gigabaud. We had 90 wavelengths, microcomb lines. So this is broken down into 10 parallel kernels, if you like. Each kernel, 9 wavelengths, or 3 by 3, so 10 3 by 3 kernels. So the net computing speed of this, the vector processor, is 2 times 90 times 62.9, which is 11.3 teraops. Now, for the matrix, two-dimensional matrix calculations, we actually have to flatten the image into vectors, and this is a fundamental issue. It just requires an overhead, basically, and you lose this factor of 3 for a 3 by 3 kernel. There's no way around that. Well, there are ways around it, but basically by making the system in parallel. But it's a fundamental issue. So our speed for the image processing was almost 4 teraops per second. So this shows the schematic of the convolutional neural network. So the convolutional accelerator that I just presented was the first half of our experiments. The second half was to use that same hardware to form a convolutional neural network to do the decision making. So this network, this shows a schematic of it, basically consists of 3 parts: the optical convolution layer, the electrical layer, which we did, the pooling layer, which we did electrically in our case, although you can do this optically quite easily as well. And finally, the fully connected, the actual network itself, the guts of the network, the fully connected layer. So this corresponds to or involves 72 synapses with 10 neurons. So the convolutional layer greatly reduces the scale, the required scale of the optical neural network. So it's very efficient. So this shows some of the detail in the waveforms of the convolution accelerator part of the optical convolutional neural network. Just you know, some of the details, extracting the feature maps here to greatly reduce the requirements of the neural network. So the vector computing speed of this is actually was slower because our baud rate here was only 11 gigabaud. So it was, the vector speed was about 1.8 teraops, but still much faster than previous networks. This summarizes the testing of the convolutional neural network. I'm really glossing over a lot of work here. This is really tour de force, I guess, experiments. So we tested the recognition of all 10 digits, which is very rare. Only one or two other papers have ever done this optically. And using this famous NIST, modified NIST data set, which is also very rare for optical networks. We used 60,000 images for training and tested it on 500 images. Almost all of the neural networks, optical neural networks, used 50 images to benchmark the system. Our referees really put us through the ringer on this and made us do further experiments on 500 images. And this just shows a small segment of the feature maps that the convolutional front end extracted as part of the process to come up with the decisions. So this shows the confusion matrices, theoretical and experimental, showing an accuracy of 88%, close to the theoretical of 90%. This can easily be improved a lot by scaling the network to achieve accuracies comparable to electronics. So one of the questions, I guess, of this work is, does it scale, and what is the potential for increasing the speed and the size, the scale, and the power, and so on. So this shows one particular embodiment based on extending the wavelength range to the L and S band as well, so C, S, and L bands, generating about 400 wavelengths and 50 gigahertz spacing. And if you combine this with polarization multiplexing to get a factor of 2 and spatial multiplexing as well, you can get you can reach the peta-op regime with this technology. So there's a lot of room for scaling. And remember that this is for a single processor. So a lot of the Google, the TPU chips and so on that have 200 teraflop speeds are based on sort of 65,000 parallel processors. So it's quite a different approach. So this just shows a quick summary of the different wavelength bands that are available, and things really are evolving. I mean, I'm a telecom person myself, so used to the C and L band, but these days, even the S band, you can get wave shapers apparently for the S band and the extended L band as well. And the E bands opened up because of new water-free fiber and so on. So potentially there's quite a wide range. And remember, we're not doing long-distance transmission here. This is just very short reach as part of the system. So this is another example of a scaled network to give you more synapses and neurons for more complex tasks. So this is using the C, L, and S bands, which are very standard wavelength bands, to achieve up to 25,000 synapses, which is pretty much as you would want for most applications. So this is the conclusions for the neural network part of my talk. So this, we reported the first high-speed demonstration of neuromorphic processing based on Kerr microcombs. We achieved 11 teraops per second convolutional accelerator, and also a basically teraops regime optical convolutional neural network to do recognition of the full 10-digit data set. So this just shows some of our work in RF photonics using and high bandwidth applications using Kerr microcombs. This really started around 2014, I think. In our first conference paper, it was 2015, and this was the first application of combs to RF photonics. It was about the same time as a paper by Zhao Zhu from Andy Weiner's group, so we both got into this roughly the same time. And then we had these papers after that, and then the other big benchmark, I guess, was around the middle of 2018. We switched from using relatively incoherent, widely spaced 200 gigahertz combs to 49 gigahertz free spectral range soliton crystal combs, and this was a real game changer for us, and that's more or less what we've been using since then. And this shows some of our work in the last couple of years in microwave photonics. This shows my group and collaborators. This is Xinwen Xu, who's now back in China. He's got a professor position back there. Mengshi or Simtan has just graduated. Myself, Professor Arna Mitchell at RMIT, and Dr. Bill Corcoran from Monash University is driving the data communications work, and Dr. Jiayang Wu in my group. So thanks very much, everybody, for listening to my talk, and I hope everybody stays safe and healthy as this pandemic hopefully winds down. Thanks very much.
Thank you for that insightful talk, Professor David Mas. And now moving on to our next presentation by Dr. Jinhua Jiang, the Australian National University, Australia, and presenting on the title Second Harmonic Generation and Spontaneous Parametric Down Conversion in Dielectric Loaded Lithium Niobate Thin Film. So on behalf of Professor Jinhua, I'm going to play his video presentation.
Which I will present our recent work on enhanced second harmonic generation and the spontaneous parametric down conversion in lithium niobate non-local metal surface. Here is the outline. In the beginning, I will talk about the background and the motivation of have entangled photon source at the nanoscale. After that, I will present our approach by using lithium niobate non-local metal surface. Then I will show you that this metal surface can realize orders of magnitude enhanced nonlinear light-matter interaction, such as the second harmonic generation and the spontaneous parametric down conversion. Then the last part is the experimental demonstration of the special entanglement of the photon pairs from the SPDC. Firstly, let me give a brief introduction to the photon entanglement. When we see two photons are entangled, which means they are linked in a certain way, then no matter how far away apart they are in the space. Because of this, a measurement of one photon can automatically provide information about another entangled photon. Entanglement is an unique feature of quantum mechanics and actually is an essential resource for many quantum applications, such as in the secure quantum communication, quantum computing, and quantum imaging. So how do we create entangled photons? In quantum optics, the most common way is to use the nonlinear process called the spontaneous parametric down conversion, SPDC. In this process, a pump photon with high energy goes through a quadratic nonlinear crystal and splits into two photons with lower energy, one called singular photon, another called idle photon. In this process, the two generated photons should match the energy conservation and the momentum conservation. Because of this, these two photons are automatically entangled in the frequency and the spatial domain. By spatial design, the SPDC can also directly generate polarization entangled photon pairs. However, traditionally, the nonlinear crystals are bulky with thickness on the order of centimeters, and this is not suitable for the miniaturized quantum devices. One may think that we can reduce the thickness of the crystal, but the SPDC efficiency will drop as well. So the research question is how to realize ultra-thin SPDC source while remain high efficiency. To realize this goal, we use metal surfaces. What is metal surface? It is a two-dimensional arrangement of the nanoscale optical nanoresonators made by metallic or dielectric nanostructures, which can support localized plasma resonance or localized me resonance. When we put different nanostructures at different spatial positions, we can control the wavefront of light within sub-wavelength thickness and resolution. Metal surface is actually also a very promising platform for nanoscale nonlinear optics. This is because they can support strong nonlinear light-matter interaction because of the resonant enhancement of the field inside the nanostructures, And also this enhanced nonlinear frequency conversion can happen in all directions due to the relaxed phase matching condition. Especially, lithium niobate has been one of the most promising materials for making nonlinear matter surfaces. What makes lithium niobate so special is that it has low optical loss in the broadband, high quadratic nonlinear coefficient. Also, we have mature thin film techniques for lithium niobate, and it has low fluorescence. All these properties make lithium niobate a good material for nanophotonics of nonlinear process or the quantum SPDC process. Indeed, there are recent experimental works that demonstrated the lithium niobate matter surfaces for enhanced second harmonic generation or the SPDC process by exciting the localized mid-resonance inside the lithium niobate nanostructures. When I talk about localized resonance, it means that the resonance can happen within a single nanostructure. However, the problem of localized resonance is that it has low quality factor and the field enhancement. Therefore, the nonlinear enhancement is also limited. For example, in this work, the SHG actually is enhanced by only 2 times compared to the thin film without nanostructure. In this work, the SPDC was enhanced by 20 times. And another problem of this design is that they all need the nanofabrication for lithium niobate. This process can damage the edge of the lithium niobate material and reduce the nonlinear coefficient. As I will show you later, how do we solve these 2 problems at the same time in this work? To enhance to increase the quality factor, we will use local matter surfaces. This is the recent work published in Nature Nanotechnology. They proposed a local matter surface, which includes a very thin 3 nanometer thick silicon 1G grating on top of silicon nitride thin film. The reason we call it local matter surface is this structure can support guided mode resonance by exciting the extended slab waveguide mode inside the silicon nitride layer, and because of the because this waveguide is mode can extend it to a large area, so we call it local. Also, because this waveguide mode has low radiation loss, this local matter surface can support very high quality factor. For example, they demonstrate the quality factor more than 1,000 in experiment. At the same time, the field enhancement is more than 1,000 inside the silicon nitride layer at the resonance. So these properties makes local matter surface a better platform for nanoscale nonlinear optics. Indeed, two recent theoretical works from our group showed that local 3.5 semiconductor matter surfaces can further enhance the SPDC process by 3 orders of magnitude. However, until now, there is no experimental demonstration on this idea, especially on the lithium niobate. In this work, our approach is to create local matter surfaces based on the lithium niobate on insulate platform. This is the design structure, which has silicon dioxide 1G grating on top of the lithium niobate thin film. In the design, the grating and the input polarization are all along the optical axis of the lithium niobate, so we can make use of the largest nonlinear coefficient of lithium niobate. Similar to the previous design, this structure can support non-localized guided mode resonance when the input wave number from the grating and the incident plane wave equals to the wave number of the waveguide mode. In our design, the thickness of the lithium niobate is around 300 nanometers. Another novelty of this design is that we don't need the nanofabrication of the lithium niobate layer. And this figure shows the simulated transmission spectra of the structure at normal incidence and a small angle for 1 degree for an optimized design. At the normal incidence, there's a transmission dip, which indicate the optical resonance at 1570 nanometers. With a small angle, there are 2 optical resonances. And eigenfrequency study tells us that this structure supports 2 optical resonance mode, and they are both angular dependent and local resonance. The interesting part is that these resonances have quality factors more than 500, and the field enhancement inside the least niobate layer is more than 600 at resonance. So both these 2 parameters are 1 order of magnitude than the reported values from the localized least niobate metasurface. After that, we simulated the enhanced sound frequency generation process. We consider a special case here. There's a singular beam input from the top with input transverse wave number of 0.21 radius per micrometers, and there's another idler beam input from another side, symmetrically from another side. This direction, because of the symmetry of this structure, both the singular and idler beam will have the same optical resonance happens at 1568 nanometers, which is this black dashed line, and this double resonances will contribute enhanced nonlinear current at the pump wavelength of 784 nanometers, which is at the normal output direction, and also the SFG will be enhanced. So from the simulation, we can see that the SFG efficiency in the metasurface is enhanced by 22,000 times when compared with the thin film without the top graded. Here, the SFG efficiency is defined by the output SFG intensity divided by the product of the incident singular and idler intensities. So now, after the SFG, how about the SPDC? Because SPDC is a quantum process and it's a spontaneous process, it's very hard to simulate directly. Fortunately, we can predict the SPDC process by the SFG efficiency based on the quantum classical correspondence theory, because SPDC is the reverse process of the SFG. So its efficiency is related to the SFG efficiency by a constant. Therefore, the SPDC will also be enhanced at the same frequency and the same output angle because of the correspondence. The beauty of the non-local metasurface is that it has angular dependent optical resonance, and because of that, we have the flexibility to realize enhanced SPDC for a broad range of angles and wavelengths by simply tuning the pump wavelengths. However, different from SFG, SPDC is as I mentioned, it's a quantum process. It's spontaneously. It can happen for all the singular and idler photons that match the energy and the momentum conservations. So because of this, in order to completely simulate the SPDC process, we have to simulate the SFG process in all the directions and all the wavelength combinations, which is very time consuming. So in order to solve this problem, we developed a coupled mode theory to model the linear and the nonlinear properties of the metasurface. In this temporal coupling equation, the A is the vector representing the amplitude of all modes. The capital lambda is the coupling matrix. So the eigenvalue of this coupling matrix will be the complex resonance frequency, and the eigenvectors of this coupling matrix will relate to the amplitude of the mode. After fitting some parameters of this matrix, we can calculate the resonance frequencies from the coupled mode theory, which is this 2 black dashed line of the 2 mode. They can perfectly match the direct simulation, which is the solid lines. Based on this theory, we can also calculate the SFG efficiency by this equation. And after fitting these parameters, we can calculate the SFG efficiency as a function of the signal wavelengths, which also perfectly matched the direct simulation. So now we can quickly and accurately simulate the SPDC process in all the output angles and all the different wavelengths. For example, here shows the emission pattern when the 2 times of the pump wavelength is tuned to 1568 nanometers, which is this black dashed line, and we obtained a spatial brightness enhancement for more than 1,000 times. Then we can also obtain the emission spectra for different pump wavelengths, and we obtain the spectral brightness around 1,400 times. Then by integration over both the output angle and the singular wavelengths, we can obtain the total SPDC rate as a function of the pump wavelengths here. You can see that there is a peak value around 16 Hertz per milliwatt. It is 68 nanometers, and below this wavelength, the rate is almost flat. In order to match the experimental condition, we also did a simulation for a pump with a Gaussian pump with a radius of 100 microns. With this Gaussian pump, the SPDC rate is slightly reduced compared to the perfect plane wave pump. After the design, we fabricated the metal surface by the e-beam lithography, and here is the SEM image of the fabricated metal surface. We fabricate a large area, which is 400 by 400 microns. The linear measurement shows that this metal surface has the optical resonance near 1570 nanometers, and the quality factor is more than 450. So, which is close to our simulation. This confirms the high quality of the fabrication. In another broadband lamp measurement, we also confirmed the angular dispersion of the fabricated metal surface. After the linear measurement, we did the SHG experiment by using the setup shown in this figure. The laser source is a femtosync laser, which has central wavelength is tunable around 1570 nanometers, and the bandwidth of the pulse is 23 nanometers. Here shows the measured SHG spectrum for the metal surface and also the result for the unpatterned film. With this, we obtained a 50 times enhancement over the unpatterned film when the center wavelength of the pulse is sitting in within the resonance. This enhancement is lower than the previous simulation. This is because the bandwidth of the pulse is larger than the bandwidth of the optical resonance. So anyway, so this result confirms the enhanced nonlinear wave mixing due to the non-local resonance. So then next, we also did the quantum SPDC measurement by using the Hanbury broad trace setup shown in this figure. Here we use the continuous wave laser source, which is tunable near 785 nanometers. And the beam diameter of the pump is 100 micron. We use the generated photon pairs after the metal surface was connected by a fiber coupler, and their coincidence was analyzed by a 50-50 beam splitter and two single photon detectors. This figure shows the two photon coincidence for different delays between the two detectors, and the blue is for the metal surface, while the gray is for the unpatterned film. In this result, we obtained 450 times enhancement when the 2 times of the pump within the optical resonance. And in the experiment, which is this dot with error bars, the result is there's a blue shift of the peak compared to the transmission dip, which is consistent with our simulation from this red line. And in this result, we obtained the coincidence to accidental ratio is more than 5,000. So both the rate enhancement and the car value are 1 order of magnitude larger than the previous result obtained from the localized metal surface. After that, we obtained the rate is around 1.8 Hertz for 85 milliwatt of pump, and we also confirmed that the generated photon pairs are pure polarized along the optical axis of the lithium niobate. To confirm the spatial entanglement, we did another experiment by adding the square aperture after the matter surface and measured the two photon coincidence when moving the aperture transversely. The size of the aperture is L, which is larger than the emission beam. We define the position of the aperture as YA. When YA equals minus 0.5 L or 0.5 L, half of the beam is blocked. When YA equals 0, there is no beam blocking. So this figure shows the two photon coincidence as a function of the position of the aperture, which we can estimate the beam size is around 2.5 millimeters. Most importantly, when the beam is blocked by half, the coincidence is dropped by 13 times in the measurement, which is larger than the classical limit. So this result confirmed the spatial entanglement and the quantum behavior of the generated photon pairs. To conclude, we have proposed and demonstrated a non-local lithium niobate matter surface for enhanced SHG and SPDC, and to generate photon pairs with the spatial entanglement and the enhancement by 450 times. This will show a pathway towards lower type of matter optical devices in applications in quantum imaging. We recently uploaded this paper to arXiv. If you want to know more details, please read this arXiv paper or ask me any questions. Thank you very much for your attention.
Thank you for that insightful talk, Dr. Jinhua. Now the stage is open for questions. Hello, Dr. Jinhua, can you hear me?
Yeah. Hi. Yeah, I can hear you. Can you hear me?
Doctor, thank you for that insightful talk. Now the stage is open for questions, Doctor. Okay, Doctor, I assume that you have no questions from the speakers. Once again, I thank you for being a part of this webinar and hope to associate with you in your future events as well, Doctor. Thank you, Dr. Jinhua.
No worries, thank you.
Now moving on to our next presentation by Dr. Ang Yu, Jian Jiaotong University, China, presenting on the title 3D Human Joints Extraction and Application Choosing Infrared Time of Flight Depth Camera. Hello, Dr. Ang Yu. You can start the presentation now.
Okay.
Thank you, Doctor.
Hello, everyone. Good morning. The topic of my presentation is 3D human joints extraction and applications using infrared time of flight depth camera. The outline mainly contains the 4 parts as following. First, I introduce the background of this research. Human joint estimation has already played a vital role in some frontier applications, such as computer vision, multimedia communication, medical image, automatic drive, epidemic prevention and control, and augmented reality. However, human joint detection on RGB image has some difficulties. Complex backgrounds, lighting conditions, occlusion and self-occlusion are easy to affect the extraction accuracy. Recent advent of low-cost depth sensors provides an alternative solution to extract human joints. According to the ranging principle, we divide the depth sensors into 3 categories: binocular stereo vision, time of flight, and structured light technologies. The 3D information obtained by depth camera can be expressed in different forms, such as the depth image, point cloud, voxel length, and so on. Compared with the other data, point cloud intuitively provides a true 3D display of the detected object and can automatically determine the actual proportion of the object. Besides, point cloud can provide geometric and photometric information for subsequent processing. For 3D human joints estimation, the work can be classified into 3 methods: template-based method, feature-based method, and machine learning-based method. A template-based method needs to build the human template, and the search process is time-consuming. In feature-based method, geodesic distance is often used to find the 5 human joints. Machine learning-based method requires a lot of training data, and the process of hand-labeled is time-consuming. In our proposed method, the 2 methods are proposed to extract 3D human joints. In the first work, we mainly use the geometric features. The proposed approach consists of 3 stages: data acquisition, data pre-processing, and joint estimation. In order to evaluate our algorithm, we build a data set containing 4 classical poses in advance. In our data set, we capture 4 main poses: upright, raising hands, parallel arms, and akimbo of 10 people, which contains 1,200 frames depth images with a time-of-flight camera. While maintaining a pose, the knees have 2 forms, upright and bent respectively. We record 5 times for every pose. Each time subject remains in the same position. When a group of poses is finished, each subject puts on different clothes and repeats the previous pose. Each person changes 3 types of clothes. In data pre-processing, due to the huge amount of point cloud acquired by the instrument, not all points are useful for joint extraction. We first segment the human body from the hosting point cloud as a global feature. Silhouette is used to save computing cost. When the viewpoint of the camera is not aligned with the direction of the human body being facing, it will cause partial occlusion, which increases the difficulty of recognition. So the point cloud along the positive direction of the y-axis is projected to obtain a top view. The farthest 2 points on the axis are picked out in the top view. The straight line is determined between the 2 points of the projected point cloud. Then it's simple to compute the angle gamma between the x-axis and the straight line. Then we first extract the hand and feet point hand and feet joints. According to the threshold of body proportion. The hand is segmented to get the centroid point. Meanwhile, left or right feet can be obtained using the same method for subsequent processing. The extraction process of joints is also slightly different for different poses. In order to solve the problem of pose classification, we compute an angle alpha, which is the angle between the hand and the farthest points on the positive and negative x-axis of the point cloud. When alpha is equal or less than 90 degrees, it represents upright or akimbo pose. When alpha is greater than 90 degrees, it belongs to raising hands or parallel arms pose. Next, in the upright and akimbo poses, the length ratio is used as a basis for further judgment. In the raising hands and the parallel arms poses, the aspect ratio is calculated for detailed classification of the two poses. When we calculate the waist joints, the central line can be first obtained, then the projected point can be divided into two parts, the left waist and the right waist. To find the waist joint, we traverse the points in the left and the right waist, respectively, to compute the distance from the central line. The joint which has the minimum distance is the waist joint. Starting with the waist, we can easily find the left or right shoulders by extending the vertical lines from waist along the negative y-axis. To get the intersection with represented by delta yk. When the ratio of delta dk and delta yk is less than the threshold value, the needs are in the upright state. Otherwise, they are in the bend state. The results of extracting 3D joints from G3D dataset and our dataset. The first column is the extracted silhouette from the raw point cloud. The second column is the joint map extracted by the algorithm from the silhouette. The third column is the extracted joints displayed on the raw point cloud. And the fourth column is the hand-labeled joint map. We quantify average distance error as the evaluation criteria per joint. Because of loose fitting clauses, the extraction of the waist on the silhouette has a large deviation. When in the upright pose, the waist indirectly affected the detection of knees and hands, and the process of automatic correction can be further included in the next work. The average distance error is less than 5.8 centimeter. The second work is 3D human joints estimation using part segmentation. In our proposed method, PointNet++ model is first applied to human part segmentation. The dataset is built by ourselves to train the network, and 6 human parts are obtained, including hand, neck, arm, trunk, leg, and feet. These parts are further processed in the next stage to estimate human joints in different poses. The public available 3D human segmentation dataset is not as abundant as the 2D dataset, so we built the human part segmentation dataset. The human point clouds in our dataset come from the public G3D dataset and the in-house captured dataset. Our human point clouds from the 2 datasets are input to the cloud compare software for segmentation and the manual annotation. After obtaining 6 parts of the human body, each part is numbered with 1 to 6 and is stored in a TXT field together with the coordinate. To increase the feature dimension, the normal vector of each point is also computed and saved in the text field. The segmentation results are shown in the right figure. In table 1, we compare the MIOE of the other part segmentation methods. Although the accuracy of the human segmentation is slightly lower than some works in table 1. It is within a reasonable range. The ShapeNet part dataset mainly contains point clouds of different static objects, such as tables, lamps, at the central. Compared with the parts of the human body, the features of static objects are relatively obvious, and they can be regarded as regular geometric shape. The human point clouds used in the synthetic human dataset are synthesized by the software. The first FCN model explored the result of human part segmentation under occlusion, and the method may not be suitable for the other scenarios. Moreover, the FCN model is not as robust as .NET++ in acquiring spatial features. Therefore, the method proposed here is relatively innovative to certain extent. In order to ensure the joints closer to the real presence of the human body, the human joints are divided into the active joints and the inert joints. The former represents more flexible part, including elbow, hand, and knee joints, which need to be located on the thinner side of the human arms and legs. Inner joints only need to be extracted using simple geometric features. First, we take the elbow joint estimation as the example. The silhouette of arm point cloud is calculated in advance to save computing cost. The bounding box of 3D arm silhouette is first calculated to roughly charge the long axis direction. When the direction is determined, arm silhouette needs to be rotated twice on different projection planes to make the elbow joint in the vertical direction. Then the piecewise linear function is applied to separate the inner and outer silhouettes of the rotated arm point cloud. The points in the total arm silhouette above the piecewise linear function belong to the inner silhouette, and the rest of the points belong to the outer silhouette. According to the spatial character Sizes to be measured in this work include multiple vertical heights and horizontal widths of the human body. For vertical heights, such as shoulder height, waist height, knee height, and armpit height, length calculation only needs to calculate the distance between related joint points. For the measurement of the jerseys, we mainly measure the human waist or chest sizes. First, we segment the 3 areas by using the obtained joints. The related parts of multi-frame point cloud are projected to the XZ plane. The corresponding discrete points of the projected point cloud are extracted, and these points are further utilized to calculate the circumference by ellipse fitting. The measurement results of the jersey are mainly related to 3 parameters. One is the segmentation length of the jersey area and the number of discrete points involved in the ellipse fitting. Third parameter is the frame of the point cloud. In order to avoid the influence of the first 2 parameters on the result, we use cross-validation method to find the optimal solution. The segmentation length is selected as 5% and 10% of the normalized height. The number of discrete points is controlled between 10 and 50, and a parameter is selected for each interval of 5 numbers to calculate just circumference. When the appropriate parameters are selected, the measurement error of waist jersey based on 3 frame point cloud research point cloud reach the lower value, and the measurement error of hip and chest jersey based on 2 frame point cloud reach a lower value. The obtained size results are further verified with manually measured sizes. The average error of human size measurement based on joints is less than 4.1 centimeter. Finally, we summarize the above work. We proposed 2 new methods to locate the positions of human joints. First work, we have proposed a geometric method to extract 3D joints from a single frame point cloud of human body. We test the estimation joints in the in-house captured dataset and the public G3D dataset. It has high accuracy, and the average distance error is less than 5.8 centimeter. In second work, 0.9++ model is first applied to human part segmentation. Each human part obtained by the network is then processed with mathematical analysis methods to obtain the relevant joint. The result shows that the average distance error of 14 human joints is less than 4.2 centimeter. Besides, we also investigate human size measurement. Compared with manual measurement data, the size error is less than 4.1 centimeter. The above is my presentation. If you have any questions, please contact me by email. Thanks.
Thank you for that insightful presentation, Dr. Angvi. Now the stage is open for questions. Okay, Dr. Yangi, I assume that you have no questions from the speakers. Once again, I thank you for being part of this webinar and hope to associate with you in your future events as well. Thank you, Doctor. Now moving on to our next presentation by Dr. Xiao He, University of Electronic Science and Technology of China, and presenting on the title by Fast Infrared Beam Streaming based on Reconfigurable Meta Surfaces. On behalf of Dr. Xiao He, I am going to play his presentation.
Good morning, ladies and gentlemen. My name is He, and I'm a student of Professor Shao He. I come from the University of Electronic Science and Technology of China. It is a pleasure to be here with you today. Today's topic of my presentation is about fast infrared.
Hello.
Hello.
Can you hear my voice very clear?
Okay, Doctor. Please share it in full screen mode.
Shall I begin my presentation now?
Okay, Doctor.
Good morning, ladies and gentlemen. My name is He, and I'm a student of Professor Shao He. I come from the University of Electronic Science and Technology of China. It is a pleasure to be here with you today. Today's topic of my presentation is fast infrared beam steering based on reconfigurable metal surfaces. The content of today's topic will be in 6 parts, which include background, working principles, numeric simulations, fabrication, experimental results. And finally, I will give you a conclusion of my presentation. Now let's begin with the background information of the metal surface. Metal surface is a 2-dimensional artificial dispersion material, which can modulate the phase, amplitude, and polarization of the light, where the phase modulation function has been widely applied on the wavefront control, where it can be described by the general Snell's law. The phase modulation by metal surface have been applied in areas such as the deflector, hologram, flat lens, and optical vertex beam generator. And the metal surfaces can also be applied to implement beam steering. However, they're based on the traditional paradigm, the same as the geometry optics. Here I want to show some traditional ways to achieve dynamic beam steering. And the first one here is the optical phase array. It has a large field of view. However, it makes the control system to be very complex because it needs to control pixel by pixel. And the second one here is the microglometer array. Because it uses MEMS technology, so it has very fast modulation speed, but it still have a limited field of view. And the third one is a macro lens array. It also faces the problem, have a limited field of view. There are many work have been done, have been demonstrated based on the metal surface beam steering device. First shown in the left figure is using a metal surface lens array to imply fast 2-dimensional beam steering.
It is based on the traditional paradigm, which is the geometry optics, which has widely been applied in LiDAR. And this design has very limited field of view. And in the second type, they designed metal surface LSMs. The metal surface can function as the specialized modulations to have beam steering functionality. However, the devices are all limited by the current paradigm of SLMs. On the design of the beam steering devices. So it has very complex control system. And even so, molecule cannot change unit cell by unit cell. They are tuned molecule group by group. So only one direction of beam steering is achieved. So our design focuses on two aspects. First thing is that we want to demolish a fast beam steering functionality. And the second thing is that we want a very simple control system compared with the others. So we are thinking about the output wavefront is 2 degrees of freedom. So a control system with 2 degrees of freedom would be good enough for this, which have already been proved by the geometry optics device. But this time we use the metal surfaces. And in our design, we need to convert the arbitrary wavefront to a reconfigurable wavefront at first. And what does the reconfigurable wavefront means? Because in our design, we only have 2 degrees of freedom. That means the arbitrary wavefront cannot be controlled using just a kind of this kind of control system. It is not like the FMs, which can accept any wavefront. So we need to transfer the arbitrary wavefront to be a reconfigurable wavefront by the metal surface A. And then we use a movable metal surface as a tuner. This metal surface can tune the wavefront to be our desired wavefront, which is the planar wavefront. And it is tunable on the directions. This is the phase function design procedure of the metal surfaces. Basically, our design is inversely design of the wavefront because we need to know the phase distribution of these 2 metal surfaces. So it is similar to the inverse method for our designed front output part. We know it's a planar wave. Then we want to know what kind of wavefront can be controlled by 2 degrees of freedom system. So that the phase distribution of the tuner, which is the metal surface B, can be decided. Then for the evolution of the reconfigurable wavefront from metal surface A to metal surface B, it's connected by the Rayleigh Snowfield refraction formula. So we can reversely derive the wavefront coming out from the metal surface A. Since incident wavefront is known, then we can use 2 wavefronts to determine the phase distribution on the metal surface A. In this way, the phase distribution on both metal surfaces can be decided so that we can design our metal surface deflector. Here I want to show some memory simulation results. First is our unit cell simulation results. Figure on the left is the structure of unit cell, and our unit cell is designed in a cylinder shape. And the right side figure is the simulation results. And you can see the unit cell can cover the 2 pi phase shifts, and the transmittance of the unit cell is basically above 60%. Then I have to show you the simulation result of the wavefront. And the GIF on the left side shows that as I move the metal surface B, which is a tuner metal surface, the beam will scan from continuously scan from minus 70 degree to positive 70 degree, and the output wavefront keeps flat. And the right side figure is the far field light intensity distribution on the different displacement of the metal surface B. And you can see the maximum light intensity satisfy a cosine value of the deflection angle. And here I want to introduce the fabrication process and the fabrication result of our metal surfaces. The fabrication process of our metal surfaces still follow the traditional lithograph process, and it is shown in the flowchart below. Firstly, the substrate is preprocessing with HDMS to enhance the adhesion of photoresist, and before the gluing and the pre-baking. Then the photoresist is exposure with UV light to transfer the pattern from mask. And after developing and post-beam baking, we examine the face through the microscope. And finally, we fabricate the sample by etching. And here is our fabrication result. In the first figure, it is our photograph of the metal surface. And you can see there are many different colors on the metal surfaces. That is because the diffraction of the visible light. And the second figure and the third figure are the top view of metal surface A and metal surface B, respectively. And both of them have a good fabrication quality. And here we also test the cross-section of the metal surfaces, and we found the depth is uniform. And also there is a little bit rest on the bottom side of the cylinder, which is very difficult to avoid in the fabrication processes. And here I want to introduce our experimental results. This is a light path setup of our experiment. And the incident light is coming out from a carbon dioxide laser. And then it passes through a pinhole. And this pinhole is used for regulate the beam path, which is widely open during the test process. And our metal surface are sitting on the translation stage. One of the metal surface is fixed, and another will move. The requirement of our experiment is very strict because both of the metal surface should perpendicular to the direction of the beam. So how to design this one? We use two calibration light paths. One light path is used for calibrating the first metal surface here, and the second one is used for calibrating the second metal surface. And this metal surface needs to turn during the experiment. So we are monitoring the light from the calibration light path 2. During the turning process, the light path should not move. If it moves, it means that the displacement direction is not perpendicular to the beam direction. And finally, by doing so, we can make sure the metal surfaces are perpendicular to the beam direction. And finally, the diffraction beam is detected by the beam analyzer, which is on a circular track. So we can measure the deflection angle from -65 degrees to positive 65 degrees. And actually, our design can reach 70 degrees, but the track has a limited moving range, so we can only measure this one. And here is our experimental result. The figure on the upper side is the cross-section of our deflection beam. And here figure on the left side, it is the experimental result of the evolution angle testing. And we can see that as we are moving the Turner metal surface, which is the metal surface B, it can cover the evolution angle from 0 degree to -65.6 degree. And because And because this testing results only show the beam steering on one direction, so we'll provide a video for the omnidirectional direction of the omnidirectional of the beam steering. The beam steering is controlled by the displacement of the metal surface B. As we are moving the metal surface B, the deflection beam, which is shown as a blue spot here, will be straight to different positions, where we can say it covers the field of view for around 130 degree multiplies 130 degree. Here is come to our experimental result of the deflection angle. And you can see in the first figure, the theta here means the evolution angle. And this figure means the evolution angle of the deflection beam related to the displacement of the metal surface B. And in the second figure, there the phi means the azimuth angle of the deflection beam. And this figure means the azimuth angle related to the displacement direction of the metal surface B. And here we can see the experiments are basically agreeing with the theoretical design. And here is the experimental result of our modulation speed. The first figure here is the setup of our beam deflection rate test. We replace the translation stage of the metal surfaces to a piezoelectric ceramic. And the beam polyphore changed to a point deflector. And the received light power can be shown in the oscilloscope. So we can collect the experimental data. And the figure on the right side is our experimental result. And the right line here is a voltage that applied on the piezoelectric ceramic. And the blue line means the intensity of the light deflection beam, which is received by the deflector. And from this experiment, we found the modulation speed of modulation frequency of our metal surfaces can reach 6 kilohertz. And we also demonstrate a very funny functionality of this steering device. With this for we have a laser which is very powerful, so it can show something like the balloon. We also use the electro control translator to control the metal surface B, so that the shooting position can be programmed by our computer. So we programmed this one to make our beam steering device only shoot the blue balloons. Finally, I want to give a conclusion of my presentation today. Based on our design, our metal surface deflector can achieve a faster beam deflection and with a large field of view. Our field of view can exceed 130 degree multiplies 130 degree, and the modulation frequency can reach 6 kilohertz, and the control system of it is much simpler than the OPA or the SMs. And the figure below here, below is the contrast between the metal surface and the traditional lens. And the metal surface have such advantage over the traditional lens. Thank you very much for your patience.
Thank you for that insightful talk, Dr. Shaovi. Now the stage is open for questions. Okay, Dr. Shaovi, I assume that you have no questions from the speakers. Once again, I thank you for being a part of this webinar and hope to associate with you in our future events as well. Thank you, Doctor.
Sorry, I cannot hear it very clear.
Okay, Doctor, I assume that you have no questions from the speakers. Once again, I thank you for being a part of this webinar and hope to associate with you in our future events as well. Thank you, Doctor. Hello, Doctor, can you hear me?
Or can you repeat that again?
Sorry, Doctor. Hello, Doctor. Thank you for your presentation.
Sorry, can you repeat that again? Because I cannot hear it very clear.
Now, can you hear me?
Yeah.
Okay. Okay, Doctor. Thank you for your insightful talk. And we'll moving on to our next presentation by Dr. Chao Xin, Fudan University, China, and presenting on the title Emerging Optoelectronic Devices for 6G Wireless Optical Links. Hello, Doctor. You can start your presentation now.
Great, wonderful. Thank you.
Thank
you.
you.
I hope everyone can see my screen and can hear me clearly.
Yes, yes.
Okay, so first, good morning, good afternoon, and good evening. My name is Chao Shen. I'm now with the School of Information Science and Technology at Fudan University in Shanghai. So it's my great honor today to deliver this talk on the emerging optoelectronic devices for 6G wireless optical links. The talk of today will be including the following parts. So I will first give an introduction motivation on why we started the optical devices and the opportunities for wireless data link, especially those based on optical components in the beyond 5G and 6G networks. Then I will focus on the current trends in the development and the demonstrations of light-fi, the light fidelity technology, the visible light communication technology, and those in underwater, which namely the underwater wireless optical communication or the UWOC technology. Yeah, since today's talk will be focused on the device and physical layer technology, so I will discuss in detail about the transmitter technology, including those light sources like LEDs, the micro LEDs, nanowires, the superluminescent diodes, and the laser diodes. The second part will be the receiver technology, including the comparison of different kinds of detector, such as PMT, the tube, the semiconductor photodetector, the avalanche photodetector, the micro photodetector, etc. Then we will have a brief discussion on the other important devices in optical communication, such as the modulators, amplifiers, and how to integrate them together to make photonic integrated circuit. Yeah, the presentation will be concluded with a summary and outlook. Actually, the opportunity for visible light communication or optical wireless communication, OWC, is quite aberrant. That we are talking about 5G technology today. So the requirement for 5G and beyond 5G means more and more data and more devices connected, and you need lower and lower latency, and the data rate and the battery life will be increased by 10 to 100 times compared with the previous generation of wireless communication. It's also worth noticing that the current mobile network will cover those metro area, but it's not able to cover other parts of the world, for example, underwater and underground. And that's why Nokia's future network aims to go all the way, including to cover those underground network and underwater IoT network. So in this case, optical wireless communication came into the picture that will help to address those challenges. For example, can help to increase the mobile data traffic by orders of magnitude. And to be more specific, there are many important applications like smart cities, VR, and AR displays. They all require very large communication bandwidth. Yeah. And the smart traffic, for example, is one of the driving force for those optical wireless communication in smart cities. And for AR, VR, and XR, the video streaming requires like few hundreds megabits per second data rate for single user or for single device with a latency required smaller than 1 millisecond. And those provides a huge pressure to the current Wi-Fi system, which means we need to looking for a different opportunity for next generation wireless communication or data link. And apart from that, Berkeley mentioned that there's no internet in underwater. The human activity in underwater or in ocean is significantly limited by the lack of communication technology. So we can find a lot of resources in the subsea environment, but the wireless data link becomes the missing component. So for example, the current acoustic can reach a quite long distance, but the data rate is limited to a few tens of kilobits per second. You can only send a very simple text message, but you cannot even send an image, let alone videos. But the conventional RF technology, due to the huge attenuation in water media, the transmission distance is quite limited. Then there's a huge empty space that need to be filled. And here, the optical wireless communication came into the picture that will bridge the gap, the technology gap for underwater IoT network. So if you're looking beyond the different technologies, we can see that optical wireless communication will do have their advantage to achieve high data rate utilizing unlicensed band that will help to release or to partially relieve the congested electromagnetic spectrum. Because you know, in current 5G deployments, the carrier will need to spend quite huge amount of funding or money to bid for the spectrum they can use. But for optical, especially those visible and infrared color regime, that is not regulated band. So if you look at the entire spectrum, so actually we can move apart from radio and microwave band into the optical band, including using infrared to build those free space optical communication or FSO link. We can use visible light to build VLC and the light valley. We can also use UV to build those UV solid band communication or non-line of sight communication link. Yeah. One of the driving force to use visible is like you have so many LEDs or lighting systems around the cities that you can integrate those communication functionality with the lighting system. But definitely those OWC, optical wireless communication, will not replace the conventional RF and microwave. I believe those technologies, they are complementary with each other and will coexist. So if you look at the global research activity on visible light communication only, as you can see, currently there are over 10,000 journal papers published, and you can see a rapid growth since 2014. So this has become one of the rapidly growing research topic in communication field. And if you look at the global interest, you can see that both Asian countries like China, Japan, Korea, and India, they invest quite a lot, and also European countries like UK and the rest of the EU countries, they also have a lot of research work, and the US as well, and Australia, Canada, they all have the researchers working on the visible light communication. So this has become a global interest. If you look at what are the key components or key device used in visible light communication, the lasers actually is become showing growing interest compared with LEDs. And if you look at the research work published, and you can see there are more and more laser related, the VLC system demonstrated or investigated. And if you look at the underwater, so actually compared with the free space related work, underwater is relatively a small community, but you can see there are still very rapidly growing research on underwater communication devices and systems. But the conference, due to the global pandemic, the conference activities has become quite affected in the past 2 years. But you can see the journal papers is still a rapidly growing trend. And now if you look at the device technology, what are the key enabling device for those VLC system or OWC system? Thanks to the three great scientists to invent this blue LEDs that will enable those white lighting, and also those light emitting diodes become a very, very promising device to directly be modulated and transmit data. It has become very, very low cost today to buy or to purchase those LEDs. The advantages of LEDs definitely is long lifetime, that you can use like the device for tens of thousands of hours without replacing it. And the device is very compact, which means that the feature size of the such device can be reduced from centimeter to millimeter, even to micron level. But it is a very good device for lighting. However, if you look at the communication functionalities, people always want to go for high data, high speed. But the LED, the bandwidth, especially those nitride-based LED, the blue and green color regime, is quite limited. And also there's another problem. It's called efficiency droop, which means if you want to go for high power, especially for outdoor applications, you always want to have high brightness light source that can allow both large area illumination as well as to support long range, long distance data communication. The efficiency droop become an issue because that will reduce the power efficiency for such device or for such system. And recently, the micro LED or mini LED become a very hot topic. That the major driving force, of course, is from the display part, the display business, that people want to make high efficient, high density, high brightness displays. But we also found that the micro LED also shows unique properties for communication performance, that they can help to address the potential bandwidth limit. Why? It is because with the reducing the feature size of the LEDs, you have both a reduced RC time constant. Also, it will help reduce the internal polarization field due to the strain relief, the strain relaxation. That will also help to improve the bandwidth with a smaller LED feature size. Yeah. And recently, by using PAM4 and the DC OFDM modulation technology at data rates about 3.5 gigabits per second and 5 gigabits per second has been reported by using those micro LEDs. Yeah. Is it possible to further reduce the feature size? I mean, from micro to nano, and this is possible by building those nanowire LEDs. Yeah. This is a part of work we did at COUT between 2015 to 2018. That we tried to use those nanowire structure to build high efficient and high performance LEDs. And you may know that the heat generation is not an ideal thing for all kinds of devices, semiconductor devices. That's why if we want to use a metal substrate, that will help. I mean, it will become a nature heat sink that will help to improve the thermal performance of such device. And it also supports the material serve as the electrical contact and a light reflector to improve the light extraction efficiency for such devices. And with this case, we can build the nanowire LED. And the unique things for nanowire LED is that you can quite easily engineer the band gap of such device. On the other hand, it means you can engineer the emission wavelengths. Yeah, for example, we can build UV nano LEDs, blue, green, cyan, yellow, and red nano LEDs. Yeah. And the most important thing is that you can build them together to make into a white LED without using phosphor. Yeah. I've also started the modulation bandwidth of such device, which also shows quite interesting performance. But compared with LEDs, yeah, lasers are quite typically used in the fiber communication system. And we mentioned that the droop become a problem for high brightness devices, and nano, mini, and the micro LEDs also have suffering from limited power, optical power. So, is there any other devices that can be used for building those optical communication systems? The answer is yeah, we can use the lasers. So beyond LEDs, use lasers, you can significantly improve the modulation bandwidth of such device. Like for LEDs, even with equalizer or other technologies, the bandwidth is only a few tens or even 100 megahertz. But for lasers, you can directly increase to gigahertz or beyond gigahertz modulation bandwidth. That will help to improve the system performance. But lasers, some people may have concerns about safety. Yeah, that's why we developed another technology called super-luminescent diodes. So here I compare the properties and performance of 3 different kinds of devices: light emitting diode LED, SLDs, and lasers. Yeah. SLD is based on amplified spontaneous emission or ASE mode. Laser is on the stimulated emission mode. So as you can see, the SLDs also is free of efficiency droop and also have a very good bandwidth. So this is old data in 2016. Actually, now we already go beyond 1.2 gigahertz bandwidth for SLDs. For lasers, is it possible to further improve the modulation bandwidth? Because we all know that the nitride-based lasers nowadays they are intentionally designed for 2 applications. One is for the Blu-ray optical storage, the DVD, and the second is developed for the high power metal processing, like the big laser machine. So none of them are optimized for communication purposes, which means the bandwidth or the modulation performance of such laser diodes is orders of magnitude lower than the very, very matured infrared, like indium phosphide and gallium arsenide based devices. So in this case, we developed those, high speed structure. One of the approach is to use the DLB, the distributed feedback gratings. Like the advantage is like for IP lasers, usually become a molecular mode, and at high modulation, you don't want those mode hopping or that will introduce those nonlinear effect in the RF or high-speed operation of the laser diodes. And by use those DLB grating. So this work we did with this is the 10th order, high order DLB grating using using FIB to directly write on the waveguide. And then you can see that we can engineer the emission spectrum to make the laser from a multi-mode to a single mode. And this is for blue color. We can also do the same thing for green color devices. Like here, it shows the DLB lasers in the green and blue color regime. And such device can support high-speed data communication that can reach the beyond 10 gigabits per second data rate using the 16-QAM OFDM modulation technology. So this confirms that yes, by using the developed DLB lasers, we can achieve really high-speed communication. So apart from the conventional FP lasers, very important, we also have those VCSELs, the vertical cavity surface emitting lasers. The VCSELs actually will have even higher speed, although the fabrication process is very complicated due to the lack of natural DDR reflector. So you need to use like tens of pairs of dielectric DDR, and you need to worry about the how to fabricate and process those VCSELs. So natural VCSELs is still unmeasured until today, but we found that in the future, if you can make very good VCSELs, the data rate can achieve. I mean, the bandwidth is already beyond 25 gigahertz bandwidth, and you can see, you can imagine that the data rate achieved by using VCSEL-based transmitter is easily go beyond 50 gigabits or even up to 100 gigabits per second data rate. That will become a very, very promising or competitive device for future wireless communication applications. But I want to bring you back a little bit to see those superluminescent diodes. The SLD is actually a very, very interesting device that can hybrid advantage of both LED and laser diodes. So I don't want to go. I don't have enough time to go too much detail about the design and fabrication process, but I don't want to let you know to see the spectrum. So the emission spectrum for the LEDs is very broad, as you can see in the black curve. For the lasers, it's very narrow, like in the blue color. But the SLD is something in between. So the red curve refers to the spectrum from the superluminescent diodes. So it is something like between LED and the laser. If you make it into a white light source, you can see similar thing that the color rendering index and color temperature is exactly in between LED-based white light and laser-based white light, and it's more close to LED-based white light. And this is the far field emission pattern. It also shows quite good curve if you compare with the LED with the laser-based white light. So that means we can use SLD as a good transmitter for white lighting and use it for high-speed modulation. So you can see a quite high modulation bandwidth and a very good open eye in the data communication system by using OOK modulation technology, the OOK modulation technology. Now the speed here is 1.3 gigabits per second. It's not so, I mean, it's not so good, and also the Wi-Fi, the CI is about like 60 something, and we can further actually improve it to close to 90. Yeah, by engineering the phosphor use, and the power can go to a few hundred milliwatt. Yeah, and the bandwidth we can achieve is beyond, it's over gigahertz bandwidth, and the data rate we can achieve is even higher. So this is in 2018. This is in 2019, and in 2020 we published paper in OEA, the Optoelectronic Advances, that by using the CAP motion technology, we achieved close to 3 gigabits per second data rate, actually 2.95 gigabits per second data rate, using the carrierless amplitude and phase modulation technology. Actually, the data rate can be further improved by using the OFDM, using the 16-QAM DMT. We achieved 3.4 gigabits per second data rate in 2019. Recently, just like 4 months ago, we report an even higher data rate, over 4.5 gigabits per second data rate, using the bit loading and power allocation algorithm in those DMT communication system. So this is an engineered loop SLD that with optimal waveguide design. So I just want to let you know that the self-fluorescent diodes that we are developing will show quite good potential for high-speed data communication purposes. So we further make into some modules that can be directly used as the transmitters, including those white light transmitter modules, the high-speed laser and SLD transmitter modules that integrate those optics, the drivers, the temperature controllers for communication test system, which can support both high speed and white light generation. So those can be devices used in high performance optical wireless communication system. And the data rate we achieve for those white laser systems is over 4.7 gigabits per second data rate. And those can be used for a wide FOV, the wide field of view communication system, which means it's no longer a point-to-point communication link, but become a quite broad area coverage that can support multiple users, and it can support like communications with like moving objects or moving units. So talking about the transmitters, I also have spent a few minutes talking about the receivers. Yeah, in receivers we have PMPs, the PDs, and the nitride-based PDs and APDs. So I don't think I don't have enough time, so I will go a bit quickly. I just want to highlight the 3 nitride-based micro photodetectors, and those we have micro LEDs. We also have those micro photodetectors that can support high-speed data communication. But the unique part is like with those quantum wave-based active region, we can achieve selectivity in the responsibility spectrum, which means we can have a quite good SNR, because for silicon, the responsibility curve is quite broad, which means it will receive signal, it also receive those noise. But with those nitride-based photodetectors, we can have a quite good selectivity. For communication, this is beneficial because we have improved SNR. And by using those micro PD as a receiver, we also achieve like few gigabits per second data rate communication. And also we can use, we can use those devices because those are all on 3 nitride material system. So we can further integrate all the functionalities, like using the same material platform to include the signal generation, light receiving, energy harvesting, and beam tracking. All those functionalities it is possible to integrate it together, like solar cells, HAMs, LED, PDs. They can all use the same material system on a single chip. So I will skip this one. I will. This is the high-speed receiver module. So we already make into a very compact module that can be used in the system. So now I will go into the discussion about the integration. For indium phosphide-based material system, people already start to integrate those lasers, optical amplifiers, modulators, and the photodetectors in a single chip. So integration will bring a lot of advantages, and reduce the size and improve the functionality and reduce the cost for the system. So for nitride, actually until 2014, the CNRS in France started to work on the integration of light emitters and the transmitters and the receivers in a single device. So it's a core shell nanowire structure that one end is an LED, the other end is a detector. And the translation time is below 0.5 seconds. This is a very, this is good, but it's too low for communication. So later group of researchers, Professor Wang Yujin from Nanjing University of Post and Communication, his group actually worked a lot of excellent work on the LED platform, try to integrate those LEDs with PDs and waveguides and other devices on a single material platform, and reveals that or confirm that the light emission and light receiving can be coexist in a single material system or on a single chip. So Suzhou Institute of Nanotechnology, Chinese Academy of Sciences, is also working on those integration. So on-chip integration of nitride lasers, modulators, and PDs has been reported by a group of researchers. Yeah, this is the first author is Feng Meiqing, and latest author is Sun Qian, Professor Sun. They all have very, very excellent work on integrate those different functionalities on a single chip. This has been reported in JSTQ in 2018. So we also did the demonstration of high efficient waveguide modulators and integrated with the layer diodes. So I will not go too much details, but I don't want to highlight that with a single polar quantum field structure, we can achieve a quite large extinction ratio which means on-off ratio is quite high. That will bring to a very, very high modulation efficiency. That is of advantages. So I will skip the discussion about the mechanisms, but I just want to show you that instead of directly modulate the lasers, with the waveguide modulator integrated, we can use those modulators to modulate the transmitter. The advantage is that modulator is a reverse bias devices, which means that the power consumption is very, very low. So in this case, what happens like we can save energy during this communication or during the signal transmission process. And we can achieve the data rate of over 1.5 gigabits per second data rate. The other thing is like we integrate the waveguide photodetector with a layer diode, so which means it can become a transceiver. It can receive, it can transmit light, it can also receive the signal. Yeah. So this is the integration of a transmitter and receiver for power monitoring and on-chip communication. Yeah, another thing is like we develop our optical amplifier SOA integrated with layer diode, and those integrated SOA can have a large gain under 6 volts, and with the modulated SOA scheme, we can support high-speed data communication. This will enable high-speed modulation for optical wireless communication applications. So to sum up, the optical wireless communication is a promising technology for wireless data link in the next generation 6G network. It will address many important applications. For example, the Internet of Underwater and Underground Things, or IOU strategy. The new applications I already covered. So what are the challenges? So of course, the optical wireless communication, if you want to final massive deployed in the 6G, yeah, you still need to face the fundamental limit by the light sources and detectors, which is currently what we are doing at Fudan. And also we need the ASIC chip for the baseband, for the signal processing. Yeah, we cannot directly use those in the telecom the system. So we need to engineer the ASIC. Yeah, and also there are other challenges that we are currently working on, like different device technology and system. For example, we have our unique modulation algorithm and other system technology to help to compromise the nonlinear effect in such light emitters and light receivers. So finally, I'd like to thank you for staying with us. So I have enclosed few references related to the topic we discussed today. And you are welcome to contact me through email. This is my WeChat and WhatsApp. So thank you, and welcome any questions.
Thank you for that insightful presentation, Professor Chao Xin. Now the stage is open for questions.
So I wish that everyone will stay safe in this
Okay, Doctor, thank you. I assume that you have no questions from the speakers. Once again, I thank you so much for being a part of this webinar and hope to associate with you in our future events as well, Doctor. Thank you.
Wonderful. Thanks so much.
Thank you, Doctor. So now moving on to our next presentation by Professor Sun Handang, Nanyang Technological University, Singapore, and presenting on the title by Micro Lasers Made from Hybrid Shell Colloidal Quantum Walls. On behalf of Professor Handang, I am going to play his video presentation.
Hi, my name is Han Dongsen. I'm from the Division of Physics and Applied Physics, School of Physical and Mathematical Sciences, Nanyang Technological University in Singapore. Today it's my great pleasure to present on micro lasers made from hybrid shell colloidal quantum wells. Here is the outline of my talk. First, I will present the motivation of why employing colloidal nanoplatelets as optical gain materials for semiconductor lasers. Then, I will briefly describe how to manipulate the optical properties of colloidal cadmium satellite nanoplatelets, including 3 approaches: nanoplatelets with different thickness, post-synthesized ligand exchange, and heterostructure engineering. I will then report our work on the fabrication and the characterization of microcavity lasers made from co-gradient shell nanoplatelets. Finally, I will conclude with a summary. As is well known, colloidal nanostructures have been attracted a great deal attention as an optical gain materials many years ago. There are a few reasons accounting for the motivation. First, the effective band gap of colloidal nanostructures can be conveniently modified by either the composition or the size of the nanocrystals Therefore, the emission wavelengths from these materials can be tunable. Second, the electronic structure of low-dimensional materials are favorable because of the discrete density of state, which makes them promising for low pump threshold lasing and the potential to build quantum emitters. Thirdly, compared to bulk semiconductors, nanostructured semiconductors demonstrate better temperature insensitivity. Lastly, the fabrication of solution processing of colloidal materials makes them cost-effective and can be able to be integrated with optical cavity. This would be a great advantage because the optical gain material and the optical cavity can be developed separately. Because of the above-mentioned advantages, colloidal nanostructures have attracted attention 2 or 3 decades ago. The initial focus of developing the colloidal nanostructures had been on the development of colloidal quantum dots. Indeed, research on colloidal quantum dots have been rewarded with inspiration. However, the subsequent investigation indicate that the performance of zero-dimensional quantum dots-based lasers is limited by the fast Auger recombination inherent to the electronic structure of quantum dots. This can be clearly seen in this figure. Normally, in a quantum dot, because of Pauli exclusion law, there are 2 excitons can be allowed at the ground state. If one electron is excited from the valence band to the conduction band, the formed exciton may undergo stimulated emission. However, the remained electron in the valence band can be absorbed by a photon with the same energy and the same probability as the stimulated emission. This means that the dot is in the state of transparency. In order to have optical amplification, 2 excitons should be excited by increasing the pump intensity. Because of the quantum confinement, 2 excitons were bind together to form a bi-exciton. The radiative interaction between a photon and the bi-exciton through stimulated emission may provide light amplification. Meanwhile, the bi-exciton may experience decay through a larger channel. This is the so-called Auger recombination. In this process, the combination of bi-exciton will not release one more photon, but rather the energy will be dissipated to generate the ionization of electrons or a hole. Apparently, the competition between the stimulated emission and the Auger process will lead to higher pump threshold for light amplification or lasing. In this context, nanostructures with no confinement in 1 or 2 dimensions would be preferred. Indeed, this is actually the first modification of developing 2-dimensional nanoplatelet for optical gain material, because in this structure, the quantum confinement only in one direction. Compared to colloidal quantum dots, colloidal nanoplatelets have another advantage of small inhomogeneous broadening, which lead to a narrow gain profile and further reduced the pump threshold. The third motivation of colloid nanoplatelet lies in the cost-effective fabrication compared to epitaxy-based quantum wells. In epitaxy-based semiconductor lasers, several requirements shall be considered simultaneously, including lattice mismatching, refractory index contrast, and band alignment between different heterostructures, or between different heteral layers, which makes the available materials very limited. Lastly, the colloid nanoplatelets have broad spectral tunability, as will be demonstrated later. There are three approaches to manipulate the emission wavelengths, including cycles in vertical direction, the ligand modification, and the core shell architectures. Now, I will report what we have done in this field. First, we fabricate bare cadmium selenide nanoplatelets with different number of monolayers. We measure the electronic structure of these samples by spectroscopic ellipsometry. The optical absorption spectra of sample with monolayer 3, 4, and 5 are shown in this figure. The excitonic absorption spectrum of samples, the excitonic absorption spectra corresponding to different optical transitions and systematic redshift of the transition energies as the monolayer increase can be clearly seen. The corresponding transition energies are consistent with the simulation based on 8-band KP method. The details can be referred to this JPCL paper. And in this paper, we also provide detailed information about the dielectric properties of cadmium selenide nanoplatelet thin films. This would be important for the application of lasers. As is well known, there are ligands on the surface of colloidal nanoplatelets. So the second method we can use to manipulate optical properties is to change the ligand. And the pristine nanoplatelet were carboxylate capped and demonstrate low PL quantum yield. After the processing of ligand exchange by cadmium bromide, the sample demonstrates spectral redshift and the quantum yield improvement. These features have been commonly observed by several groups. Actually, the bromide treatment can be regarded as an approach to fine-tuning the emission wavelengths from nanoplatelets. Okay, once more, we further explored the temperature-dependent PL and observed different behaviors between the pristine and the bromide-treated samples. In particular, the abnormal negative thermal quenching behavior has been observed in bromide-treated samples. This implies the potential change of the electronic structure by ligand exchange. Previously, some models, such as cyclase change or strain change induced by ligand modification, have been proposed to explain the spectral redshift. However, those models cannot explain the quantum yield improvement and the abnormal thermal quench. We propose a surface definition model. In this model, a large amount of charge on the surface of pristine nanoplatelet leads to bending. The charge on the neutral can be neutralized by bromide treatment. This reduced surface charge lead to weaker quantum confinement for carriers. So this model can consistently explain the experiment phenomena, including spectral redshift, quantum yield increase, and abnormal temperature-dependent PL. In particular, the transition energy are in agreement with the theoretical simulation. And also, again, the detail of this study can be seen from this JPCL paper. The third approach of manipulating the electronic structure is the core shell architecture. The shell layers will provide protection of non-radiative defects on the surface of nanoplatelets and improve the PL quantum yield. More importantly, the choice of different band alignment between the core and the shell offers an extra degree of freedom to manipulate the wave function distribution of the electrons and the holes in the normal direction of the nanoplatelets, and therefore it will change the optical gain property. Here, we report our progress in nanoplatelet comparison cadmium satellite core and cadmium zinc sulfide shell with gradient composition. The advantage of gradient composition in the shell includes higher PL quantum yield and further reduced order recombination rate. Here we show the characterization of a typical sample. The excitonic absorption peaks can be clearly seen in the optical absorption spectrum, and that the PL quantum yield is as high as 8%. We fabricate thin film from this core shell nanoplatelet solution by spin coating and investigate the optical gain properties at room temperature by pumping the thin film in a stripe shape and measuring the PL from the edge. The pump light is a nanosecond laser with wavelengths of 532 nanometer. Upon weak pump, the PL shows broad spontaneous emission, just like this. As the pump emission increases, a new emission band emerges at longer wavelengths. The PL intensity of this new band increase sharply as the pump fluence increase, and the spectral width of this new emission band is much narrower. This is the clear indicator of stimulated emission. The pump threshold for the stimulated emission is only 17.3 microjoules per centimeter square, and the optical gain can be conveniently determined by the variable stripe length method. And as you can see, the optical gain is very high for under two different pump fluence. Based on the excellent optical property of the core gradient shell nanoplatelets, we construct whispering gallery mode laser by drop casting the solution onto the surface of a microsphere. We found that a smooth and uniform layer of the solid state nanoplatelet can be formed on the surface, and the thickness is around 500 100 nanometer. Actually, it's 490 nanometers. We investigate the laser property under a homemade optical measurement system. A long working distance microscope is used to collect the laser signal, and the microsphere sample is pumped by inclined illumination of a nanosecond green laser. We measured the polarization and the spectral resolved optical signal through the optical components, and 750 centimeter molar chrometer combined with intensity enhanced CCD. We monitor the spectral evolution of the emission from samples with different diameters and observed clear laser emission with multiple longitudinal modes. The laser threshold of all samples is very small and also related to the sphere size. The optical field distribution can be seen along the perimeter of the sphere, as this can be clearly seen here. So this implies the Whispering Gallery mode laser. To verify the laser mechanism, we did a simulation based on FTTD platform. In this calculation, the information about the refractive index of the nanoplatelet thin film was obtained by spectroscopic ellipsometry. The size of the device is determined by SEM. All the longitudinal modes can be well identified. The Q factor is around 4,000. The size dependence of free spectral range is well consistent with Whispering Gallery modulation. So, and also it is noticed that the optical field is strongly localized inside the nanoplatelet active layer. So this is probably accounted for the low threshold and the high Cornet factor. To study the polarization anisotropy of the nanoplatelet Whispering Gallery mode microlasers, the laser emission spectra as a function of rotation angle with respect to a linear polarizer below and above the laser threshold are recorded for comparison. Below the threshold, very little change in the PL intensity is observed with variation of theta. This indicates a very low polarization ratio for spontaneous emission. However, the laser action above the threshold is strongly polarized with dominant optical feedback paths perpendicular to the equator plane. The polarization anisotropy can be as high as 79%. This result verifies the Whispering Gallery mode mechanism and also tells the selected optical feedback path, which is related to the pump direction. We also examine the evolution of the laser intensity of this Whispering Gallery mode laser and the continuous and strong nanosecond pulse excitation for over 100 minutes at room temperature in ambient conditions. Please note that the pump excitation was already 1 order of magnitude larger than the laser threshold, so the pumping is very strong. So the result shows that all the laser peaks are kept at the same position, and there is no significant quench of the laser output or chemical degradation is observed during the measurement. So this means that the microcavity laser is very stable. Lastly, we exploit the Vernier effect, in which the shared resonant mode of the individual cavity will be enhanced, while the other longitudinal modes will be suppressed in coupled microspheres. We choose two microspheres with diameter 48 micron and 44 micron respectively. Both microlasers demonstrate multi-mode lasing when they are isolated. However, when putting them together, the coupled laser delivered laser output of single mode. The wavelength of this mode is actually shared by the two isolated ones, as like this. So this means that the two microcavities are coupled by effervescent field and governed by Vernier effect. The coupled single mode laser may find great application in high sensitivity sensors for temperature, as well as chemical and biological sensing. I would like to benchmark the performance of our nanoplatelet microlasers to the reported ones. We attribute to the excellent performance of our lasers to the choice of interface engineered core gradient shell nanoplatelets with remarkable gain properties, and also appropriate spherical microcavity with high Q factor. Our work offers a compact, robust, and universal fabrication method towards fabricating colloidal nanomaterial-based high-quality single-mode coherent light source, which cover the whole visible spectral range. To summarize, we demonstrate capability of synthesize high-quality nanoplatelets for the application in colloidal semiconductor lasers. We have synthesized high-quality nanoplatelet, and we also systematically explored spectral tuning of nanoplatelets by 3 approaches, including nanoplatelet sequence, ligand exchange by bromide treatment, and interface engineering through core shell architecture. Through detailed optical spectroscopic characterization, we obtained better understanding of the underlying physics. Especially proper physical models have been proposed to consistently explain the optical property. We have found that engineering the gradient shell on the surface of cadmium satellite nanoplatelets result in excellent optical gain properties. Based on optimized nanoplatelet material, we have constructed Whisper-Gary mode microlasers by coating the nanoplatelets on the surface of a microsphere. Benefiting from the high optical gain of the nanoplatelets and the good optical field confinement provided by the Whisper-Gary mode structure, we obtained low threshold, high Q factor lasers. Furthermore, we realized single frequency lasing by exploiting Vernier effect from 2 microcavities with different size. Before I conclude, I would like to express my gratitude to my group members and also collaborators. I'm also grateful to the funding agency from National Research Foundation and A-Star for their support. With that, I'd like to thank you very much for your attention, and I would be happy to answer your question.
Thank you for that insightful talk, Professor Sun Handang. Now the stage is open for questions.
Thanks a lot, Professor Sun. I think this is a very, very insightful and a great talk. So actually, I have the question. Actually, we are interested in the using those kind of quantum dots, especially colloidal quantum dots and the nanoparticles to as a phosphor material to convert some of the UV light, especially for UVC, into, for example, a longer wavelength in the blue, green, or red color regime. Yeah, I think you are the expert in this field, and I look forward to further learn and collaborate with you in the future. Thank you so much.
Thank you, Professor Sun. Yeah, I noticed your question because you are asking about the absorption by UV. To tell you the truth, that most colloidal nanomaterials can absorb at UV. However, so far the emission wavelengths of most colloidal nanostructures usually emit at red, or some emit at green. There's still not easy to extend the wavelengths to blue or even UV. Of course, this would be an important direction. And we are very interested to develop some blue and UV colloidal nanostructures. Currently, there are some progress. However, we have never reported. Hopefully, we can report it soon. Yeah. Okay. Of course, I look forward to the collaboration with you. Thank you.
Thank you for answering the questions, Dr. Sun Handang. Once again, I thank you for being a part of this webinar and hope to associate with you in our future events as well.
Thank you,
Doctor. Thank you so much. Now, moving on to our next presentation by Dr. Yunxi, Chinese Academy of Sciences, China, and presenting on the title, Development of CEGD3 GAL5O12 crystals scintillators by optical floating zone method. Hello, Dr. Yunxi. Hello, Dr. Sun Handang, please.
Can you hear me now?
Yes, doctor.
Okay.
You can start.
Yes, it's clear.
Okay.
Hello everyone. I'm Shi from Shanghai Institute of Ceramics, Chinese Academy of Sciences. And firstly, on behalf of my colleagues and assistants, I would like to express our thanks to the organizer. To give me such a chance to share our research work here. Today, I would like to talk about the development of serum-doped GGAG crystal scintillators by the optical floating zone method. I will present the work according to the following outline. In the first part of my report, I'm going to begin with the background of my work, including the introduction of composition engineering strategies and optic floating zone method. And then secondly, I would discuss in more detail specific issue which concern the fast growth of serum GGAG crystals, stable growth of it, and wide concentration of the serum and terbium co-doped GGAG crystals. And finally, I will give conclusions and perspectives. As shown here, the scintillation materials can transfer high energy rays to particles to or all particles to visible light, working as the spectral and energy transformer, and when combined with a photomultiplier tube or photodiode to form a scintillator detector, they are widely used in high energy physics and nuclear medicine imaging for tumor detection, and for security clearance for inspection, industry CT for non-destructive testing, and even can be used in food security field. Well, this graph presents the development of representative scintillators with high light output, which have been studied for many years in the past few decades, and abundant compounds, including both oxide and halide components, have been proposed to meet the growing demand on high performance of devices and apparatus. The higher density, faster decay, and better energy resolution and higher scintillation light yield is expected. And among those, the serum doped GGAG is considered as one of the most promising candidates. It has a cubic body-centered lattice and symmetric garnet structure, which means both crystal growth and transparent ceramic fabrication are available. More importantly, the empirical calculated light yield value of serum GGAG is the highest among the oxide scintillators found so far. It also has excellent energy resolution, much better than another material commercial scintillator, the serum doped LYSO. Besides, it was found that the change of the gallium and aluminum ratio in the component can affect the energy band gap, and that would lead to the variation of light yield. So it sheds light on a possibility of performance optimization through the composition engineering. Till now, different types of serum doped GGAG have been developed, including power, film, transparent ceramics, and crystal. Considering the crystal has the most perfect structure than any other types, and it can avoid influence from power, particle diffraction, and ground boundaries, and it would help to reflect the inner information of the materials. So the researchers from Japan ever growing the serum GGAG crystals by the macro pulling down method, they found that compared with the negative effect of lutetium ions, proper amount of gallium ions help to suppress the effect of shallow electron traps, and thus lead to the improvement of the scintillation efficiency. The optimum gallium content is suggested to be between the gallium and aluminum ratio range between 3 to 2 and 2 to 3. The highest light yield lies in the gallium 2, aluminum 3 composition. However, the scintillation decay is slow in this case, which indicate a comparatively higher concentration of atomic level defects. Well, according to the above composition screening results, they also explored the large size crystal growth by the CZ method. However, as shown in this picture, it is difficult to grow serum GGAG crystals when, especially when the gallium to aluminum ratio is lower than 322. After careful study, it is proposed that the gallium oxide is easy to volatilize during high temperature crystal growth process, and the component deviation caused by the gallium evaporation will certainly introduce twisted growth like this, and formation of defects and even appearance of polycrystalline and or mixed crystals. So to solve the volatilization problem, traditionally 1 to 3% excess gallium was added to an otherwise stoichiometric melt composition in order to compensate for its volatilization loss from the melt. However, it is revealed that the afterglow intensity will remarkably increase by around 2 orders of magnitude in the excess aluminum and gallium compositions. Besides the excess gallium composition strategy, the oxygen-rich environment also works in restraining the decomposition of gallium oxide. However, in order to prevent possible oxidation of the iridium crucible, the typical growth atmosphere is usually inner gas instead of oxide for the micro pulling down or CZ method, or so only a few % of oxide mixed. Accordingly, the iridium particles volatilized due to high temperature and oxidation tends to adhere to the surface of the crystal. And because the iridium has a strong thermal radiation capacity, its temperature is lower than that of the melt, so which leads to unsymmetrical temperature field. It will result in twisted growth of the crystals. That's the failure of cerium-doped GGAD crystal growth, especially when gallium to aluminum ratio is lower than 3:2. Considering the above problems, we propose the use of the optical fluorescence method. Compared with the common crystal growth techniques such as the micropulling down CZL Bridgman method, the optical fluorescence method is characterized by crucible-free and atmosphere adjustable. It has advantages in the growth of incongruent melting crystals, compounds with the volatile components, and real-time observation. So the container-free avoids the contamination of impurities from the crucible, which is essential to the defect-sensitive scintillators. Now, in the following, I will show what we conducted in the growth of cerium GGAD crystals by the OFZ method. The scheme in the right side is our experimental process. The commercial oxide powers were mixed according to the chemistry stoichiometric and ball milled before the calcination. Then they were pressed to a long rod and centered in air to form a ceramic rod for crystal growth. The final crystal growth was conducted in OFZ furnace. Considering the problem of gallium oxide volatilization when crystal grows at a high temperature, we adopted the oxygen atmosphere 100% and auxiliary pressure, which is 0.3 millibar to inhibit the gallium oxide volatilization under a containerless environment. The crystal quality, luminescence, and the scintillation performance were evaluated accordingly according to the cerium concentration. In this part, we also investigated the traveling solvent fluorescing zone method with a TSFZ method, which is a modified OFC method to realize the stable growth of cerium GGAD crystals. And I will explain the second part. And in order to improve the improve the luminous property, we also investigated the effect of terbium co-doping in a wider concentration range, which I will present in the third part. Well, the first is the faster growth of serum GGAG single crystals. As you can see, a series of GGAG crystals with different serum concentration from 0.2 to 0.8 were designed and grown by the OFZ method. As shown in the picture, they are bright yellow and transparent. The X-ray diffraction and the lower photograph demonstrated they are pure garnet structure with good crystal quality. And the characteristic absorptions origin from the 4F to 5D transitions of the serum 3+ ions basically deepened with the increase of serum concentration. The main emission located at 540 nanometer, and it can be observed by both photoluminescence and radioluminescence spectra, which were originated from the 5D to 4F transition of the serum 3+, and both the PL and radioluminescence intensity of the serum GGAG crystals are higher than that of the ceramic analogies. The graph and table in this page summarized the serum concentration dependence of the scintillation light yield and decay under the gamma ray excitation. The 0.6% was found to have the strongest photoluminescence and radioluminescence intensity, fast decay, and the optimum scintillation light yield. Well, the second part of our work is about the stable growth of serum GGAG crystals. Although we have made progress in OFC method in the first part of our work, we also can find there are some disadvantages. As shown in the picture, it's difficult to keep the molten zone continuously stable during the crystal growth process. It is due to the increased incongruent melting trend in the low gallium and aluminum ratio compositions, which may remarkably affect the crystal quality by introducing cracks and composition uniformity. So we can see it further according to the diagram of the gadolinium and aluminum oxide system. The gadolinium aluminum garnet phase is made stable and at high temperature, and cannot be grown by the melt growth due to incongruent melting and phase instability. So comparatively, the traveling solvent floating zone method have been widely used to grow incongruently melt compounds. It can also grow crystals in lower temperature with a stabilized molten zone using suitable solvent components selected according to the corresponding phase diagram. Well, here we designed and investigated a series of solvent compositions where the mole ratio of the gadolinium oxide and aluminum oxide is 25 to 75, 27 to 73, 29 to 71. Respectively. Solvents help to compensate the composition deviation during the crystal growth. It can then obviously help to sustain a steady molten zone during the whole crystal growth process, and the continuous and stable crystal growth was not achieved. The GGAG crystal growing using the 25 and 75 composition solvent were found to have the strongest XEL luminance intensity, and their optimum scintillation light yield reaches around 34,132. which is comparable to the previous published crystal growing by the OFZ method or micro pulling down method. Moreover, the S-growing serum GGAG crystal with 29% gadolinium and 27 and 71% aluminum solvent demonstrated a faster decay and higher ratio of faster component. So the TS-FZ method is thus proposed to be an effective novel method for growing approximately incongruent melting GGAG compounds. Well, after systematically studied on the OFZ and TS-FZ method, we already achieved the successful growth of cerium-doped GGAG crystals. In order to obtain a deeper understanding of the energy transfer mechanism between the cerium and terbium ions in the aluminum garnet host to find new and high efficiency scintillator materials, the cerium and terbium co-doped GGAG crystals were growing by the OFZ method, and we investigated in a wide range of terbium concentration range from 1.1% to 66%. Well, from the X-ray diffraction pattern of the presented and the raw materials powers and as growing crystals, detectable perovskite phase can be observed in high terbium concentrations, which reveals a difficult solid solution of terbium ions into the GGAG lattice. It might be related to the terbium doping saturation effect owing to the lattice mismatch, as well as the decreasing of crystal field symmetry after more replacement of terbium to gallium in a doctahedral position. The stability of GGAG can be achieved by partially substituting gadolinium with smaller rare earth ions, while radius of ions is larger. While with the increasing of terbium concentration, the lattice mismatch may be serious. The SEM EDS mapping image for cerium terbium element of the crystals were presented here. The homogeneous element distribution can be found, and by the XPS vector, we explored the valence state of terbium ions in the S-grown GGAG crystals and used the commercial terbium oxide power as reference. The results indicate that the terbium-3 and terbium-4+ coexisted in the compound. So the origin of the second phase observed in the X-ray pattern can thus be mainly ascribed to the cerium and gallium evaporation introduced the composition deviation, as well as the formation and existence of terbium-4+. In the nominal terbium concentration range of 1 to 66%, the optimal content of terbium is 7%, which was found to have the most intense pure intensity and comparatively the highest light yield value. The opinion presented so far may be summarized as follows. Fast cerium-doped GGAG scintillator crystals growing with the gallium to aluminum is 2 to 3 ratio were demonstrated in this work. The OFZ method is proved to be effective to grow cerium-doped GGAG multi-composition crystals, considering its advantages in adjustable and crucible-free to inhibit the gallium oxide evaporation effectively and avoid contamination. And second is stable cerium GGAD crystal growth can be achieved by TSFZ method. The method is thus proposed to be an effective novel method for growing approximately incongruent melting cerium GGAD compounds. And the third is a wide range terbium concentration in cerium GGAD crystals was investigated from 1 to 66%. The optimal content of terbium is 7%, which was found to have the most intense photoluminous intensity and the comparatively highest light yield value. Then scintillation performance optimization in GGAD-based crystals can be expected after careful study on regulation of crystal growth parameters and composition engineering strategy. The research development summarized in this presentation were collected from our recent works, which were presented in the following publications. Shown here for your reference. And as a member of the editorial board, a short advertisement here. The Chinese Journal of Luminescence is a comprehensive journal specializing in luminescence. It will accept and publish both Chinese and English papers. So we are looking forward for your submission. I would also like to express my appreciation here to my colleagues, Professor and Dr. Huang Xintang from Central China Normal University, Professor Dr. Papinov and Dr. Chaling from Far Eastern Federal University, and of course to many thanks to my students Wu Tong, Wang Ling, Zhang Qian, and Xiu Yifei for their contributions to the experimental process. Well, that's the end of my presentation, and thank you very much for your attention.
Thank you for that insightful presentation, Dr. Yunxi. Now the stage is open for questions.
Yeah, I have a question for Dr. Shi. So I noticed that in recent years, many people are interested in applying halide perovskite as a scintillator for X-ray detection. So I'm not sure what's the advantage of your material compared to halide perovskite.
Yes, it's a good question. As I ever talked in this page, there are two kinds of scintillator materials. One is oxide, another is halide. And for both of them have their own advantages. I'm focused on oxide. So for oxide materials, scintillator materials, the advantages is mainly their stable chemical and physical properties. And another character of oxide materials is their usually high melting temperature, usually beyond 1000 degree. So for this kind of material, their light yield is around the highest light yield. For the series light yield is around 80,000. So, but for the as you know, we can see this band gap graph. But for the halide materials, usually the band gap energy is very low, around less than I think 3 or to 5 around the electron volt. So you can see the light yield is the relationship with the energy gap is there is if the energy gap is lower, the light yield would be higher. So for most of the halide materials, their most advantages is their very high light yield value, usually higher than that of oxide materials. But for highlight materials, they have their own disadvantages that could be do more study to improve it, such as they are low temperature, unstable in the high temperature environment, or like not many highlight crystals can be growing for large size. I think both of them have their own advantages and disadvantages.
Yeah. Thank you. Yeah. Understand. Thank you.
Thank you for answering the questions, Dr. Yunxi. Once again, I thank you for being a part of this webinar and hope to associate with you in your future events as well. Thank you, Doctor. Now moving on to our next presentation by Dr. Moon Hushral Edhernibat, Chungbum National University, South Korea, and presenting on the title 3D 2D switchable augmented reality display system using liquid crystalline microlens array and electrical polarizer. On behalf of Professor Moon, I am going to play his video presentation.
Hello, my name is Moonkuchil Irtunbat from Chungju National University, South Korea. Today I would like to present our recently developed 3-dimensional and 2-dimensional switchable augmented reality display system using liquid crystalline microlens array and electrical polarizer. Today's my presentation consists of main 4 sections: the introduction for previously conducted related research, the main description of the proposed system, the experimental results and conclusion, and future research. The head-mounted display based on the virtual reality and augmented reality methods have gained much popularity in recent years. The head-mounted displays are that the user wears it on the head like a helmet or eyeglasses. Most of the virtual reality systems are based on the stereoscopic 3-dimensional technique, which is the simplest way to display the 3-dimensional image through the binocular depth cues of human visual perception. And the user is completely sequestered from the real world. It displays slightly different dual 2-dimensional images to the left and right eyes respectively, and both images are combined in the brain to give the perception of 3-dimensional depth and parallax views. Unlike the virtual reality technique, the augmented reality systems can mix the digital items with the real-world environment, that it's able to overlay the digital elements into the real world. Here, the user controls the digital elements without using any specific device, only by the face actions and hand gestures. The see-through AR systems can be replaced for the smart mobile device in future, because all of the functions of the mobile device are included basically, and it has enough of computing power. There are several types of waveguide method are utilized in AR systems: the reflective type, the diffractive type, and holographic waveguide type. Among them, the holographic waveguide type AR method is most effective and advantageous. Note that in order to implement the virtual components mixed with the real-world environment, it's necessary to design the optical system considering the pupil size, virtual image, optical distance of the image of the eye relief, the image magnification, and field of view. Since the optical elements such as mirror and beam splitter are utilized, the overall device becomes much bulky and heavy, and it's difficult to mount the various elements in the narrow space. As mentioned before, the holographic waveguide type AR system is an advantageous method with a simple structure and lightweight, that only 2 holographic optical elements guide the light beams from the microdisplay to the observer's eyes. and the light beams are propagated by total internal reflection phenomena. The biggest advantage of the holographic waveguide is that it doesn't require any glass substrates in the in and out couplers. Since the holographic waveguide type AR systems use the holographic optical elements, the number of optical devices are remarkably reduced. The holographic optical element is the thin film that obtains the desired waveform by recording a hologram through the optical holographic recording process. The holographic optical element can be the lens or lens array, mirror, prism, and so on. So currently, many conventional optical elements and devices are replaced by the holographic optical elements. For the HOA fabrication of the holographic waveguide type AR system, the prism hologram prism sandwich recording method should be applied. This is the schematic diagram of the sandwich recording for in-coupler and out-coupler HOEs using two prisms. The reference beam is incident vertically and the signal beam is incident at 50 degrees. So the diffraction grating capable of total internal reflection is recorded onto the holographic material when it's attached to the waveguide. During the recording, the input and output HOEs can be recorded on the same waveguide by changing the setup to match the recording beam directions. Here, the real appearance of the holographic waveguide type AR display system and displayed contents. Most of the AR systems display only two-dimensional images according to the structure and types of the holographic optical elements. So it's necessary to find out the three-dimensional image display method for AR systems. As a background research, first I would like to introduce the recently proposed three-dimensional holographic waveguide type AR system using holographic micromirror array. Here, the holographic micromirror array is replaced on the in-coupler HOE and it reconstructs the elemental image displayed by the microdisplay as three-dimensional images according to the integral imaging technique. This system can display the three-dimensional images without requiring any additional device. The integral imaging technique acquires the three-dimensional information of the given object and reconstructs the three-dimensional visualization of the object through the lens array. This captured image is called by the array of elemental images and it encodes the full three-dimensional information, that the color, depth, and parallax information of the object. Here, each corresponding elemental lens samples the three-dimensional perspectives with different viewpoints from their respective overlooking locations. In the construction, the three-dimensional visualization of the object is reconstructed through the same lens array from the same elemental image array. This reconstructed three-dimensional image is observed in the space of in front or behind of the lens array, so it can be seen as a volumetric three-dimensional image. Here, the holographic micromirror array is recorded by 4F lens system based on the sandwich recording method, and the optical mirror and microlens array are used as a reference for holographic micromirror array fabrication. So this process is much simple and stable. For the outcoupler HOE, the conventional holographic optical element is used as it is. From the experimental results, it has been certified that the system can be an effective way to implement the see-through AR three-dimensional display that mixing the virtual three-dimensional images and real skins without using any additional optical device. However, due to the optical aberrations of the holographic micromirror fabrication, the quality of the virtual image was degraded. Recently, the polarization-dependent switching liquid crystalline microlens array-based light field camera system has been proposed. Here, according to the electric switching layer of the polarization layer, the three-dimensional and two-dimensional modes can be time-sequentially switched quite rapidly. In order to implement the polarization-dependent switching liquid crystalline microlens array, the planar convex passive microlens array is utilized as a reference. The polarization-dependent two-dimensional and three-dimensional modes phase profiles can be preserved well after converting the reactor mesogen, which is the liquid crystalline layer, to the solidified film with UV-induced polarization. In the experiment, it has been verified that the two-dimensional image sends elemental image array for a three-dimensional light field image are captured according to the polarizing directions. From the captured elemental image array for a three-dimensional mode, the orthographic view and depth refocused images have been reconstructed successfully. So this method was confirmed that the liquid crystalline microlens array can display the clear view two-dimensional and three-dimensional images as the function of the electrical switching. And in this report, the three-dimensional and two-dimensional switchable AR display system using the liquid crystalline microlens array and electrical polarizer is proposed. Here, the depth camera is used for supporting the proposed system with three-dimensional information or two-dimensional image of the real object. The liquid crystalline microlens array switches its functions according to the polarizing directions. The proposed method's overall procedure is following. When the user presses the switcher of the electrical polarizer, the depth camera captures the depth and color image or single color image from the real object for two-dimensional and three-dimensional modes. In the two-dimensional mode, the captured color two-dimensional image is displayed on the microdisplay as it is, and the observer can see the displayed image directly. In the three-dimensional mode, for displaying the image, the three-dimensional model of the object is generated according to the captured depth and color information, and the elemental image array is rendered by the direction inverse propagation method. And finally, the generated elemental image array is displayed on the microdisplay. Then the liquid crystalline microlens array is reconstructs the three-dimensional image from the displayed elemental image array, and observer can see the reconstructed three-dimensional image with the real-world scan. The switcher of the polarizer and depth camera are interconnected with the integrated controller, so the three-dimensional and two-dimensional modes are switched automatically. Here, the flowchart of the proposed system is illustrated. The integrated controller synchronizes the electrical polarizer, depth camera, and microdisplay, and displays the corresponding images. In the two-dimensional mode, the captured two-dimensional color image is directly displayed on the system. In the three-dimensional mode, as mentioned before, the first depth and color images are acquired by the depth camera, and the elemental image array is generated through the direction inverse propagation method based on the GPU parallel processing. Here, the number of the lens, NX and NY, the pitch and focal length of the elemental lens, the PLA and FLA, and the gap between the elemental image array plane and lens array are inputted. Finally, the liquid crystalline microlens array reconstructs the three-dimensional image after the generated elemental image array is displayed on the microdisplay, and it's observed is mixed with the real-world objects through the proposed holographic waveguide type AR display system. The ray propagation for each pixel of elemental image array is from the elemental image array to the object points of the acquired tape data. The emitting light from the single pixel passes through the nearest elemental lens and intersects with the nearest object point. After the light rays from each pixel are intersected with the object points, the corresponding color information is carved from the captured color data to the corresponding pixel. For the direction inverse propagation method, the elemental image array is generated with the less computation, and the number of the object points doesn't affect the computation time. From this figure, it can be seen that the liquid crystalline microlens array focused and defocused incident light beams according to the polarization directions. Here, the three-dimensional mode and two-dimensional mode. In the experiment, we applied the liquid crystalline microlens array into the holographic waveguide type AR display system. Here we have a glass waveguide with in and out coupler HOVs. In front of the in-coupler HOV, we place the micro display and liquid crystalline microlens array with electrical polarization. The specifications of the main device are here. For the holographic optical elements, we use the Bayfall HX200 photopolymer. The liquid crystalline microlens array was consisted of approximately 45 by 45 elemental lens, and pitch and focal length of each elemental lens was 1 mm and 7 mm respectively. Then we checked the focusing and defocusing function of the liquid crystalline microlens array. Here, the beam patterns through the optical microscope. The liquid crystalline microlens array focused the incident light in the three-dimensional mode, where the incident light beams were passed through the liquid crystalline microlens array as they are on the two-dimensional mode. For the image of the A and B letters, the liquid crystalline microlens array could pass the two-dimensional image and reconstruct the three-dimensional images, respectively. These figures show the user interface of the integrated controller. In the three-dimensional mode, the depth and color images were captured by depth and color section, and in the two-dimensional mode, only the color image was captured in the color section automatically. And here are our recently obtained optical experiment results. We displayed the simple three-dimensional images of the prototype to check the two-dimensional and three-dimensional features of the proposed system. From the letters H and C, with different depth information, the two-dimensional image and elemental image array were generated and displayed by the microdisplay respectively. The input two-dimensional image was displayed as it is in the two-dimensional mode, but in the three-dimensional mode, the elemental image array has been input and displayed on the microdisplay, and the three-dimensional image was reconstructed and displayed on the proposed system. Here, the camera was focused on the H letter, which has the depth information of 10 millimeters, and here the camera was focused on the C letter, which has the 20 millimeter of depth plane. And we have checked that the letters have been reconstructed on the different depth plane, so the three-dimensional and two-dimensional images of the objects were displayed successfully on the proposed holographic waveguide type AR display system, according to the polarization direction of the electrical polarizer. Currently, the full-color HOV and real object-based optical experiment is under progress. And finally, let me conclude my talk. In conclusion, we proposed the holographic waveguide type AR display system using the liquid crystalline microlens array and the electrical polarizer and depth camera. According to the polarization direction of the electrical polarizer, the two-dimensional or three-dimensional modes of the proposed system are switched easily. And The depth camera requires the depth and color information or only color information according to the polarization direction. The integrated controller synchronizes the electrical polarizer, the depth camera, and handles the image displaying for two-dimensional and three-dimensional modes. The experimental results confirmed that the proposed method can be the effective way to display the two-dimensional and three-dimensional images of the real object on the holographic waveguide type AR display system. Our further research is focused on the completion of the system implementation, the full color display with the high diffraction efficiency of the holographic optical elements, and fast computation for the image processing. Thank you for your attention.
Thank you for that video presentation, Dr. Moon. Now moving on to our next presentation by Dr. Anar Kudurchulun, Changbuk National University, South Korea, and presenting on the title Full Color Holographic Stereogram Printing System Using Fast Digital Content Generation Based on IDP Algorithm. On behalf of Dr. Anar, I am going to play the presentation.
Hello everyone, I am Anar Kudurchulun from Chungbuk National University, South Korea. Today I am going to talk about full-color holographic stereogram printing system using fast digital content generation based on IDP algorithm. So here is my content. Firstly, I will talk about some introduction, and then I'm going to explain the proposed method. After that, I will talk about the numerical simulation and experimental result. Finally, I will conclude my talk. Holographic printer. Holographic printer is one of the applications of holography, and in recent years, the holographic printer has been tending to be the most promising application of holography with a high potential for a realistic 3D representation. And these figures show the printed holograms produced by commercial companies, and the holographic printer produces hard copies of a 3D object, and it can reproduce the realistic image from 3D digital data, and also it can provide very large field of view in any direction and high resolution 3D image. Moreover, the holographic optical element fabrication using holographic printer have proposed by several research groups, and it used in virtual and augmented reality display techniques. So in generally, there are two types of holographic printers. The one is holographic stereogram printer, and another one is a wavefront printer. As you can see, this table demonstrates the comparison between two types of holographic printers, and for these two types of holographic printers, the both color selectivity and white light viewable, and hologram type is both volume. And also one of the big difference is the digital input data, and for the holographic stereogram printer, the digital input data is parallax related images, and for the wavefront printer, the digital input data is computer generated hologram. So here the first image shows the printed holographic stereogram, and whereas the second image shows the printed hologram by wavefront printer. And the wavefront printer can provide the exact 3D image space, but the motion parallax information is low, and it requires a huge complex computation due to using the point-based algorithm compared to the holographic stereogram printer. And we focused more holographic stereogram printer, and it can provide the exact 3D realistic image with the shadow, textures, and occlusion effect. Now I'm going to talk about the principle of holographic stereogram printer, and this figure shows the basic configuration of the conventional holographic stereogram printer. And there are three main parts are required to produce a conventional holographic stereogram. The one is a digital content generation, and another one is a controlling system and optical printing process. So for the digital content generation, firstly, the perspective images are rendered from the 3D object, and then Hoggle images are generated from the rendered perspectives. After that, through the controlling system, the generated Hoggle image is displayed on the spatial light modulator and object beam propagating through the SLM and exposed on the holographic material by using an objective lens, while the reference beam illuminates the holographic material from the opposite side of the object beam. And finally, here the volume hologram is created as a single Hoggle. So to obtain the whole holographic stereogram, the Hoggle is recorded into holographic material one by one sequentially, and until all Hoggles are recorded into the holographic material. Moreover, for the controlling system, the electrical shutter, SLM display, and XY translation stage, these three optomechanical devices are work under the synchronized controlling system based on personal computer. And also, I will talk about the digital content generation in the next slide more detailedly. So for the digital content generation of the conventional holographic stereogram, it consists two main steps. And first step is acquisition of the perspective images, and second step is a transformation process from the perspective images to Hoggle images. And as you can see from here, the camera array is placed and rendering the perspectives of the 3D object. And here the example of 9 rendered perspectives are shown. And after rendering the perspectives, the transformation process is applied, and here all pixels of the perspective image is transformed to the Hoggle image pixel according to this equation and generating the Hoggle images. So the Hoggle images are generated from the rendered perspective images. And in the conventional holographic stereogram, it needs a high memory consumption and calculation time to obtain the perspective images by using a computer graphics software and algorithm execution to do the pixel-to-pixel mapping process from the perspective image in order to generate the Hoggle images. So our motivation is produce a full-color holographic stereogram which can provide exact wave dependence properties and accurate depth information by using a fast and simple effective method. And here the main configuration of the proposed full-color holographic stereogram printing system is shown, and it consists two major steps. The first step is digital content generation, and second step is a full-color Hoggle printing. And in the first step, the elemental images are generated according to our proposed direction inverse calculation based on integral imaging method, and then phase modulation is executed for each generated elemental image to enhance the image quality. And in the final step, the hologram printing process is applied to get the whole holographic stereogram. And our proposed method not only can provide simple and fast computation, and also it can provide the full parallax and depth information of the 3D object. Step 1. Elemental image array generation based on inverse directed propagation algorithm. As you can see from this figure, there are elemental image plane and virtual lens array and 3D object, and also the distance between elemental image plane and virtual lens array is a g. And here The inverse directed propagation is conducted from the elemental image plane to 3D object without checking each object point for every lens compared to the conventional integral imaging. And in other words, in the IDP algorithm, the each elemental image point is only checked through the corresponding single lens. So the iteration number of full computation is defined only resolution of the elemental image plane. So it doesn't depend on elemental lens number and number of the object points. That makes fast and effective computation. In addition, during the calculation, the collision effect is easily included without applying a specific algorithm, for example, hidden point removal algorithm, because in the calculation, if there are multiple points are defined on the one line propagation, for example, from this figure, there are 2 points are defined as A and B, but we get the nearest point A and replace it on the elemental image plane. So occlusion effect is easily included during the calculation. And also here, the equation of the conventional integral imaging calculates the elemental image point is transformed to this equation, and it calculates the 3D object point in the IDP algorithm. Phase modulated full color Hoggle. So in this figure, the entire process of digital content generation for the proposed system is presented. Firstly, elemental image array is generated from the 3D object based on IDP algorithm, as I explained in the previous slide. After that, the CGI generation process for phase modulated full color Hoggle is implemented, and here for each generated elemental image is scaled by pixels for the RGB channels, depending on the utilized wavelengths to remove the chromatic dispersion error in the full color hologram. And here, the blue channel is set as a reference, and each channel is resized by pixel using this equation, and after that each channel is zero padded to separate it from the zero order beam, and also each channel is phase modulated using a single FFT based on the Fresnel diffraction, and also the optimized phase shifting fringe pattern is added for each channel to record the 3 channels on the holographic material at the exact same position, and that process is repeated for all elemental images and generated the phase modulated full color Hoggle data. So step 2 is full color Hoggle printing, and this figure presents the schematic optical setup of the proposed HS printing system, and here the 3 electrical shutters corresponded to the RGB lasers and single phase only SLM, and also XY translation stage. These devices are work under the synchronized controlling system based on personal computer, and in the Hoggle printing process, the time sequential method is implemented by eliminating each laser beam sequentially for single full color Hoggle. Moreover, for each laser beam elimination, it starts when the shutter is opened. The laser is go through the several optical components for the laser beam initialization, and then divided into 2 beams by the first PBS as an object beam and the reference beam. The object beam eliminates the SLM through the mirror 2 and reflected from the SLM and demagnified by the objective lens 1 and 2, and then recorded into holographic material with the reference beam. The reference beam illuminates the holographic material from the opposite side of the object beam during the exposure time, and so the RGB channels displayed on the SLM sequentially and recorded into holographic material also sequentially at the same position in the holographic material with corresponding laser beam. After that, material is shifted to the next toggle position and RGB phase modulated toggles are displayed on the SLM sequentially one by one and recorded into holographic material as a full color toggle. So that process is repeated until all toggles are printed into holographic material. In addition, here a software-based controlling graphic user interface of full color toggle recording is shown, and this part is the SLM controlling part, and this one is a shutter controlling part for RGB laser beam illumination, and this part is the XY translation stage for material shifting. And as you can see here, this figure shows the toggle printing path, and this is the first toggle printing position, and toggles are recorded into holographic material one by one following this path, and toggles are recorded into holographic material until all toggles are recorded successfully. Numerical simulation. In the numerical simulation, there are three different 3D objects are used. The first object is 3D OYP, simple letters. The second object is pianage sphere. And third object is a real object Venus. By using a depth camera, we obtain the 3D point cloud object from the real object. And for these two objects are both virtual objects, and also in this table the object points number for 3D object are demonstrated here. And also, as you can see from these figures, generated elemental image arrays based on IDP algorithms are shown corresponding to each 3D objects, and also here phase modulated toggles are shown respectively. And in addition, this figure shows the computation time of the proposed and conventional method with the GPU computation, and from this figure the proposed method is generated the content effectively, and it doesn't depend on the toggle number. And also from this figure it shows the proposed method with GPU computation when using three different objects, and it shows that the computation time is almost constant, even the toggle number is increased. So our proposed method can provide fast and simple computation. Optical experimental result. These figures show the optical reconstruction of the printed holographic stereograms from different viewpoints, and in this experiment for the toggle printing process the only green laser beam illumination is applied, and as you can see from there you can see the full parallax information of the each reconstruction. And now let me show you the video of printed holographic stereogram, and from there you can feel the full parallax and depth information of the 3D objects. And for each printed holographic stereogram, here 50 by 50 holes are printed into holographic material, and each hole size is 1 millimeter. Now I will present a numerical simulation for full color toggle generation, and in this numerical simulation the simple object OYP letter with different depth is utilized as a 3D object, and from the 3D object 30 by 30 elemental images are generated based on IDP algorithm as shown here, and also generated phase modulated RGB channels of Hoggle is presented here. And in this table demonstrates the comparison of computation time and for the used object, which has over the 1 million points. And as you can see from the table, in the conventional method, the elemental image array is generated by 1.17 seconds in GPU computation without occlusion effect, whereas the proposed method, elemental image array is generated in 0.84 seconds in GPU computation, including the occlusion effect. So it means the proposed method is effectively generate the elemental image array within the fast computation without degrading the image quality. And also for the CJ generation for the RGB channels, the computation total time is 193.2 seconds in GPU computation, and also the specification of the utilized personal computer in the experiment, numerical experiment, is shown here. Also, as presented in this figure, the final CJ patterns of the RGB channels for the single Hoggles are obtained by adding the optimized phase shifting fringe patterns for the corresponding channels. And here the numerical reconstruction of the phase modulated single full color Hoggle is shown, and it's verified the full color Hoggle generation, where RGB channels of single Hoggle is reconstructed at the same coordinate without the chromatic dispersion error. Optical experimental result. So before applying full color Hoggle printing process, the each channel recording of Hoggle with the corresponding laser beam illumination is implemented, because it's need to define the optimized the optical condition for the each channel of Hoggle recording to get the uniform holographic stereogram. And from the reconstruction of the each channel Hoggle recording, the 3D visualization of used 3D object is observed successively with the full parallax and depth information. And also the parameters used in the optical experiment is shown in this table. As you can see from the table, here 30 by 30 Hoggles are recorded, and the printed Hoggle size is 1 by 1 millimeter, and material shifting distance is 1 millimeter. And also in the optical experiment, the Holla Eye Leto is used, and it has a 6.4 micrometer pixel pitch. And for the holographic material, we use the Litho Hollow material. And for the printing time, it takes 1 hour, and for the field of view is 15 degrees. Conclusion and future work. In this paper, full-color holographic stereogram printing system using fast digital content generation based on IDP algorithm is proposed, and the digital content generation of full-color Hoggle is fully analyzed. And also before applying the full-color Hoggle printing, each channel's recording of Hoggle is implemented optically, and the 3D visualization of the used object is observed successfully by including the full parallax and depth information. So our future research focus on the optical optimization for full color Hoggle printing to obtain color uniform holographic stereogram. Thank you for the pay attention.
Thank you for that insightful presentation, Dr. Anand. Now, moving on to our next presentation by Dr. Nemsiren Darkhan Batar from Changu National University, South Korea, and presenting on the title, The LCMLA using the Holographic Waveguide Type HOE for 2D, 3D Image Switchable. Hello, Dr. Nemsiren, you can start your presentation. Hello, Doctor. Please share it in a full screen mode, doctor. Hello, hello, doctor. Hello. Hello, Dr. Nansurin. Please use your screen.
Hello.
Hello, doctor.
My presentation is now playing, but it's didn't hear. You didn't hear.
Please send me.
Please wait a minute.
Please use that green color button, screen share button. Okay, doctor. You can start your presentation now.
Excuse me.
Yes, doctor, please.
Did you hear that?
No, doctor. When you're sharing your screen, please click on that share sound option as well. Please
now
try again.
Now I play, and you can take this, and you can. Okay.
Okay, okay. Hello, doctor.
Oh yes, I running.
Please try again. Please once try again.
Okay.
Okay. Please click on your share screen button at the bottom of your Zoom meetings window. And at that time, share your computer sound with other applications also.
Please take a minute.
Okay. Hi, doctor. It's not audible. The sound is not working. Please close this video and open it again.
Okay.
Once close this and please share again.
Excuse me, and I will running the presentation. Will you check it?
But it's not audible, doctor.
Hello everyone, my name is Nimsur. Hello everyone, my name is Nimsuranda Hambatar from Chungbuk National University, South Korea. Today's my talk. Did you hear that?
Yes, doctor. It's fine now.
Final mark.
You can start your presentation. Thank you.
Okay. Hello everyone, my name is Nimsuranda Hambatar from Chungbuk National University, South Korea. Today's my topic is the liquid crystal microlens array using the holographic waveguide type holographic optical element for 2D and 3D image searchable. Here is my content. Firstly, I will introduce of the augmented reality technique, and then I proposed my method, and I will explaining my recording setup, and I will show you experimental result, and finally I will conclude my talk and future plan. Here is the introduction of the augmented reality technique. Augmented reality technique is a system for the head-mounted display, have attracted considerable interest because it allows the users to observe virtual computer-generated precipitation in a real-world environment. The most of AR head-mounted displays are glasses or helmets, and this is all virtual space. Basically divided three types system, and first is projective AR system. It is the project directly onto real object with dark environment. Second is video see-through AR system. It is the composite captured reality video with virtual images. Third is optical see-through AR system. This system is direct wave of the real world through the optical combiner. Usually, optical combiner is the holographic optical element. Our study is based on optical see-through AR system. AR system. However, most such systems are considerably bulky or heavy because the feature of the microcomputer, projector, a prism and mirror, micro lens, and a half mirror. They create discomfort if worn for a long period. Therefore, the AR head-mounted display must be highly portable and as light as possible. This slide is showing introduction of conventional holographic waveguide. This figure shows the basic diagram of conventional holographic AR system. In this system, waveguide display and waveguide, also in and out coupler, holographic optical element, and observer eye. The many AR head-mounted displays features a waveguide type structure. It's the involving and combiner class of the predetermined thickness, which transmits light between two fields, in and out couplers, by guiding the waves propagated via total internal reflection without any loss of input information. The light is transmitted from the microdisplay to observer eye. An image from the microdisplay is collimated by the lens for a plane wave, which is diffracted onto the in-coupler with the incident angle dictated by the waveguide. The light wave is then modulated, sent through the glass waveguide, then coupled out by the out coupler prior to delivery to observer's eye as an original light. Several types of the waveguide exist according to the properties of in and out couplers: reflective, polarized, diffractive, and the holographic type. Among them, the holographic waveguides are appropriate for the augmented AR head-mounted displays because the thin films are used to guide the light beams, so the device size and weight are reduced. The thin films of the in and out couplers are composite of the holographic optical elements, which are fabricated using the holographic recording method. Here is our proposed method, waveguide type 3D AR display. This figure shows the symmetric of the 3D AR display system. The proposed system features a waveguide with the two HOVs and a micro display, a generated lambda image set based on computer-generated integral imaging. Imaging is displayed by the micro display, reconstructed as a 3D image via the holographic mirror array in coupler, and then input to waveguide at the incident angle that is greater than a statistical angle. The light beams are propagated inside the waveguide to ensure total internal reflection. After the incoherent light beams of reconstructed 3D images are reflected within the waveguide, they are sent to the aft coupler and then reflect to the observer's eye. Both the aft coupler and in couplers are seen through holographic mirrors, which diffract light beams. Features of the 3D AR system display. The reconstructed 3D image resolution and the real-world scans at the same time by holographic mirror array, which using the integral imaging technique, and this system using any additional optical element or device, and holographic mirror array is fabricated through the conventional optical element, is micro lens array and optical mirror, and fabricated in coupler. Holographic mirror array is for a 3D image construct, and holographic mirror array shapes and function is same as the micro lens array but doesn't flat. It's a convex or concave, and field of view is increased compared with the conventional holographic AR display system. Here is the conventional and proposed methods compressed. Conventional mirror arrays. The conventional mirror arrays are high costly, and it's very hard to find mirror array with the decided specifications. It's possible to manufacture the mirror array by using some chemical elements, and the manufacturing process is too complicated, and also the hazardous due to the chemical elements. And our proposed holographic mirror array is the recording process using the hologram recording process and recorded function of the micro lens array and mirror in the recording material photopolymer. And fabricating process of the holographic mirror array simply doesn't high cost and doesn't using any chemical elements. Here is the recording setup in coupler holographic mirror array. Our recording setup is using the laser 532 nanometer and diurnal density filter and half-wave plate and special filter, electrical shutter and collimating lens, aperture, polarizing beam splitter and micro lens array and lens reflecting mirror, reference mirror for the holographic mirror array, the magnetic filter, holographic optical element. Here is the laser beam is passed through the neutral density filter and half-wave plate at which is the control the power ratio between reference and signal beams. Electrical shutter extended by the special filter, the collimating lens and aperture. The transmitted beam is split by the polarizing beam splitter into reference and signal beam. A conventional lens array and optical mirror serve as the point as reference. Both optical functions are recorded on holographic material using the total internal reflection using prism. The waveguide and the recording material are placed between two right-angle prisms that alter the reflective indices. The signal beam is transmitted through the half-wave plate 2, which is in source as polarization of the two beams. It's then reflected onto the reference mirror and absorbed by the holographic material via prism 2 with an incident angle. Simultaneously, the reference beam is passed through a micro lens array for a lens system, which recorded the original size of the micro lens array on the holographic material, and is then recorded on material through the prism 1 perpendicularly. Thus, both signal and reference beams are purified through the prism and identical recording and different diffraction angles during holographic mirror array
proliferation, the elemental mirror array may be concave or convex depending on the applying. The array can be adjusted over 118 degrees, and the size and focal length are adjusted by moving the recording plane within a region of the micro lens array. Here is the recording setup of aft-coupler HOV. This figure shows the symmetric configuration of aft-coupler HOV fabrication, which is similar to in-coupler holographic mirror array fabrication, but the 4F lens system and micro lens array are absent because the only reflection is required. A larger beam passes through the NDF and half-wave flat one and electrical shutter and culminating length. The extended beam is divided by the polarizing beam splitter into signal and difference beam, which are reflected to mirrors respectively. Two beams thus cross the recording material from the opposite direction. The signal beam passes through the prism tube and waveguide and is recorded by the holographic material at an incident angle. The reference beam is recorded perpendicularly to material after passing through the prism line. Here is the handling process of the holographic mirror array and aft-coupler HOV recording setup. For the in-coupler HOV reference beam should be reflecting the beam a certain angle, which is the incident of the 90 degree, whereas the aft-coupler HOV needs to reflect in the 90 degree, which is transmitted beam in the waveguide at the 15 degree. In the in-coupler HOV recording procedure, a HOV is located on the signal beam side, hence in and aft-coupler HOV recorded procedure and HOV is located on the reference beam side. Here is the experiment recording process of the holographic mirror array and aft-coupler HOV. And here is the in and aft-coupler HOVs are recorded through the total internal reflection using prism recording method according to the recording condition based on the inhibition characteristic of the photopolymer and enlarged of both recorded HOVs are shown. Note that the HOVs must be reflection type for holographic waveguide type air display in the holographic mirror array function 120 concave micro mirror of 1 mm pitch was recorded on an approximately and 20 by 10 mm area of baffle HX 1 layer 2 photopolymer. The focal length of each entire micro mirror was 3.3 mm, and the recorded aft-coupler HOV area was identical to area of the holographic mirror array per approximately 20 by 10 mm. Both HOVs employed in identical flat optical mirrors. Also, the exposure time for each HOV recording was 7 to 8 seconds. The power of the signal and reference beams were 1 milliwatt, and identical intensity ratio of optical signal and reference beams was 1/6 due to the reference lens array, and half-wave flat one reduces the intensity of the signal beam to the ratio of 1/1. Beams of the similar intensity were delivered to the photopolymer. The reference beam passed through all of the microlenses. After recording, both HOVs were fixed by the helical lamp, illustrated 50 mm distance from recorded HOV. The diffraction efficiency of half mirror array was approximately 82%, and aft coupler HOV's diffraction efficiency is approximately 95%. Here is the experimental setup for AR display. Implementation of the proposed 3D AR display system and the side view of the proposed method with real object. Here is the distance between in and aft coupler is 11.4 mm. Total distance of traveling between the waveguide is 23.9 mm. Camera is we was using Sony Alpha 900, and micro display bright is 800 CD, and here is the distance between real object and aft coupler HOV is 45 mm, and waveguide thickness was 5 mm, height is 30 mm, width is 17 mm. Micro display resolution is resolution and fixed pitch in size is in here. Here is the optical reconstruction. We was using the integral imaging technique. The elemental image is a good application for AR display because it provides full parallax 3D image and supplies various physiological depth so that viewers can freely change the accommodation and convergence between the virtual 3D image and the real world scene without feeling any visual discomfort. We are created the OIP letters, and OIP, always distance from display is 10 mm, I is 25 mm, and P is 20 mm. And here is the reconstructed result. The reconstructed image and real objects are able to observe well in dark environment rather than in light environment. Yes, it is shown the reconstructed 3D image. It is reconstructed the star. Star is stars of elemental images created by integral imaging technique and displayed by micro display, and reconstructed image is passing through the waveguide and reflected on optocoupler Joey. Observer can then reflect the reconstructed image can see. Here is the first picture is captures the dark environment, and Kitty was longer than focal point, and second picture is dark environment and Kitty and star is same location, and third is Kitty and star was same location and a bright environment. Here is my conclusion and next plan. The holographic waveguide type 3D air display was based on integral imaging techniques proposed. The proposed system doesn't require any additional device to display the 3D image, but consisted of the main devices of the conventional holographic waveguide-based AR display, the fabricated holographic mirror array for 3D image reconstructs, which it was the recorded function of microlens array and mirror, and it was based on holographic recorded system. The optocoupler usually was recorded function of only mirror, which is following the holographic recording process. The future research focus on fully implementing the 3D AR display using a full color holographic mirror array, improving image quality in reconstruction. Thank you for attention.
Thank you for that insightful talk, Dr. Darkhan Batar. Now the stage is open for questions. Okay, Doctor, I assume that you have no questions from the speakers. Once again, I thank you for being a part of this webinar and hope to associate with you in your future events as well. Thank you.
Yeah, thank you.
Thank you so much.
Thank you so much.
Now moving on to our next plenary presentation by Professor Sukhdev Rai, Dayal Bhag Educational Institute, India, and presenting on the title Low Power and High Frequency Optogenetic Control of Neuronal Spiking. Hello, Professor Sukhdev Rai, you can start your presentation.
Okay, thank you very much.
Okay, Doctor.
Let me share my screen. Please let me know if you can see the slides.
Yes, Doctor, it's fine. You can start.
And can you hear me also clearly?
Yes, Doctor, clearly.
Okay, fine.
Thank
you see, the title of my talk is Low Power and High Frequency Optogenetic Control of Neuronal Spiking. Now, let us first look at what exactly is the main basic scientific challenges. Now, we are still trying to understand what is a human being, what is the mind-body relationship between in a person. So first of all, let me tell you the outline. I would first focus on importance of optogenetics, then discuss computational optogenetics, then low power and high frequency control of neurons, excitation, inhibition, and bidirectional control. Then present results on optogenetic retinal prosthesis, and then finally conclude. So the point is that we are confronted with very fundamental questions as to what is health and well-being, and we feel that it all depends upon our understanding of how the brain works. All right. And finally, the most important question as to what is consciousness and how can we measure it. So it's a transdisciplinary topic, and we need ideas from different subjects, different branches of human knowledge in order to answer these fundamental questions. So there are many unresolved medical challenges like blindness, cancer, immunological diseases, neurological disorders, all right? And there are several challenges in neuroscience, from consciousness, perception, learning and memory, neuroplasticity, free will, sleep, language, diseases, right? So the point is, human brain is very complex. It's the complexity of the human brain can be ascertained from the phenomenal memory capability and computational speed.
It's made of maybe thousands of different kinds of.
Now, the point is, the brain is the most complex system in the known universe. And we need to understand its architecture, its functions, how signal processing takes place, and how can we then control this signal processing through a non-invasive, non-intrusive, high-precision manner where we can control a single neuron with very high efficiency, fast control, and of course, the method has to be cost-effective. So the understanding the brain is something which is very, very challenging, and people are claiming that the new century is this 21st century is the century of the brain. Now, why we are so optimistic is because we have developed very advanced neuroimaging tools, such as the functional magnetic resonance imaging. So here what we have is, when a person performs any function, we can image the bold signal, that is blood oxygen level detection, and we can then try to figure out what parts of the brain actually are involved in that functioning. But those small parts of the brain also are those clusters have hundreds or thousands of neurons, all right? So that we do not have the desired spatio-temporal resolution in order to understand how the brain functions. So there are several global initiatives on brain research, the European, the American, the Swiss Brain Project, the Human Connectome Project, and so on and so forth, with billions of dollars in euros, which have been invested on brain research. A very important question that arises is, does the brain have anything to do with light? Can it be controlled by light? In fact, in a paper published in 2016, people theoretically showed that there are microtubules within the neurons, and there one can consider them to be analogous to optical fibers, where optical signals or biophotons can traverse. And there's another important theory proposed by Sir Roger Penrose and Stuart Hameroff, that there might be quantum processing taking place inside the brain, and these microtubules could be the the systems where the coherence, quantum coherence, can exist for a long time. Now, in 2005, a very revolutionary idea was proposed, and what was proposed was the following: that we have natural photosensory receptors, all right, which have been discovered, one of them being channel rhodopsin, which was discovered in 2002. Now, this is a rhodopsin protein. So when you shine light, it allows ions to permeate from the extracellular to the intracellular side of the membrane. And then people thought that if we can integrate them or genetically code them into neurons, then we can make neurons sensitive to light, so that the ion transfer can trigger action potentials, and one can then fire or control the neuron. So this very exciting area is called optogenetics, controlling the brain with light, which was the method of the year in 2010, and also received the Brain Prize in 2013, shared by 6 eminent scientists. Now, this is what happens. So the light-sensitive protein from, let's say, Chlamydomonas reinhardti, right, an algae, is taken, and then through a vector, it is inserted into neurons. So a neuron then grows with these channel rhodopsins onto its surface, and when you shine blue pulses of light, the channels allow ions to pass through. They open and close based on the excitation with blue light, and therefore you can trigger action potentials. Now, we know that there are photoreceptor cells in the retina which get damaged through age, and people have thought that how can we cure blindness? So if you insert channel rhodopsins, all right, these light sensitive proteins, then you can see that a blind mice is not able to find its way inside this maze, but a treated mice is immediately able to perceive and then find its way. So optogenetics has tremendous potential in various research studies, neurological studies. Here you have a mouse which is very well fed, and it is not it doesn't have the capacity to eat, but through an optical fiber cable in a part of its brain, when the light pulse comes in, it triggers the neurons and it starts again having this urge to eat, all right? And as soon as the pulse is switched off, it does not eat anything. So again, as the pulse arrives, it starts eating. So people claim that they have found neurons responsible for overeating. So using optogenetics in different parts of the brain, one can then study the functionality of the brain at unprecedented spatial temporal resolution. The other thing is that a constraint which you find in optogenetics is that if you have an optical fiber attached to the brain of an animal, then it is confined to move only in a small area. But it would be good to see or study behaviors, all right, of animals if they can be freely moving. So wireless optogenetics has also been proposed and implemented with electrodes, with self-powered electrodes, and this is a very important development for nanoBiophotonics, all right, using nano electrodes with biophotonics. Now we have these small electrodes, electric or optic, which are available commercially also, and one can then study the subject and study what parts of the brain control what kind of functionality, all right? Now, the important point to note here is that the photoreceptors that are introduced into different kinds of neurons are very, very important. Now, they are very sensitive to different wavelengths of light. So they have their own absorption spectrum and so on and so forth. So wide range of photoreceptors have been discovered and engineered for desired applications. So for example, you have photoreceptors which can excite a neuron. So when the light is on, it starts firing. Similarly, you have photoreceptors which can inhibit a firing neuron. So when the light is on, this orange light, then the spikes during that period are switched off. So this graph shows you various kinds of photoreceptors. These are optogenetic tools that are very, very important, and we need high spatiotemporal resolution. So the kinetics should be very fast so that we can control it very with high frequency. The other thing is that it should be very sensitive to light so that with low power and minimizing heating effects in the brain, we can control different neurons in different parts of the brain. The other important aspect is we can also co-express excitatory and inhibitory opsin, and we can have both excitation and inhibition, and this is called bidirectional control. So having pairs of photoreceptors, one can control different neurons in different parts of the brain, and then one can study anxiety, Parkinson's disease, auditory system, memory deficits, and other kinds of neurological disorders, and to see which neurons play a role in different ailments. The challenges here are low power control, high frequency control, temporal precision. So if I have a pulse, let's say at a particular time interval, then it should be able to precisely excite or switch off, inhibit firing neuron. Then we should be minimizing heating effects, and we should have deep penetration of light so that we can control neurons which are deeply situated inside the brain. Then we should have capability of independent population control also. So these are some of the main challenges that are faced by optogenetics. Now, computational optogenetics again is something which is very important. You see, you cannot do experiments you can in different conditions. There is a limitation to how many experiments you can do. So therefore, theoretical simulations or theoretical modeling or computational optogenetics becomes important so that one can study different photostimulation conditions and then optimize those conditions and predict what would happen, all right, under different circumstances with different kinds of options and so on and so forth, so that the experimentalists can then fine-tune their experiments and achieve the desired spatial and temporal resolution. So in computational optogenetics, you have these two aspects. Number one has to accurately model the photocurrent of the opsin, all right, the channel rhodopsin. So you have 3-state or 4-state model depending upon the experimental data available, the characterization data, spectroscopic characterization data. One then looks at different transitions, whether thermal or photo induced transitions, and they all exhibit a photocycle. All right. So we have to accurately model the photo response and then integrate this photo response in a accurate neuron model. So there are different kinds of neurons in the brain, and so therefore there are different kinds of models that have been proposed. And then one has to first validate the model with experimental results which have been reported in the literature, and then look at optimizing the results for making better experiments or achieving better resolution. So these are like channel rhodopsin 2 and chronos, right? There are protein, very important ones, rhodopsin, which can be modeled through a 4-state theoretical model. And you can find the parameters from the spectroscopic data which has been reported in the literature. Similarly, for inhibitors, you have these different options which have been discovered, and one can accurately model. We have seen through a 3-state model for these two. And then there are different effects which one can take into account, such as chloride rebound effect, blue light activation effect, and so on and so forth. Now, there are different kinds of neurons, and there are different kinds of models which have been proposed in the literature. One of them is the Hemon neuron circuit model. All right, so there are these different gating variables, the different ion currents, all right, and their functions, which have to be taken into account in the theoretical model. Similarly, you have the interneurons, which are fast switching neurons, and the Wang-Buzaki neuron circuit model is a very fundamental model which is used to simulate or model their response. So these are the gating functions and the values of different parameters, all right, which can be used. So theoretical simulations. Now, in the year 2014, a very interesting discovery was made, and this was by a group at MIT. So they discovered chronos, a new kind of channel rhodopsin with very high photocurrent, very high light sensitivity in the blue-green region, and it has the fastest reported kinetics to date with an on-off time of 2.3 and 3.6 milliseconds, with 100% spiking at 0.05 milliwatt per millimeter square to 20 milliwatt per millimeter square, and it can robustly mediate light sensitivity and control neuron spiking across a range of expression levels. So we undertook a detailed theoretical analysis of using chronos in optogenetic switching of neurons. So first we validated our models. You can see the comparison between experiment and theory. Experiment was reported at 5 milliwatt per millimeter square, and the theoretical results are in very good agreement with experiment. And then one can see that even at 2 milliwatt per millimeter square, the switching is reproducible. Similarly, here you have the comparison between experiment and theory for CHR2 and chronos. So you can see chronos is very, very sensitive to light, so that even at 0.1 milliwatt per millimeter square, it shows full switching characteristics, whereas CHR2 is not able to invoke spikes, all right, at that low intensity. Here is the effect of conductance and pulse width. So if you increase the conductance or the pulse width, you have multiple spikes coming in, which is not a desirable feature. And we have worked out what exactly is the effect of the stimulus rate, all right, as you increase the stimulus rate, how exactly is the driven rate, okay, how does the spikes get affected. So this was reported in Neurophotonics in 2018, and you can look into the more details in this paper. Now, blue light scatters most, we know this, and it is not able to penetrate deep inside the brain tissue. So therefore, what is desirable is red-shifted channel rhodopsins. Now, a group at Max Planck Institute in Frankfurt came upon another very important and interesting crimson mutant, all right? And this is called very fast crimson. So we undertook a theoretical study of this also, and we first validated our theoretical model with experiments, and by accurately simulating the experiments, as you can see from the slide, and then optimizing the characteristics for high frequency firing. And we showed that at this combination of parameters, you can switch the neurons to as high a frequency as 1 kilohertz. All right. So 60 hertz, 80 hertz, 100 hertz is very high in any case, but you can even go to as high as 1 kilohertz. So this was reported again in Neurophotonics in 2019, and one can look into the details. Now we come to inhibition. Now this is netronoferonis halorhodopsin, which is an inhibitor. So you can see the experiment that has been reported that as soon as this orange pulse comes in, the spikes are switched off. And here our theory is also in excellent agreement with the reported experimental results. Same is the case here with experiment and theory. Then precise inhibition of spikes, so at different time intervals, we have these different pulses, and you can see that they are able to inhibit a spiking neuron, all right, very accurately, precisely. So this again is very well matched with the theoretical simulations. So based on this, one can then look at optimization of inhibition at high frequencies, and for ENPHR3 and JAWS, you can see that one can go to 160 hertz, 200 hertz, and 250 hertz also. So that's a high frequency. This was published in Biomedical Physics and Engineering Express in 2020. Now, a group, the pioneering group by Carl Dizerath at Stanford University discovered CHR mine, all right? Another very important, channel rhodopsin with very interesting characteristics with large photocurrent, high sensitivity. So we have undertaken a detailed theoretical analysis here as well. And so you can see the comparison is excellent with experiments. And then we also worked out bidirectional optogenetics with these different pairs which have been reported in the literature, and then looked at the excitatory and inhibitory options, and then chose the most recent ones, the best ones that have been reported with the best characteristics, and then theoretically simulated the new prospective opsin pairs such as Chronos JAWS, Kerif JAWS, Chronos and EPHR 3.0, and so on and so forth. So here you can see these are the experiments reported in Nature in 2007, the experiment and theory, which is in good agreement. And then by validating these results, then we have worked out the high frequency limit with CHR2 NPHR for hippocampal neurons and neocortical neurons. So you can go up to 60 hertz and 100 hertz for neocortical neurons. Then this new pair of opsins, Chronos and JAWS, which are the best ones, all right, with the best characteristics, when we have shown that in hippocampal neurons, you can go to a firing frequency of 90 hertz, whereas in neurocortical neurons, you can go to as high as 180 hertz. Again, for another opsin pair, one can go up to 250 hertz, all right, and this was published in Neuroscience into 2020, the bidirectional optogenetic control. Now, another important problem in medical science is retinal or blindness, retinal degenerative diseases. Now, there are different treatments, but optogenetic treatment has tremendous, power based on spatial resolution and being a non-invasive technique. So one can go for applications of optogenetics in retinal prosthesis. So here, there's the first clinical report on human trials where a partial recovery has been reported in Nature Medicine in 2021, where a visually blind patient was able to recover vision partially, all right, through optogenetic approach. So here, the channel rhodopsin that they used was Crimson R, all right, along with goggles which actually focus the light at different parts of the retina. So we now did a very interesting theoretical study with CHR mine, the newly discovered protein by the Stanford group. So this is redshifted activation, large photocurrent, fast turnoff, and fast recovery kinetics. And we showed that it is very suitable for improved optogenetic retinal prosthesis. And CHR mine expressing retinal ganglion neurons begin to respond at very, very low, ultra low intensities, 10 to the power minus 4 milliwatt per millimeter square. All right. So you can see the comparison with these different ones, and you can see that even at 10 to the power minus 4, CHR mine shows spiking, whereas crimson R, which has been reported in Nature Medicine, is not able to switch that with that intensity. So here we have spike latency, an order of magnitude shorter first spike latency in CHR mine expressing RGNs, then stable latency of subsequent spikes in CHR mine expressing RGNs has been observed. Then our theoretical simulations show that high frequency limit with single spike resolution with CHR mine expressing RGNs can be 40 Hertz, which is 2 orders lower than the safety threshold because it is so sensitive to light. And for crimson R expressing RGNs, you can go up to 100 Hertz, but that exceeds the safety threshold. So CHR mine has tremendous potential for retinal, prosthesis. So you have redshifted activation of CHR mine, which is another advantage. Theoretical model we have reported for the first time, and this can be integrated with other neurons. And this is very important for low power and high frequency optogenetic retinal prosthetics. So CHR mine, with 2 milliseconds time, 40 Hertz and 0.6 microwatts per millimeter square with 280 Hertz of maximum firing frequency under continuous illumination far exceeds what you can with other, options. So this was published in Journal of Neural Engineering in 2021, and one can look into the details. Now, in a very recent one published in this month, in Journal of Neural Engineering, we have shown that if you co-express a fast channel adoption with a step function option, then you can overcome the spike failure due to photocurrent desensitization in optogenetics, which is a very fundamental issue and challenge in optogenetics. So this is a theoretical work and theoretical simulation, and then we expect that the experimental scientists would take up this idea and then verify it experimentally. So to conclude, we have formulated accurate theoretical models for photoresponse of opsins, then optogenetic control of opsin expressing neurons, excitation, inhibition, and bidirectional. Then we have focused on hippocampal neurons and fast spiking interneurons. And then we have optimized the photostimulation conditions for continuous and pulsed illumination so that we can have low power excitation or control of neurons, high frequency control, and temporally precise control. So experimentally reported options, you can see here, new prospective options you can see, and you can see that, they can go for very high frequencies, and the proposed ones which have not been studied experimentally and reported in the literature, these pairs can give us better results. So fast and cost-effective method to engineer photoresponse of opsins and optimize photostimulation conditions has been reported. Models can be easily integrated to different kinds of neurons and can be upgraded to large neuron population. We can design new optogenetic experiments with higher spatiotemporal resolution. Then these new prospective opsin pairs would enable low power and high frequency control required to probe various neural phenomena. So you see, when you are, there are different phenomena in the brain functioning, which require long-term, sustained excitation of neurons in order to study the functionality. So these results will be, useful for those studies. Then we have a very important, challenge as to what is the neural coding that takes place. How does the signal processing or codes, are deciphered in different parts of the brain, and how do they propagate, and so on and so forth. So this could lead also to understanding neuronal coding. So thank you very much for your kind attention. And if there are any questions, I would be very happy to answer.
Thank you for that insightful presentation, Professor. Now the stage is open for questions.
Hello?
Hello, Doctor. The stage is open for questions now.
Hello?
Hello, Doctor. Can you hear me? Okay, Doctor. I assume that you have no questions from the speakers.
Hello?
Once again, hello? Hello, doctor.
Would there be any questions?
Yes, doctor. The stage is open for questions. So we'll wait for another 2 minutes.
From anybody?
We'll see, doctor.
Hello?
Okay, doctor. I assume that you have no questions from the speakers. Once again, I thank you for being a part of this webinar and hope to associate with you in our future events as well. Thank you so much, Professor.
Thank you.
Thank you. So with this, we completed with all the presentations for day 2. So once again, I thank you all for making this webinar a huge success and hoping that our association continues for further events. If you have any queries, please write back to your conference secretary. And we are closing the session now. Thank you, everyone. Thank you for your participation.
Thank you.
Thank you.
Thank you.